Hi, and welcome to the Applied Machine Learning component of the University of Michigan's online course in Applied Data Science. My name is Kevin Collins Thompson, and I'm an Associate Professor of Information and Computer Science at the University of Michigan. I'll be your instructor for this part of the course. I have about 20 years of research and development experience in applying machine learning to a wide variety of problems in both academia and industry, everything from language tutoring software to commercial search engines. This is an incredibly exciting time to be involved in machine learning, and I hope this part of the course inspires you to look more deeply into this fascinating world. This week, you'll learn what machine learning is and why it's important to data science, how machine learning is applied to key problems in our information economy, and how to set up your first machine learning application in Python. Okay, so what defines the field of machine learning? Well, in a lot of cases, when a computing problem needs to be solved, for example, storing and retrieving data from a database, the way we often address it is to write a program that manually specifies a series of programming steps that need to be run to solve that particular problem. This works great for the vast number of computer science problems that are out there. However, not all problems lend themselves to being solved effectively by writing a handcrafted program or a set of rules. For example, how would you write down a set of rules in a programming language for accurately converting human speech to text, a process known as speech recognition, which is now available on millions of smartphones or used in customer support systems all over the world? I mean, given how subtle and complex human speech is, with the huge variety of different pronunciations, vocabulary, accents, and so forth, writing a set of program rules by hand that could recognize portions of an audio signal and decide which words were in the signal and so forth would be a gargantuan task. And even then, it would still likely be inflexible and not very robust at recognizing different types of speech. Moreover, if we needed to customize the system so it could recognize new words or other features that we hadn't encoded in our existing rules, we'd have to write a whole new set of rules, which would be a prohibitively difficult task. Machine learning, on the other hand, gives us the technology that allows us to automatically learn these complex rules efficiently from labeled examples called training data in a way that is much more accurate and flexible than attempting to program all the rules by hand. Moreover, since it's unlikely any future examples we see would match exactly what was in the training set, a primary goal of effective machine learning algorithms is to be able to generalize, to correctly predict or recognize new objects that weren't seen during training. So the basic problem of machine learning is to explore how computers can program themselves to perform a task and to improve their performance automatically as they gain more experience. Now, this experience can take the form of data in a lot of different formats or situations, such as label examples that are used to train the system's initial structure, like in email spam detection. A system could get feedback from the user. For example, a search engine gets clicks on the search page. Or a system could get data from the surrounding environment that's gathered over time. For example, self-driving cars that can detect nearby objects and events and learn to move more reliably. To accomplish this goal effectively and efficiently, machine learning draws heavily on statistics and computer science. These statistical methods give machine learning algorithms ways to infer conclusions from data and to learn from data, and also to estimate how reliable those conclusions are. Computer science methods, on the other hand, give machine learning algorithms the computing power to solve problems, including effective large-scale computational architectures and algorithms for capturing, manipulating, indexing, combining, and performing predictions with data. Think about how quickly a commercial search engine can match your query against billions of web pages and almost instantly return a set of useful results. That's an ideal illustration of the power of combining statistical methods with computer science. There are also growing connections between machine learning and other fields that are really fascinating. For example, the problem of how someone or an individual or a system can optimize their performance in a given environment is also shared somewhat with research that people have done in biology on how organisms forage for food. It also connects to research in economics on how optimal pricing and market structures can be computed. And even psychology, especially psychology, where we have models and factors of human learning and are using those to influence the design of machine learning techniques. So this evolving field of machine learning really brings together insights across multiple scientific fields. And that's one of the things that I find so fascinating about it. Machine learning algorithms are now involved in more and more aspects of everyday life, from what you read and watch, to how you shop, to who you meet, and how you travel. Here are just a few examples. For example, fraud detection. Every time you buy something using a credit card, machine learning algorithms immediately check your purchase to verify whether or not this might be a fraudulent transaction. To do this, these algorithms look at features of the current transaction that you've just made, such as the time, location, and amount, and they make a prediction of whether it's fraudulent or not based on whether that purchase is consistent with the features of your previous purchases. The system also records any user feedback on whether the transaction was in fact fraudulent, and it uses that feedback to make better predictions in the future. Search and recommendation systems are also a huge area of application for machine learning. And in fact, those machine learning algorithms are at the heart of how commercial search engines work, starting with the moment you begin typing in a query. So one algorithm might monitor your keystrokes to predict the best queries to autocomplete while you're typing. And then once you've finished your query, some other machine learning algorithms will be applied to determine the selection and ranking of the web pages that you see for that query. Still other machine learning algorithms will determine which ads, if any, you see on the page, which related queries the system suggests for you, and so forth. In addition, search engines typically use data about how you interact with the search site, such as which pages you click, how long you read the pages, to improve their future effectiveness. In a similar way, movie recommendation sites use machine learning algorithms to model what you liked in your past reviews, based on your past reviews and your interaction patterns with the site, and how your preferences relate to those of other users. And it uses this data to learn a model for your personal taste, to hopefully give you better choices that keep you more engaged with the site, or that leads you to make more movie purchases over time. And then finally, a third example area that's really seen a significant improvement in the past several years in terms of recognition quality, speech and image recognition. So although researchers have been working on speech and image recognition for decades, recently the development of increased computing power, better algorithms, including the use of deep learning, and vastly increased volumes of data have all led to a significant jump in accuracy and flexibility of recognition algorithms in the last 5 years or so. Now, recognition technology is reliable enough and fast enough that it's used as an essential feature of smartphones and home devices that can act on spoken commands or questions. Computer vision and image recognition can now give increasingly accurate identification of objects and actions in images or video. Even for a while now, over 85% of handwritten mail is sorted automatically with very high accuracy by the United States Postal Service. There are very exciting advances in the medical domain, where image recognition algorithms are being developed to classify cancer cells as malignant or benign, estimate the best course of personalized treatment, or to find hard-to-detect tumors in medical images. And of course, self-driving or autonomous vehicles make extensive use of real-time image recognition and video processing, as well as other technologies such as reinforcement learning. Now, these examples only scratch the surface of how machine learning is being applied in today's society, and we'll encounter and work with some other examples during the progression of this course. The name of this course module is actually Applied Machine Learning. So what does the applied part mean? Well, when we designed this data science series, we felt there was a need for a course that focused more on how to properly apply and interpret the results from machine learning algorithms at a high level, and less on the technical details of exactly how these algorithms work internally. There are a number of excellent existing core machine learning courses that already provide that deeper level of technical detail. And that detailed knowledge isn't always necessary to work with machine learning algorithms and to use them for specific applications. In fact, there's a very exciting trend happening where ready-to-use machine learning algorithms for speech recognition, language translation, text classifications, and many other tasks are now being offered as web-based services on cloud computing platforms, greatly increasing the audience of developers that are able to use them, and making it easier than ever to put together solutions that apply machine learning at a high level. The following book, Introduction to Machine Learning with Python, is not required to complete the course, but we recommend it as an additional resource that may be useful to you as you progress and for later reference. Like this course, the book focuses on the practical details of building your own solutions to machine learning tasks using scikit-learn in Python. It provides further background on machine learning concepts, more depth on specific topics covered in this course, as well as a number of additional topics, and some additional coding examples. Machine learning tasks, including the ones I've described as examples, credit card fraud detection, movie recommendation, speech recognition, and so on, can be categorized into two main types. The first type is known as supervised learning. And here, our goal is to predict some output variable that's associated with each input item. So if the output is a category, a finite number of possibilities, such as a fraudulent or not fraudulent prediction for a credit card transaction, or maybe it's the English word associated with an audio signal for speech recognition, we call this a classification problem within supervised learning. And the function that we learn is called a classifier. If the output variable we want to predict is not a category, but a real valued number, like the amount of time in seconds it would likely take a car to accelerate from 0 to 100 kilometers per hour, we call that a regression problem, and we're learning something called a regression function. More formally, we typically denote a table of data items using capital letter X, and there's one data item per row, and the labels that we associate with each item are stored in a variable y. And our goal is to learn some function that maps a data item in X to a label in y. And to do this, the system's given a set of labeled training examples of inputs x sub I and outputs y sub I. And this set of labeled training examples is what's used to identify the function that best maps the input to the desired output. For example, if the supervised learning problem is image recognition, this involves building a classifier where the input, x sub I, could be a set of pixels that describe a single image, and the desired label, y sub I, might be the label of the object in the image. Now, there are many algorithms that scientists have developed that can do supervised learning that could be used to estimate this function f from the training data, and we'll cover a number of those algorithms in the course. Supervised learning needs to have this training set with labeled objects in order to make its predictions. But if the whole point is to predict these labels, where does this initial set of labeled items come from? The answer is that the training labels are typically provided by human judges. Now, obtaining labels for some problems can be easy or difficult, depending on how much labeled data is needed, the level of human expertise or expert knowledge that is needed to provide an accurate label, and the complexity of the labeling task, among other factors. Now, the use of crowdsourcing platforms like Amazon's Mechanical Turk or Crowdflower or others have been a significant source of explicitly provided labels from human workers, where customers with machine learning tasks that need labeling can connect with groups of workers that can provide labels using human intelligence. So those are more explicitly obtained labels. We can also obtain implicit labels. So for example, if a search engine detects a user clicking on a result link and then sees no more activity for another minute or two before the user comes back to the search engine, the system might use that activity as a kind of implicit label for that page. In other words, if the user took some time to visit the page, it was more likely that that page was relevant to their query. The second major class of machine learning algorithms is called unsupervised learning. In many cases, we only have input data. We don't have any labels to go with the data. And in those cases, the problems we can solve involve taking the input data and trying to find some kind of useful structure in it. Now, what do I mean by structure? Well, typically this means finding interesting clusters or groups within the data. So once we can discover this structure in the form of clusters, groups, or other interesting subsets, the structure can be used for tasks like producing a useful summary of the input data, maybe visualizing the structure. For example, if you run an e-commerce site that sells products to customers, let's suppose you've got many thousands or even millions of customers, you might want to know if you can categorize or group the customers into different types. For example, there might be power users who use more advanced features of the site. There might be quick browser type users who only look for a cheap discount and stay for very little time on the site itself. There could be sort of careful researcher type users who spend a lot of time comparing different items. And if you could take your data of how people interact with the site and use unsupervised learning to discover these different groups, you could imagine then maybe tailoring your site's offerings to each group so that improve the chance that a user from that group would maybe purchase a product or have a better experience using your site. Now, you don't know how many groups there are out there ahead of time or even what they look like, and you don't have any labeled examples. And so this is a classic example of an unsupervised learning problem. Another type of unsupervised learning problem that is very important is something like flagging abnormal access to a web server. So for security reasons, you might want to be notified if a website user is making requests that could be a cyber attack or is somehow very different from typical user behavior on your site. Since there can be many different types of hacking or intrusion attempts to break into the server or exploit it in some way, we don't have reliable training labels that we could use to train a classifier using supervised learning. Instead, we need an unsupervised approach that allows us to perform something called outlier detection that doesn't assume future attacks will be of the same form as previous attacks, but that does assume some features of attacks on the site will look different somehow than average user behavior. Okay, so suppose you have a situation where you think machine learning might be applicable, either using a supervised or an unsupervised approach. How would you apply machine learning to solve your problem? Well, there are three basic steps, and I'm going to use classification as my typical machine learning scenario, so I'll often just use the term classifiers as an example of a machine learning task. But what I'm about to describe applies to other forms of supervised learning like regression that we'll cover later, or unsupervised learning like clustering as well. So the first step in solving a problem with machine learning is you have to figure out how to represent the learning problem in terms of something the computer can understand. You need to be able to take your data or even formulate a description of your object that you're interested in recognizing, for example, in a way that you can use as input to an algorithm. And you also need to decide what type of learning algorithm to apply to this data. For example, there are many different ways you could represent an image. Typically, it's represented as an array of colored pixels. There could also be metadata associated with the image. You could think about how you might represent a credit card transaction if you want to do fraud detection. So that might be represented by the time, the place, and the amount of a transaction. So you need some way, some representation of the data you have and the choice of what kind of algorithm you want to apply to the data. The second thing you need to do is decide on an evaluation method that provides some type of quality or accuracy score for the predictions or the output that is coming out of the machine learning algorithm, typically, let's say, a classifier. So if you have an evaluation method, this allows you to assess and compare the effectiveness of different classifiers. So you can tell what classifiers are doing well, which are the good ones, and which are the bad ones for your particular problem. For example, a good classifier will have high accuracy. That is, it will make a prediction that matches the correct true label a high percentage of the time. The third thing you need to do in applying machine learning to solve a problem is once we've decided on how to represent the input data, the type of classifier, and an evaluation method, we need to then search for the optimal classifier that gives the best evaluation outcome for that problem. And we'll go into all three of these areas in this course. And then we'll use Python in this course as well to solve some specific examples. And we're about to see a concrete example of how we use machine learning libraries in Python to solve a classification problem. So let's go through these three steps in a little more detail now. Let's first talk about what it means to convert the problem into a representation that a computer can deal with. This involves two things. You need to convert each input object, which we often call a sample, into a set of features that describe the object. Second, we need to pick a learning model, typically the type of classifier that you want the system to learn. So let's look more closely at what we mean by a feature representation for an object. Each data point in your data set represents something, some object or situation or event, some entity that's being represented by a list of properties. For example, an email might be represented as a list of words that are in the message. A picture might be represented by a matrix of color values for the pixels that make up an image. A piece of fruit, like this apple, could be represented by its color, its shape, its texture, and so forth. So these attribute values for an object are called features. You can think of the input data containing this feature representation as the input to your function. You can visualize it easily as a table, where each row of the table represents a single data instance, and where the columns of the table represent the features of the object. There could be many different choices for how to represent an object using features. So, for example, I showed you a piece of fruit. Let's pick up a lemon. A lemon has a shape, a width, a height. It also has mass, taste, and I guess if you buy lemons in the store these days, they also come with a handy barcode that identifies the type of fruit that it is. So there are lots of different types of information we could gather about a thing in a form that a computer could understand. So this problem of trying to figure out how to represent an object for a machine learning algorithm is actually it's a challenge, and it's known as feature engineering or feature extraction, and we'll cover that in week 4 of the course. The other key part of representing a machine learning problem is choosing the type of classifier that's appropriate for the problem. And we'll cover many different types of classifiers in this course. They all have different trade-offs in terms of their accuracy, their interpretability, and their speed, and so forth. And we'll cover those in the second week of this course. So often the process of addressing a machine learning task is a cycle. It involves an iterative process, as I show here, where we make an initial guess about what some good features are for the problem and the classifier that might be appropriate. We then train the system using our training data, produce an evaluation, see how well the classifier works, and then based on what worked and what didn't work, which examples get classified correctly or incorrectly, we can do a failure analysis to see where the system is still making mistakes. And then with the results of that failure analysis, we typically will always refine the set of features. We may discover that an important feature is missing that would help fix some of the mistakes, for example. So in my experience, this iterative process is very common. In fact, it's very typical of solving problems with machine learning. Typically, you might want to go through this cycle several times to continually refine the features and assess their effect on accuracy, or look at try different types of classifiers based on the evaluation method that you've chosen in order to determine if you have the right approach for your problem. Okay, now that we've covered a little bit of background on what machine learning is and some of the major types of machine learning problems, there's nothing like getting started with our own machine learning application in Python. And we're going to get started on that right now. So to do that, we're going to make use of several important Python libraries that will support our work. These include scikit-learn, scipy, numpy, pandas, and matplotlib. We recommend installing all of these using the Anaconda Python distribution, since it comes with all the libraries we'll need in this part of the course. If you have some other existing Python installation, you can install the libraries we'll be using from the command line using pip, like this. The most important library we'll be using for machine learning is called scikit-learn. Scikit-learn is the most widely used Python library for machine learning, and it will be the basis for this course. It's an open source project that's under continual development and improvement, and supports a very wide array of important machine learning algorithms. It has excellent online documentation and a very active user community. Because of this broad adoption, scikit-learn has many sample applications, tutorials, and code examples that are available online. So one valuable reference that we recommend you use while you take this course is the scikit-learn user guide and the API documentation, which contains further details on the different algorithms that are in the library, along with details on the various options that these algorithms support. Scikit-learn makes use of two other Python scientific computing libraries called scipy and numpy. Scipy is a Python library that supports data manipulation and analysis methods that are commonly used in scientific computing. So this includes support for statistical distributions, optimization of functions, linear algebra, and a variety of specialized mathematical functions. In some parts of this course, we'll make use of scipy's ability to provide what are called sparse matrices, which are a way to store large tables that contain mostly zeros. So more on that later. NumPy is a Python library for scientific computing that contains support for some fundamental data structures used by scikit-learn, such as multidimensional arrays. Typically, data that's input to scikit-learn will be in the form of a NumPy array. Pandas is a Python library for data manipulation and analysis. And if you took course 1 in this series, you've already had experience with what pandas can do. The key data structure pandas supports that we'll be using is called a data frame, which is basically like a spreadsheet table with rows and named columns. So unlike the arrays supported by NumPy, the columns in a data frame can be of all different types. You can have one column holding string values, another column holding a date, another column holding a floating point number, and so on. Pandas also has great support for reading and writing data in a variety of formats, everything from comma-separated CSV files to SQL, the structured query language used by databases, and more. Matplotlib is a widely used Python 2D plotting library that produces high-quality figures in a variety of formats and interactive environments across platforms. Matplotlib can be used in Python scripts, the Python and IPython shell, web application servers, and a variety of different graphical user interface toolkits. If you've taken course 2 in this data science series, you'll already have some experience with using Matplotlib. Here we'll primarily be using matplotlib.pyplot for data analysis, since it can create histograms, bar charts, error charts, scatter plots, and so forth with just a few lines of code. So for reference, this course will be using the following versions of these libraries, as shown on the slide. It's okay if your versions don't match our versions exactly, as long as the version of scikit-learn you're using is the same or later than the one we've shown here. For our first machine learning exploration, we're going to build an extremely simple form of object recognition system. Now, although the example we'll use is very simple, it does reflect many of the same key machine learning concepts that go into building real-world commercial systems. The data set we're going to use is a small, very simple example data set derived from one originally created by Dr. Ian Murray at the University of Edinburgh for the task of training a classifier to distinguish between different types of fruit. So to create the original data set, Dr. Murray went to a nearby store, bought a few dozen oranges, lemons, and apples of different varieties, and recorded their measurements in a table. So he sat down and he looked at the height and the width, estimated their mass, and so forth. So we've reformatted his original data slightly and added one or two extra simulated features, such as a color score, for instructional purposes. This data set is called Fruit Data with Colors.txt, and it's included in the folder of materials that you downloaded for this course. Now, you might think that fruit prediction is a sort of silly and impractical scenario, and given the limited nature of this data set, it is a bit of a toy example, but actually, food companies do indeed now rely on machine learning systems that aren't all that different in concept from the ones we're about to build. So they can do automated quality control. And in fact, there do exist, for example, real systems used by fruit shipping companies that screen for rotten oranges during processing. Now, the features that they use in building these systems are a little more sophisticated than the ones we'll look at here. So, for example, quality control systems for rotten orange detection use ultraviolet light that can detect interior decay, which is often less visible than just by looking on the surface. Anyway, to solve machine learning problems, you can think of the input data as a table where each object, so in our case a piece of fruit, is represented by a row, and the attributes of the object, the measurement, the color, the size, and so forth in our case for a piece of fruit, the features of the fruit are represented by the values that you see across the columns. In a supervised learning problem, the data set will also typically contain a special column with the label of the object if the data set does not have such a field already. Sometimes you can derive it from information that's in one or more columns. So to make sure you're ready to continue, make sure you've run the following code snippet that loads the proper libraries we're going to need to proceed. And we'll show those here now. So the first thing we're going to do is to load the fruit dataset file using the very handy read table command in pandas. Now this will read the dataset from disk and store it into a data frame variable that we'll call fruits here. Okay, let's look at this dataset and dump out the first few rows of the data frame. So here we can see that each row of the data set represents one piece of fruit as represented by several features that are in the table's columns. So in order, the columns that we see are fruit label. So this is the training label that we'll use. It's a number that corresponds to the general type of fruit. So for example, 1 is an apple, 2 is a mandarin orange, 3 is a regular orange, and so forth. So this label was supplied by the human creator of the data set. The fruit name and fruit subtype columns contain text descriptions of the general and specific fruit categories. And the fruit name corresponds, it's a text form of the corresponding fruit label in the same row. Now, we won't be using these name columns as features. I've just included them here to make the data set a bit more readable for our purposes. After that, the features in this representation include measurements for each fruit that capture its mass in grams and its width and height in centimeters. And finally, there's a feature stored in a column called color score that's meant to be a single number that captures a rough idea of the color of the fruit. So in a real system, this would actually be something more sophisticated, like a histogram of the distribution of colors, or maybe the pixels from an actual image or video of the fruit. But for our purposes, we're going to just summarize the color along a spectrum scale. That'll be a handy summary that we can use that will just be easy to visualize. So scores close to 1 mean the fruit is red. Scores around 0.7 indicate yellow, and so forth. So looking at this data frame, we can see that it contains 59 rows corresponding to 59 different pieces of fruit that have been measured and entered into the table. So our goal here is to build a classifier from this data that can predict the correct type of fruit for any given observation of features, such as mass, height, width, and color score. So for example, can we tell, based on the color score and the dimensions, the difference between an orange and a lemon, and have the classifier predict the type of piece of fruit correctly, just from its observed measurements. Now, assuming for the moment that we already had a classifier ready to go, how would we know if its predictions were likely to be accurate? Well, we could choose a fruit sample called a test sample for which we already had a label. So we could feed the features of that piece of fruit into the classifier and then compare the label that the classifier predicts with the actual true label of the fruit type. So here's a very important point, though. If we use one of our labeled fruit examples in the data that we use to train the classifier, we can't also use that same fruit sample later as a test sample to also evaluate the classifier. Why is that? Well, a key ability that our classifier needs to have is that it needs to work well on any input sample, any new pieces of fruit that we might see in the future, not just on the ones that we have in our training set. Because our classifier could simply memorize every sample in the training set, it'd be pretty trivial to just give back the correct label for any one of the same samples later, right? So measuring the classifier's performance later using the same samples that we've used to train it in the first place doesn't tell us anything about how well the classifier is likely to work for fruit that we haven't seen before. It will only tell us what we already know about what's in the training set. So since our only source of labeled data is the data set we've been given, to estimate how well the classifier will do on future samples, what we'll do is split the original data set into two parts. We'll have an array of labeled samples called the training set that will be used to train the classifier, and then we'll hold out the remaining labeled samples and put them into a second separate array called the test set that will be used to then evaluate the trained classifier. So to create training and test sets from an input data set, scikit-learn provides a handy function that will do this split for us, called, not surprisingly, train test split. And here's an example of how we'll use it. This function randomly shuffles the data set and splits off a certain percentage of the input samples for use as a training set, and then puts the remaining samples into a different variable for use as a test set. So in this example, we're using a 75-25% split of training versus test data. And that's a pretty standard relative split that's used. It's a good rule of thumb to use in deciding what proportion of training versus test might be helpful. As a reminder, when we're using scikit-learn, we'll denote the data that we have using different flavors of the variable x, capital X, which is typically a two-dimensional array or data frame. And the notation we'll use for the labels will be typically based on lowercase y, which is usually a one-dimensional array or a scalar. Now, note the use of the random state parameter in the train test split function. So this random state parameter provides a seed value to the function's internal random number generator. If we choose different values for that seed value, that will result in different randomized splits for training and test. So if we want to get the same training and test split each time, we just make sure to pass in the same value of the random state parameter. And so here we're going to set that parameter to 0 for all our examples. The training test split function will put the training set here into xtrain, the test set into xtest, the training labels into ytrain, and the test labels into ytest. So this is a 75-25 partitioning of the original data into these two parts. And this is the variable naming convention we'll use for pretty much all of our coding. We'll put the rows of the data without the label, the training instances, into this capital X variable, and the list of corresponding labels for those rows into a variable called lowercase y. When using the training set and a test set, we'll then use xtrain that holds the training instances to train the classifier, and xtest to evaluate the classifier after it's been trained. And we're going to show a short snippet of code here now that illustrates how to do that. So here we can see the results of the function, applying this train test split function. You can see that it has indeed split our fruit data set into training and test sets with the correct proportion of samples. Now that we have a training and a test set, we're ready for the next step. And we'll look now into more depth at the data itself before we proceed with giving it to a machine learning algorithm. In general, if you're thinking about applying machine learning to a data set, it's a really good first step to actually look at the data set first, maybe using some simple visualization methods, or even simply scrolling through to look at the various values in the different rows before proceeding. And there are several reasons for doing this. First, it's helpful to simply get a sense for what's actually in the data set, because it may be that in inspecting the features of each object, you might get a better idea of what type of cleaning or preprocessing still needs to be done to the data, and of the range of values or the distribution of values that is typical for each attribute or each feature. This initial exploration can be especially valuable when you're dealing with complex objects like text that may be represented by many features that are extracted using a series of several preprocessing steps. For example, you might discover that the data set you got has a single column with a person's name that still needs to be split into two separate first and last name columns. As for example, if you're using the name as one of the prediction features, that might be important. Second, you might notice missing or noisy data, or maybe some specific inconsistencies, such as the wrong data type being used for a column, incorrect or inconsistent units of measurement for a particular column, a particular feature. Or maybe you'll notice that there aren't enough examples of a particular labeled class. You might notice, for example, that some measurements of a person's weight, if you're, let's say you're doing a health application with a patient record for each row, if some might accidentally have the weight in grams instead of kilograms and so forth. And that can make obviously a huge difference in how accurate your results are. So inspecting and visualizing the data will help you detect and understand these potential sources of noise or errors. And finally, it might turn out that for your data set, your problem is actually solvable without machine learning. Now, this doesn't happen all that often, but if it does, you can save yourself considerable time by simply looking at what data exists in your data set. So in one scenario, your data set might actually contain a feature that is clearly a strong indicator of the label that you want to predict. For example, if your goal was to predict whether a house's location was in New York City versus San Francisco based on attributes like its sales price, its elevation above sea level, its how big its rooms are, and so forth. It could be that your data set might also include, let's say, a URL to a photo of the house, and that image might, contain GPS coordinates to the house within its metadata, or maybe the URL encodes location in a slightly non-obvious but human recognizable way that you can pick out, and you've solved your problem just by looking at the data. So as I said, this scenario isn't all that common, but it does happen, and so a brief check of your data set could save you a lot of unnecessary work. Okay, so we'll make sure we've got a training set from our original data set unit using train test split. And we'll do all our initial visualization and feature analysis on this training set. And we're only going to use the test set for actually evaluating the classifier once it's trained. This complete separation of training and test sets is very important, and we'll go into more depth later about some specific reasons why it's important in later class. So now that we have a training set selected, let's create some simple visualizations to look at how the features of the objects in the training set, in our case, different fruits, relate to each other and to the labels. So with these visualizations, we get at least two major benefits. First, we can get an idea of the range of values that each feature takes on, and we can immediately see any unusual outliers that are very different from other points, and that might indicate noise or a missing feature or other problem with the data set. And second, we may be able to get a better idea of how likely it is that a machine learning algorithm could do well at predicting the different classes by seeing how well clustered and well separated the different types of objects are in feature space. So feature space refers to the representation of an object using specific features that are in certain columns of the data that we have. So for example, if the features for objects with the same label, for example, all the lemons, have similar feature values, we should see a well-defined cluster appear in the visualization. While if the features for objects that have different labels tend to be quite different, we should see these well separated into visibly different areas of the plot. So having objects whose classes are well defined and well separated in feature space is a good indication that suggests the classifier is likely to be able to predict the class label from the features with good accuracy. Now, the visualization techniques that I'll be showing here work well when you have a relatively small number of features, let's say less than 20. Later, when we cover unsupervised learning, you'll learn how to create visualizations of data sets that use a very large number of feature dimensions, so hundreds or even thousands or millions, to represent each object. But for now, the first visualization tool we'll use is called a feature pair plot, and that's shown here. So this plot shows all possible pairs of features and produces a scatter plot for each pair, showing how the features are correlated with each other or not. Each point in the scatter plot represents a piece of fruit, colored according to the class it belongs to, and positioned using the pair of features assigned to that scatter plot. Along the diagonal is a histogram showing the distribution of feature values for that feature. So in this pair plot, the dimensions shown here in order are the height, width, mass, and color score of the fruit examples in our training set. So the upper left corner of the histogram here shows the distribution of the height feature for all samples in the training set. And the scatter plot to its immediate right plots the width of each sample on the x-axis and the height of the sample on the y-axis. Now, just by looking at this pair plot, we can already see that some pairs of features, like the height and color score in the top right corner here, are good for separating out different classes of fruit. And this suggests that a classifier that was trained using those features could likely learn to classify the various fruit types reasonably well. Here's the code that we'll use to create this plot, and let's run this now on our training set. Note that a pair plot like this does not show interactions between all features that might exist, just between pairs of them. So the plot itself may not show all the interesting relationships that do exist between the features. But it does give you a rough idea of of some of the interactions that might exist. We can also look at feature spaces that use a subset of 3 features by creating a 3-dimensional plot. And here's the code that we can use to do this. So in this example, we plot different fruits using 3 coordinates. So here we'll show the width, the height, and the color score. Here again, each point represents a single piece of fruit, and it's colored according to its fruit label value. So in this 3D plot, you can actually rotate the plot along the various axes by holding down the mouse button and then dragging. And you can clearly see that the different fruit types are in pretty well-defined clusters that are also well separated in feature space. So now that we've taken a look at the data, next we'll look at a simple prediction task for this data set in a bit more detail. Now that we've gotten a sense for what's in our data set, as a simple example to get started, we're going to use this data set to train a classifier that will automatically identify any future pieces of fruit that might come our way, based on the features available to the classifier, such as the object's color, size, and mass. To do this, we'll use a popular and easy-to-understand type of machine learning algorithm known as k-nearest neighbors, or KNN. The k-nearest neighbors algorithm can be used for classification and regression, though here we'll focus for the time being on using it for classification. KNN classifiers are an example of what's called instance-based or memory-based supervised learning. What this means is that instance-based learning methods work by memorizing the labeled examples they see in the training set, and then they use those memorized examples to classify new objects later. The K in KNN refers to the number of nearest neighbors the classifier will retrieve and use in order to make its prediction. In particular, the KNN algorithm has 3 steps that can be specified. First of all, when given a new, previously unseen instance of something to classify, a KNN classifier will look into its set of memorized training examples to find the K examples that have the closest features. And we'll talk about what closest means in a minute. Second, the classifier will look up the class labels for those k-nearest neighbor examples. And then once it's done that, it will combine the labels of those examples to make a prediction for the label of the new object, typically, for example, by using simple majority vote. Let's look at a visual example of a KNN classifier that's based on our fruit data set. So what I've done here is taken our training set and plotted each piece of fruit using 2 of its features, the width and the height. These 2 features together form what is called the feature space of the classifier. And I've shown each data point's label using the colors shown in the legend. So as you can see, there are 4 different colors here that correspond to the 4 types of fruit that are in our data set. These broad areas of color show how any point given width and height could be classified according to a 1 nearest neighbor rule. So in other words, I've set k equal to 1 here. So for example, a data point over here that had a height of 6 centimeters and a width of 9 centimeters would be classified as an apple because it falls within this red area here that the KNN classifier has decided map to objects that are apples based on the dimensions. Or for example, if the classifier saw a piece of fruit that had a height of 4 centimeters and a width of 7 centimeters, it would be classified as a mandarin orange because it falls within this decision area that's assigned to mandarin oranges. So what does it mean to have a 1 nearest neighbor rule? Where did it come up with these different class assignments in the first place? Well, let's take a look at the apple example over here. The object that has a height of 6 centimeters and a width of 9 centimeters, if you give the classifier that point, what it will do is search within all the different training examples that it's seen. So it will look at all these points and see which one is closest. So we're looking at the nearest single neighbor. So we're looking at k equals 1. We're trying to find the one point that's closest to our what's called the query point. This is the point we want to classify. So in this case, we can see probably that this point over here is the nearest neighbor of the query point in feature space. Similarly, if we look at the Mandarin example over here, the closest training set object to the query point is one of these, probably maybe this point right here. Okay, so that's the nearest neighbor of that query point. So for any query point in the feature space, let's say we're over here in the lemon zone. The nearest neighbor to this query point would be this training set point right here. And because the training set points are labeled, we have the labels for those. In the one nearest neighbor case, the classifier will simply assign to the query point the class of the nearest neighbor object. So because the nearest neighbor here is an apple, the query point here will get classified as an apple. And if we look at the Mandarin orange point over here, the nearest data point is the Mandarin orange, so it will get classified in that region. And if we do that for every possible query point, we get this pattern of class regions. The zones where we transition from one class to another, this line right here is called the decision boundary, because query points that are on one side of the line get mapped to one class, and points that are on the other side of the line get mapped to a different class. So because this is a k nearest neighbor classifier, and we're looking at the case where k equals 1, we can see that the class, the boundaries here, the decision boundaries, let's take an example over here. We have a point over here that's an orange, another point that's a lemon here, and we can see the decision boundary, because it's based on Euclidean distance and we're weighting points equally, that the decision boundary goes exactly at a distance equidistant to these two things. It's exactly halfway between these 2 points, right? Because if it were any closer to this point, it would be mapped to the orange class, and if it were any closer to the lemon instance over here, it will be mapped to the lemon class. So you can see this pattern for all the decision boundaries here. This line is equidistant to these 2 nearest points. So this is basically how the k nearest neighbor classifies new instances. So you can imagine with points, query points where k is larger than 1, we might use a slightly more complicated decision rule. Let's take this example over here. Suppose we have a query point that's an orange, and we're doing 2 nearest neighbor classification. So in that case, the 2 nearest points are these 2 points here. And in cases where k is bigger than 1, we use a simple majority vote. We take the class that's most predominant in the labels of the neighbor examples. So in this case, the labels happen to agree. They're both oranges, and so this point in a 2 nearest neighbor situation would be classified as an orange. When you get points that are closer to, say, a point over here, the 2 nearest neighbors in that case might be these points here, in which case you could choose randomly between them to break the tie. Typically, the value of k is odd, so that we can simply, in k equals 3, it might look like this. And so you can see that the 3 nearest neighbors here are a red point, an apple, a blue point, an orange, and another red point, an apple. So in the k equals 3 case, the vote would go towards labeling this as an apple. And that's basically all there is to the basic mechanism for KNN classifiers. More generally, to use the nearest neighbor algorithm, we specify 4 things. First, we need to define what distance means in our feature space, so we know how to properly select the nearby neighbors. In the example that I just showed you with the fruit data set, we use the simple straight line or Euclidean distance to measure the distance between points. Second, we must tell the algorithm how many of these nearest neighbors to use in making a prediction. This must be a number that is at least 1. Third, we may want to give some neighbors more influence on the outcome. For example, we may decide that neighbors that are closer to the new instance that we're trying to classify should have more influence or more votes on the final label. Finally, once we have the labels of the k nearby points, we must specify how to combine them to produce a final prediction. Here's a specific example of some typical choices we might make for these 4 things. The most common distance metric, and the one that scikit-learn uses by default, is the Euclidean or straight line distance. So technically, if you're interested, the Euclidean metric is actually a special case of a more general metric called the Minkowski metric, where there's a parameter p that's set to 2 that will give you the Euclidean metric. And you'll see this in the notebook when you look at the actual settings. They're done in terms of the Minkowski metric. We might choose to use the 5 nearest neighbors, let's say, for our choice of k. And we might specify that there's no special treatment for neighbors that are closer. So we have a uniform weighting. Also, by default, scikit-learn will apply for the 4th criterion a simple majority vote, and it'll predict the class with the most representatives among the nearest neighbors. We'll look at a number of alternative classifiers in next week's class on supervised learning methods. For now, let's take a look at the notebook to see how we apply a k nearest neighbor classifier in Python to our example fruit dataset. As a reminder, you can use Shift-Tab to show the documentation pop-up for the method as you're entering it to help remind you of the different parameter options and syntax. So recall that our task was to correctly classify new incoming objects, in our example case, pieces of fruit. So our newly trained classifier will take a data instance as input and give us a predicted label as output. The first step in Python that we need to take is to load the necessary modules, as well as load the dataset into a pandas data frame. After we've done that, we can dump out the first few rows using the head method to check the column names and get some examples of the first few instances. Now, what I'm doing next here in the notebook is defining a dictionary that takes a numeric fruit label as the input key and returns a value that's a string with the name of the fruit. And this dictionary just makes it easier to convert the output of a classifier prediction to something a person can more easily interpret, the name of the fruit in this case. So for this example, we'll define a variable capital X that holds the features of our data set without the label. And here I'm going to use the mass, width, and height of the fruit as features. So this collection of features is called the feature space. We define a second variable, lowercase y, to hold the corresponding labels for the instances in X. Now we can pass X and Y to the train test split function in scikit-learn. Normally the splitting into training and test sets is done randomly, but for this lecture I want to make sure we all get the same result, so I set the random state parameter to a specific value. In this case I happen to choose 0. The results of the train test split function are put into the 4 variables you see on the left. And these are marked as xtrain, xtest, ytrain, and ytest. We're going to be using this x and y variable naming convention throughout the course to refer to data and labels. Once we have our train test split, we then need to create an instance of the classifier object, in this case a KNN classifier. And then set the important parameter, in this case the number of neighbors, to a specific value to be used by the classifier. We then train the classifier by passing in the training set data in xtrain and the labels in ytrain to the classifier's fit method. Now the KNN classifier that I'm using in this case is an example of a more general class called an estimator in scikit-learn. So all estimators have a fit method that takes the training data and then changes the state of the classifier or estimator object to essentially enable prediction once the training is finished. In other words, it updates the state of the k&n variable here, which means that in the case of k nearest neighbors, it will memorize the training set examples in some kind of internal storage for future use. And that's really all there is to training the k&n classifier. And the first thing we can do with this newly trained classifier is to see how accurate it's likely to be on some new, previously unseen instances. To do this, we can apply the classifier to all the instances in the test set that we've put aside, since these test instances were not explicitly included in the classifier's training. One simple way to assess if the classifier is likely to be good at predicting the label of future previously unseen data instances is to compute the classifier's accuracy on the test set data items. Remember that the k&n classifier did not see any of the fruits in the test set during the training phase. So to do this, we use the score method for the classifier object. So this will take the test set points as input and compute the accuracy. And now the accuracy is defined as the fraction of test set items whose true label was correctly predicted by the classifier. We can also use our new classifier to classify individual instances of fruit. In fact, this was our goal in the first place, was to be able to take individual instances of objects and assign them a label. So here, for example, I'll enter the mass, width, and height for a hypothetical piece of fruit that is fairly small. And if we ask the classifier to predict the label using the predict method, we can see the output is that it predicts it's a mandarin orange. I can then pass a different example, which is maybe a larger, slightly elongated fruit that has a height that's greater than the width and a larger mass. In this case, using the predict method on this instance results in a label that says the classifier thinks this object is a lemon. Now let's use a utility function called plot fruit k&n that's included in the shared utilities module that comes with this course. This will produce the colored plots I showed you earlier that have the decision boundaries. You can then try out different values of k for yourself to see what the effect is on the decision boundaries. The uniform parameter that I pass in here as the last parameter is the weighting method to be used. So here I'm passing in the string uniform, which means to treat all neighbors equally when combining their labels. If you like, you can try changing this to the word distance if you want to try a distance-weighted method. You can also pass your own function, but we'll leave that for later. We can also see how our new classifier behaves for different values of k. So in this series of plots, we can see the different decision boundaries that are produced as k is varied from 1 to 5 to 10. We can see that when k has a small value like 1, the classifier is good at learning the classes for individual points in the training set, but with a decision boundary that's fragmented with considerable variation. This is because when k equals 1, the prediction is sensitive to noise, outliers, mislabeled data, and other sources of variation in individual data points. For larger values of k, the areas assigned to different classes are smoother and not as fragmented, and more robust to noise in the individual points, but possibly with some mistakes, more mistakes in individual points. This is an example of what's known as a bias-variance trade-off, and we'll look at that phenomenon and its implications in more depth in next week's class. Given the changes in the classifier's decision boundaries we observe when we change k, a natural question might be how the value of k, how the choice of k, affects the accuracy of the classifier. We can plot the accuracy as a function of k very easily using this short snippet of code. We see that, indeed, larger values of k do lead to worse accuracy for this particular data set and fixed single train test split. Keep in mind, though, these results are only for this particular training test split. To get a more reliable estimate of likely future accuracy for a particular value of k, we would want to look at results over multiple possible train test splits. We'll go into this issue of model selection next week as well. In general, the best choice of the value of k, that is, the one that leads to the highest accuracy, can vary greatly depending on the data set. In general, with k nearest neighbors, using a larger k suppresses the effects of noisy individual labels, but results in classification boundaries that are less detailed. So we've taken several steps in this course so far. We've looked at a data set, plotted some features. We then took the features and learned how to compute a train test split, use that to train a classifier, and use the resulting classifier to make some predictions for new objects. So congratulations, you've just created and run your first machine learning application in Python. In next week's class, we'll go into some supervised learning methods in more depth and look beyond k nearest neighbors to learn how and why to apply other types of classifiers to machine learning problems. In the previous module, you saw a basic example of supervised machine learning using a k nearest neighbors classifier, classifying different types of fruit based on their various physical properties. Machine learning algorithms of this type are called supervised learning algorithms because they use labeled examples in a training set to learn how to predict the labels for new, previously unseen examples. The supervised aspect refers to the need for each training example to have a label in order for the algorithm to learn how to make accurate predictions on future examples. This is in contrast to unsupervised machine learning, where we don't have labels for the training data examples, and we'll cover unsupervised learning in a later part of this course. This week we'll explore supervised learning in a bit more depth, going beyond k nearest neighbors classifiers to several other widely used supervised learning algorithms. Because this is an applied machine learning course, we're not going to cover too much of the mathematical derivation or the detailed inner workings of these algorithms. For that, you can check out a number of more technical machine learning courses, such as Andrew Ng's excellent course on machine learning on Coursera. Instead, we'll focus on some higher-level goals: how to apply a number of specific supervised machine learning algorithms, and how to interpret their results for important tasks. This will include understanding how supervised learning algorithms estimate their parameters from data, how the trained model makes predictions for new instances, the strengths, weaknesses, and best scenarios to apply a particular method, and how to use the method with its parameter settings in Python programs using scikit-learn. Across all of these algorithms, we'll discuss some general principles that are critical to machine learning, like the issue of overfitting, and how overfitting relates to a model's complexity, and which parameters typically can be used to control model complexity in order to obtain good performance on previously unseen data. In this module, we won't have time to cover all the different parameters available for the various supervised learning methods, so we'll focus on a small number of the most important parameters. The full details of all the supervised algorithms we'll cover this week are in the excellent online documentation that's provided with scikit-learn, which we've included links to in the supplemental material for this course. Before we continue, let's review some basic terms. So on the right here, I'm showing a dump of the first few rows of the fruit data set that you worked with last week. The first term that we'll be using a lot is feature representation. And as you might recall, what that means is taking an object like a piece of fruit and converting it into numbers that the computer can understand. So in this data set, the feature representation for a piece of fruit consists of these columns: the mass, width, height, and color score. These are the things that will be used as the features in the various machine learning algorithms that we'll be applying to try to predict the label of a piece of fruit. So typically each column in the data set here corresponds to a different feature that's associated with each instance. So I use the term instance or sample or example somewhat interchangeably. Most of the time I'll be talking about instances or samples. So each row of this data set corresponds to one piece of fruit or one specific data instance or sample. When we work with these instances in Python, the convention we'll be using is that we'll put all the variables that represent the features in this variable capital X here. So capital X refers to all the feature columns that will be going into as the inputs for the predictor. And then we have the very important concept of a label. So each instance here, each piece of fruit has a label that's what was assigned by a human in this case. And the label is an example of a target value. So in classification, the target value is the label of an object, and in regression, it's the particular continuous value you might want to predict from the inputs. And we use lowercase y in Python for the variable name to hold the target values associated with each instance. So if you look at the data set as being, say, this big block here, typically there'll be a column of labels and then a matrix of multiple columns holding the features that we'll be using. And then we have a couple of columns in here, the fruit name and the fruit subtype, that are used only for labeling purposes to make things like plots more readable for humans. The things that go into the actual machine learning algorithms are the label for training through the y variable and the features, the mass, width, height, and color score that are in the x variable. Another concept that we saw from our first example were the concepts of training and test sets. So by that we mean, just to recap, if we think of the entire data set here as a rectangle, so this could be the fruit data set we just showed previously, we typically we take a chunk of the original data set and make that the training set, and then we reserve typically a smaller portion as the test set. So the default split in scikit-learn is typically 75-25. The function train test split here is a very handy function in scikit-learn that takes the original set of features x and the labels y and does this partitioning into a training and test set. So the variables that we'll be using to denote training and test set are x train for the training set features and y train for the training set labels, and then x test for the test set features and y test for the test set labels. Once we pass the training data into a classifier, so as you recall, we can create here a k-nearest neighbors classifier by invoking this constructor and passing it the number of neighbors that we want the algorithm to use. The training set is used to estimate the parameters for a model. In scikit-learn, there's an object called an estimator, which is either a classifier or a regressor, for example. And the goal of this estimator, this model, is to learn how to classify or predict target values for new data instances. So the procedure where we pass in a training set to learn those parameters that are internal to the estimator is called model fitting. And the result of model fitting is a trained model. So an example of that in the code here is when after we create the knn variable that has the k nearest neighbors classifier object, we use the fit method on the training data and the training labels to update the internal state of the knn object, and that's the training process. So after that line of code is finished running, the internal state of the KNN classifier has been updated to reflect the training data's influence on the internal parameters of the KNN classifier, and now it's ready to be used. So evaluation methods are typically the next step, where after we've fit the model, we want to see how well it actually does do on the test data. So in week 4 of the course, we're going to cover in detail different ways of evaluating classifiers and regressions. But for now, we'll look at accuracy. So the score method applied to the classifier will take the test data in X test and Y test and output the accuracy of this particular classifier on the test set. And then finally, we can also apply the predict method to the KNN object to get the label for previously unseen instances. So these are the terms that we'll be using throughout the course. And we'll also be maintaining a fairly consistent use of these variable names throughout all the Python code that we use. Supervised learning can be divided into 2 different types of tasks: classification and regression. Both classification and regression take a set of training instances and learn a mapping to a target value. For classification, the target value is a discrete class value. For example, a binary classification problem has 2 types of target values: 0 representing the negative class, or 1 representing the positive class. An example of binary classification might be trying to detect a fraudulent credit card transaction. The transaction's either valid or invalid. A second type of classification problem is known as multi-class classification, where the target value is more than just a yes or a no, or 1 or 0. It could be one of a set of discrete values. For example, the labeling fruit example that we saw from the first part of the course is an example of multi-class classification, because the object that we're trying to predict the label for can only have one of the possible label types. Something couldn't be, for example, both an apple and an orange. A third category of classification is called multi-label classification, where there are multiple target values. For example, we might want to take a web page and label all the different topics discussed on that page, as shown in this example. Here we see a page from Microsoft Research where the multi-label classification has decided that the labels computing, science, and so forth are applicable. In contrast to classification, for regression, the target we're trying to predict is a continuous value. For example, a model that predicts the market price of a house, given how many rooms it has, where it's located, the size of the land that it sits on, and so forth, would be a regression problem, because the market price is a continuous, otherwise known as a real valued variable. You can tell what type of supervised learning method you should apply to a given problem by thinking about the meaning of the target value. Does the target value represent something that's one of a set of mutually exclusive class values, as in the case of assigning a label to a piece of fruit, or whether or not a transaction is fraudulent? If so, it's a classification problem. On the other hand, if the target is a real valued quantity, like cost or income or height, then it can be treated as a regression problem. Finally, we'll see that many supervised learning methods come in both flavors of classification and regression. For example, support vector classifiers, which we'll cover shortly, also has a regression version called, not surprisingly, support vector regression. In this course, we'll cover both classification and regression methods, although we'll spend the majority of our time on classification, since that represents a big set of important machine learning tasks. And because classification involves some additional concepts and methods, especially in areas like evaluation, that aren't needed as much for regression. To start with, we'll look at 2 simple but powerful prediction algorithms: k-nearest neighbors, which we saw in week 1, and linear model fitting using least squares. These 2 prediction methods represent 2 complementary approaches to supervised learning. K-nearest neighbors doesn't make a lot of assumptions about the structure of the data and gives potentially accurate but sometimes unstable predictions. And by unstable, I mean that it can be sensitive to small changes in the training data. On the other hand, linear models make strong assumptions about the structure of the data. In other words, that the target value can be predicted just using a weighted sum of the input variables, a linear function. It can give stable but potentially inaccurate predictions. In addition to k-nearest neighbors and linear models, we'll cover a variety of widely used supervised learning methods for classification and regression, including decision trees, kernelized support vector machines, and neural networks. For each method, we'll explore how it works at a high level without going into too much mathematical detail. We'll also look at what kind of feature preprocessing is typically needed, and for almost all of the supervised learning algorithms we'll look at, there are one or more parameters that control its model complexity, so we'll see how to set these parameters to help avoid under and overfitting. Finally, we'll discuss the positives and negatives of each supervised learning approach to help understand what are the best scenarios in which to apply or not apply that particular method. One consistent pattern you'll see as we look at all these different methods is the relationship between model complexity and model accuracy, as shown in this plot. The relationship is different depending on whether the classifier performance is measured on the training set, what is labeled here as training set score, or on the test set, labeled here as test set score. When measuring performance against the training set, the same one that was used to train the classifier, this plot shows that as a model's complexity increases, so think of the KNN classifier with K decreasing, and with more and more highly variable and detailed decision boundaries, the model's accuracy on the training set trends upward as the more complex models fit the training data better and better. However, when the same trained model is evaluated on the held-out test set, there's typically an initial accuracy gain from the increasing model complexity up to some optimal point, but then a decrease in test set accuracy as the increasingly complex models begin to overfit too specifically to the training data and don't capture more global patterns that help it generalize well to unseen test data. Now, the specifics of these trends will vary from situation to situation, but overall, we'll see this pattern across the supervised learning methods that we'll examine. You'll be hearing a lot about models in this course. What is a model? Well, it's a specific mathematical or computational description that expresses the relationship between a set of input variables and one or more outcome variables that are being studied or predicted. In statistical terms, the input variables are called independent variables, and the outcome variables are termed dependent variables. In machine learning, we use the term features to refer to the input or independent variables, and target value or target label to refer to the output dependent variable. Models can be either used to understand and explore the structure within a given data set, as we'll see in unsupervised learning, or in the case of supervised learning methods, our goal is to develop predictive models that can accurately predict the outcome, in other words, the target value or label, for previously unseen input data. When we build a supervised learning model, whether it's for classification or regression, it's not only important for the model to make correct predictions on the examples it saw in the training data. If that were the only definition of success, then supervised learning algorithms could simply memorize all of the training data and always have 100% accuracy. Of course, that's not what happens in the real world. What we actually want from a supervised machine learning algorithm is the ability to predict the class or target value correctly on a test set of future examples that haven't been seen before. This ability to perform well on a held-out test set is the algorithm's ability to generalize. How do we know that our trained supervised model will generalize well? In other words, perform well on an unseen test set. Well, typically, machine learning makes an important assumption that the future test set has the same properties, or more technically, is drawn from the same underlying distribution as the training set. This means that if we observe our model has good accuracy on the training set, and the training set and test sets are similar, we can also expect that it will do well on the test set. Unfortunately, sometimes this doesn't happen due to an important problem known as overfitting. Informally, overfitting typically occurs when we try to fit a complex model with an inadequate amount of training data. An overfitted model uses its ability to capture complex patterns by being great at predicting lots and lots of specific data samples or areas of local variation in the training set, but it often misses seeing global patterns in the training set that would help it generalize well on the unseen test set. It can't see these more global patterns because, intuitively, there's not enough data to constrain the model to respect these global trends. As a result, the training set accuracy is a hopelessly optimistic indicator for the likely test set accuracy if the model is overfitting. Understanding, detecting, and avoiding overfitting is perhaps the most important aspect of applying supervised machine learning algorithms that you should master. There are serious real-world consequences to overfitting. The reading for this week contains one example from the medical world you might find interesting. To understand the phenomenon of overfitting better, let's look at a few visual examples. The first example that we'll look at for overfitting involves regression. In this chart, on the x-axis, we have a single input variable that might be, for example, the size of a piece of property, and we have a target variable on the y-axis. For example, this might be the market selling price of a house that sits on that piece of property. So in regression, we're looking to find the relationship between the input variable and the target variable. And we start off with the idea of a model that we want to fit that might explain this relationship. So one example of a model that we could try to fit would be a linear model. So trying to predict that there's a linear relationship between the input variable and the target variable. So the regression model might fit a straight line to these points. In this case, the model has underfit the data. The model is too simple for the actual trends that are present in the data. It doesn't even do well on the training points. So these blue points would represent the training points, the input to the training process for the regression. And when we underfit, we have a model that's too simple, doesn't even do well on the training data, and thus is not at all likely to generalize well to test data. On the other hand, if we pick a better model, for example, the idea that this might be a quadratic relationship, we might actually be able to apply that and get what looks like a much better fit. So this would be an example of a reasonably good model fit. We've captured both the general trend of the points while also ignoring the little variations that might exist due to noise. The third example might be, we might hypothesize that the relationship between the input variable and the target variable is a function of several different parameters. Let's say a polynomial, so something that's very bumpy. If we tried to fit a more complex model to this set of training data, we might end up with something that looks like this. So this more complex model has more parameters, so it's able to capture more subtle behavior, but there's also much higher variance here, as you can see. So it's more focused on capturing the more local variations in the training data rather than trying to find the more global trend that we can see as humans in the data. So this is the example of overfitting. In this case, there's not enough data to really constrain the parameters of the model enough so that it can recognize the global trend. This second example, we'll look at overfitting in classification. So this diagram shows a simple two-dimensional classification problem where each data instance is represented by a point and where there are two features associated with each data instance. This is a binary classification problem, so points are labeled either red over here or blue. And the problem in classification is to find a decision boundary. So as we saw with k-nearest neighbors, we want to take this feature space and find regions that are associated with the different labels. So one type of classifier that we'll look at shortly is called a linear classifier, where we try to find a decision boundary that's essentially a straight line through the space. So just as in regression, we can have underfitting models, good-fitting models, and overfitting models. So an example of an underfitting model would be something that really didn't look much at the data, maybe something like this, that only looked at one feature, for example. So again, this is an overly simplistic model. It doesn't even capture the patterns, the division between the classes in the training data well, and so it would be unlikely to generalize. So this is an underfitting model. A reasonably good model that fits well would be a linear model that finds this general difference between the positive class over here and the negative class over here. So you can see that it's aware of this sort of global pattern of having most of the blue negative points in the upper left and most of the red positive points more toward the lower right. And it's robust enough in the sense that it ignores the fact that there may be occasionally a blue point in the red region or a red point in the blue region. Instead, it's found this sort of more global separation between these two classes. So this is a reasonably well-fitting model. An overfitting model, on the other hand, would typically be a model that has lots of parameters so it can capture complex behavior. And so it would try to find something very clever where it tried to completely separate the red points from the blue points in a way that resulted in a highly variable decision boundary. So this has the advantage that, a questionable advantage, that it does capture the training data classes very well. It predicts the training data classes almost perfectly. But as you can see, if the actual division between the classes is captured by this linear model, the overfit model is going to make lots of mistakes in the regions where it's trying to be too perfect in some sense. So you'll see this typically with overfitting. The overfit model is highly variable. And again, it's trying to capture too many of the local fluctuations and it does not have enough data to see the global trend that would result in better overall generalization performance on new unseen data. This third example shows the effect of modifying the k parameter in the k nearest neighbors classifier that we saw previously. The three plots shown here show the decision boundaries for k equals 10, k equals 5, and k equals 1. And here we're using the fruit data set again with the height of a piece of fruit on the x-axis and the width on the y-axis. So the k equals 10 case, as you recall, k equals 10 means that for each query point that we want to get a prediction for, let's say over here, we have to look at the 10 nearest points to the query point. And we'll take those, we won't go through all 10 here, but let's just say there are several here that are nearby, and we'll average or combine their votes to predict the label for this point. So in the k equals 10 case, we need the votes from 10 different data instances in the training set to make our prediction. And as we reduce k, so in k equals 5, we only need 5 neighbors to make a prediction. So for example, if the query point was here, we'd look at these 4 and then possibly whatever was the closest in this set. Let's say that one or this one. And then finally in the k equals 1 case, that's the most unstable in the sense that for any query point we only look at the single nearest neighbor to that point. And so the effect of reducing k in the k nearest neighbors classifier is to increase the variance of the decision boundaries, because the decision boundary can be affected by outliers. If there's a point far away, it might have it has much greater effect on the decision boundary in the k equals 1 case than it would in the k equals 10 case when the votes of 9 other neighbors are also needed. And so you can see that by adjusting the value of k for the k nearest neighbors classifier, we can control, in some sense, the degree of model fitting that's appropriate for a data set. Now, the actual value of k that works best can only be determined by evaluating on a test set. But the general idea is that as we decrease k for k and n classifiers, we increase the risk of overfitting because, for the reason I mentioned before, where at k equals 1, for example, we're trying to capture very local changes in the decision boundary that may not lead to good generalization behavior for future data. To explore different supervised learning algorithms, we're going to use a combination of small synthetic or artificial data sets as examples, together with some larger real-world data sets. scikit-learn has a variety of methods in the sklearn datasets library to create synthetic datasets. The synthetic dataset we'll use for illustration purposes are typically low-dimensional examples, because they only use a small number of features, typically 1 or 2. This makes them easy to explain and visualize. Many real-world datasets, on the other hand, have a higher dimensional feature space. In other words, they have dozens, hundreds, or even thousands or millions of features. So some of the intuition we gain from looking at low-dimensional examples doesn't always translate to high-dimensional datasets, and we'll discuss that a bit more later. For example, high-dimensional datasets, in some sense, have most of their data in corners with lots of empty space, and that's kind of difficult to visualize. We'll go through some examples later in the course. But the low-dimensional examples are still useful so that we can understand things like how a model's complexity changes with changes in some key parameters. So for basic regression, we'll start with a simple problem that has one informative input variable, one noisy linear output, and 100 data samples. Here's a plot of a data set using a scatter plot with each point represented by one dot. The x-axis shows the feature value, and the y-axis shows the regression target. To create this, we use the makeRegression function in sklearn datasets. Here's the code in the notebook. To illustrate binary classification, we'll include a simple 2-class dataset with 2 informative features. Here's a scatter plot showing each data instance as a dot with the first feature value corresponding to the x-axis and the second feature value corresponding to the y-axis. The color of a point shows which class that data instance is labeled. I'm calling this dataset simple because it has only 2 features, both of which are informative. In this case, these 2 classes are approximately linearly separable, which means that a basic linear classifier placed between them does a pretty good job at discriminating the points in the 2 classes. So turning to the notebook, to create this dataset, we used the makeClassification function in sklearn datasets, creating 100 points that roughly group the data samples into one cluster per class, with here a 10% chance of randomly flipping the correct label of any point, just to make it a little more challenging for the classifier. We'll also look at a more complex binary classification problem that uses 2 features, but where the 2 classes are not really linearly separable, instead forming into various clusters in different parts of the feature space. This dataset was created in 2 steps. First, using the makeBlobs function in sklearn datasets to randomly generate 100 samples in 8 different clusters, and then by changing the cluster label assigned by makeBlobs, which is a number from 1 to 8, to a binary label by converting it using a modulo 2 function, assigning the even index points to class 0 and odd index points to class 1. To illustrate multi-class classification, we'll use our familiar fruits dataset, which, as you may remember, has 4 features and 4 possible target labels. Here on the left, I'm showing the array of scatter plots that we saw in week 1 that shows the relationship between all possible pairs of features and the class labels, with the distribution of values for each feature along the diagonal. To illustrate a real-world regression problem, we'll use a dataset derived from the Communities and Crime dataset in the UCI repository. Our dataset uses a subset of the original features and target values, which were originally created from combining several U.S. government data sources, like the U.S. Census. Each data instance corresponds to a particular geographic area, typically a town or region of a city. Our version of this dataset has 88 features that encode various demographic and socioeconomic properties of each location, with 1,994 location data instances. The target value that we'll try to predict is the per capita violent crime rate. To use this dataset, we use the load crime dataset function that's included with the shared utilities module for this course. Let's revisit the first example of machine learning we encountered in week 1, k-nearest neighbors models. Those are a good starting point to continue our exploration of supervised learning because they're simple to understand and can be used for both classification and regression. Let's recall that for classification, the k-nearest neighbor classifier simply memorizes the entire training set. And then to classify a new instance does 3 steps. First, it finds the k-nearest most similar instances to the new instance in the training set. Then it gets the labels of those training instances. And then it predicts the label of the new instance as a function of the nearby training labels, typically by a simple majority vote. Here's how a k-nearest neighbor classifier using only one nearest neighbor, that is with k equal to 1, makes its predictions for the simple binary synthetic dataset. So as you might recall from week 1, where we applied a nearest neighbors classifier to our multi-class fruit dataset, here we're applying the nearest neighbors classifier to our simple binary classification problem, where the points in class 0 are labeled with yellow dots, and the points in class 1 are labeled with black dots. And just as we did for the week 1 problem with fruit classification, here we're also showing how the entire feature space is broken up into different decision regions according to the predictions that the k-nearest neighbors classifier would make at each point in the decision space. So for example, a point out here in the yellow region represents a point that the classifier would classify as class 0, and a point, let's say over here, the classifier would classify as class 1. So because this is a one nearest neighbors classifier, to make a classification prediction for any given query point, the classifier simply looks back into its training set. So these points here represent all the points in the training set. So for any given point, let's say here, the classifier will simply find the training point that's closest, namely this one, and assign the predicted class to simply the class of the nearest point in the training set. Likewise, if we have a point over here, the nearest point in the training set is actually this point right here that has a class 0 label, and so that point would get assigned a class 0. And in fact, this whole region right here represents all the points that are closer to the class 0 training point than any of the other class 1 training points. So this whole region here represents a one nearest neighbor's prediction of class 0. So the k-nearest neighbors classifier with k equal to 1, you can see that the decision boundaries that derive from that prediction are quite jagged and have high variance. And this is an example of a classification model that has high model complexity. And in fact, you can see that the one nearest neighbors classifier is overfitting the training data in this case. It's trying to get correct predictions for every single training point while ignoring this trend between the two classes, namely that most of the yellow points are in this side of the feature space, and most of the black points are on this side. So the one nearest neighbors classifier can be said to be overfitting in this case. And here's what happens when we increase k from 1 to 11. Now the classifier must combine the votes of the 11 nearest points, not just one. So single training data points no longer have as dramatic an influence on the prediction. The result is a much smoother decision boundary, which represents a model with lower model complexity, where the decision boundary has much less variance. Actually, if we increased k even higher to be the total number of points in the training set, the result would be a single decision region where all predictions would be the most frequent class in the training data. And as we saw for the fruit data set, k nearest neighbors classifiers can be applied to any number of classes, not just two. The code for this example in the notebook uses a special function in the shared utilities library for this course called plot toClass KNN. If you run this code and compare the resulting training and test scores for k equals 1, 3, and 11, which are shown in the title of each plot, you can see the effect of model complexity on a model's ability to generalize. In the k equals 1 case, the training score is a perfect 1.0, but the test score is only 0.80. As k increases to 3, the training score drops to 0.88, but the test score rises slightly to 0.88, indicating the model is generalizing better to new data. When k equals 11, the training score drops a bit further to 0.81, but the test score is even better at 0.92, indicating that this simple model is much more effective at ignoring minor variations in the training data and instead capturing the more important global trend in where the classes tend to be located, with the best overall generalization performance as a result. The nearest neighbors approach isn't useful just for classification. You can use it for regression too. So here are 3 plots that show the same simple regression problem with one input feature and the corresponding target values in the training data. The leftmost plot here, this one, shows just the original training data points. And the middle and right plots show the predictions made by a KNN regression algorithm when k equals 1 and k equals 3. So in these plots, you can see the training points are actually in green. These green circles are the training points. And the blue triangles are the output of the k nearest neighbor regression for any given input value of x. So for example, the KNN regression prediction for this point here is this y value here. So how did the nearest neighbors regressor compute these values? Well, it did it in a similar way to what we saw for classification. So for example, if the query point we're interested in is predicting the value associated with this x value, we simply find the training point that has the x value that's closest to this query point. So in this case, that would be this training point. And because this is a one nearest neighbor problem, we simply take the target value associated with this training point and use that as the output, the target for the query point. Similarly, if this were the query point here, then the nearest neighbor in the training set would be this point here. And so the output prediction for this particular x value will be the target value of the nearest neighbor, or this value that's just above 100. And so if we do that for all these different x values, we'll get these different predictions using the one nearest neighbor approach. Similarly, if we look at the k equals 3 case, where we look at 3 nearest neighbors, let's take this example here of negative 1.25, let's say. Well, what are the 3 training points that have x values closest to negative 1.25? They would be this training point, that training point, and this training point. Now, with regression, what we do is instead of taking a majority vote, we don't have class values here as targets, we have continuous values. So we can average these 3 target values. And if we do that, we find that the output when the query point is this x value is going to be the average of the y values of the 3 nearest training points, or this value here. Similarly, if we have a query point that is here, then the 3 nearest neighbor points are here, here, and here. And the average target value of these 3 training points is something like this. Here's the corresponding code in the notebook that produced these regression plots. These use the k-neighbors regressor class, which, like the classification case, takes the n-neighbors setting as a key parameter. Because the target values in a regression problem are continuous, as compared to the discrete values that we see for classifier target labels, to assess how well a regression model fits the data, we use a regression score called R-squared, that's between 0 and 1. We'll cover some additional types of regression evaluation scores later in the course. For the R-squared value, a value of 1 corresponds to the best possible performance, a model that makes perfect predictions. A value of 0 corresponds to a model that makes a constant value prediction that's always just the mean value of all the training target values. The R-squared value is sometimes known as the coefficient of determination. Just as we did for classification, let's look at the connection between model complexity and generalization ability as measured by the R-squared training and test values on this simple regression dataset. This series of plots in the notebook shows how the KNN regression algorithm fits the data for k equals 1, 3, 7, 15, and in an extreme case of k equals 55 that represents almost half the training points. We can see the same pattern in model complexity for KNN regression that we saw for KNN classification, namely that small values of k give models with higher complexity, and large values of k result in simpler models with lower complexity. Starting on the left, when k equals 1, the regression model fits the training data perfectly with an R-squared score of 1.0. But it's very bad at predicting the target values for new data samples, as reflected in the R-squared test score of only 0.155. As the value of k increases, which we can see acts to smooth out these local variations to capture more of the global trend. Again, the training set score drops, but the model gets better at generalizing to new data, and the test score goes up as k increases. Finally, in this series, the model with k equals 15 has the best test set performance, with an R-squared score of 0.485. Increasing k much further, however, to k equals 55 results in both the training and test set scores dropping back down to lower levels, as the model now starts to underfit. In other words, it's too simple to do well even on the training data. The pros of the nearest neighbor approach are that it's simple and easy to understand why a particular prediction is made. A k-nearest neighbor approach can be a reasonable baseline against which you can compare the performance of more sophisticated methods. When the training data has many instances, or each instance has lots of features, this can really slow down the performance of a k-nearest neighbors model. So in general, if your data set has hundreds or thousands of features, you should consider alternatives to k-nearest neighbors models, especially if your data is sparse, meaning that each instance has lots of features, but most of them are 0. So to sum up, and as a review of what we saw in week 1, the 2 key parameters for both regression and classification in nearest neighbors models are naturally n neighbors, which controls the value of the number of neighbors to consider, and thus the model complexity, as we saw, and the metric parameter, which controls the distance function between points, and thus which points are considered as nearest when finding neighbors. We didn't explore the metric parameter here, and that's beyond the scope of this course, but in most cases, the default Euclidean setting works pretty well with most data sets. One of the simplest kinds of supervised models are linear models. A linear model expresses the target output value in terms of a sum of weighted input variables. For example, our goal may be to predict the market value of a house, its expected sales price in the next month, for example. Suppose we're given two input variables: how much tax the property is assessed each year by the local government, and the age of the house in years. You could imagine that these two features of the house would each have some information that's helpful in predicting the market price, because in most places there's a positive correlation between the tax assessment on a house and its market value. Indeed, the tax assessment is often partly based on market prices from previous years, and maybe a negative correlation between its age in years and the market value. So older houses may need more repair and upgrading, for example. One linear model, which I've made up as an example, could compute the expected market price in US dollars by starting with a constant term, here 212,000, and then adding some number, let's say 109 times the value of tax paid last year, and then subtracting 2,000 times the age of the house in years. So for example, this linear model would estimate the market price of a house where the tax assessment was $10,000 and that was 75 years old as about 1.2 million US dollars. Now, I just made up this particular linear model myself as an example, but in general, when we talk about training a linear model, we mean estimating values for the parameters of the model, or coefficients of the model, as we sometimes call them, which are here the constant value, 212,000, and the weights, 109 and 20, in such a way that the resulting predictions for the outcome variable y price for different houses are a good fit to the data from actual past sales. We'll discuss what good fit means shortly. Predicting house price is an example of a regression task using a linear model called, not surprisingly, linear regression. More generally, in a linear regression model, there may be multiple input variables or features, which will denote x0, x1, etc. Each feature, xi, has a corresponding weight, wi. The predicted output, which we denote y hat, is a weighted sum of features, plus a constant term, b hat. I've put a hat over all the quantities here that are estimated during the regression training process. The w hat and b hat values, which we call the train parameters or coefficients, are estimated from training data, and y hat is estimated from the linear function of input feature values and the train parameters. For example, in the simple housing price example we just saw, W0 hat was 109, X0 represented tax paid, W1 hat was negative 20, X1 was house age, and B hat was 212,000. We call these WI values model coefficients or sometimes feature weights, and B hat is called the bias term or the intercept of the model. Here's an example of a linear regression model with just one input variable or feature, x0, on a simple artificial example data set. The blue cloud of points represents a training set of x0, y pairs. In this case, the formula for predicting the output y hat is just w0 hat times x0 plus b hat, which you might recognize as the familiar slope-intercept formula for a straight line, where w0 hat is the slope and b hat is the y-intercept. The gray and red lines represent different possible linear regression models that could attempt to explain the relationship between x0 and y. You can see that some lines are a better fit than others. The better fitting models capture the approximately linear relationship where, as x0 increases, y also increases in a linear fashion. The red line seems especially good. Intuitively, there are not as many blue training points that are very far above or very far below the red linear model prediction. Let's take a look at a very simple form of linear regression model that just has one input variable or feature to use for prediction. In this case, we have the vector x just has a single component. We'll call it x0. That's the input variable, the input feature. And In this case, because there's just one variable, the predicted output is simply the product of the weight W0 with the input variable X0 plus a bias term B. So X0 is the value that's provided. It comes with the data. And so the parameters we have to estimate are W0 and B in order to obtain the parameters for this linear regression model. So this formula may look familiar. It's the formula for a line in terms of its slope. In this case, slope corresponds to the weight W0, and B corresponds to the y-intercept, we call the bias term. So here, the job of the model is to take as input, let's pick a point here along the x-axis. So W0 corresponds to the slope of this line, and B corresponds to the y-intercept of the line. And so by finding these two parameters together define a straight line in this feature space. Now, the important thing to remember is that there's a training phase and a prediction phase. So the training phase, using the training data, is what we'll use to estimate W0 and B. So one widely used method for estimating W and B for a linear regression problem is called least squares linear regression, also known as ordinary least squares. Least squares linear regression finds the line through this cloud of points that minimizes what is called the mean squared error of the model. The mean squared error of the model is essentially the sum of the squared differences between the predicted target value and the actual target value for all the points in the training set. This plot illustrates what that means. The blue points represent points in the training set. The red line here represents the least squares model that was found through this cloud of training points. And these black lines show the difference between the y value that was predicted for a training point based on its x position and the actual y value of the training point. So for example here, this point, let's say, has an x value of negative 1.75. And if we plug it into the formula for this linear model, we get a prediction here at this point on the line, which is somewhere around, let's say, 60. But the actual observed value in the training set for this point was maybe closer to 10. So in this case, for this particular point, the squared difference between the predicted target and the actual target would be 60 minus 10 squared. So we can do this calculation for every one of the points in the training set. We can compute this squared difference between the y value we observe in the training set for a point and the y value that we predicted by the linear model given that training point's x value. So each of these can be computed, as this squared difference can be computed. And then if we add all these up and divide by the number of training points, take the average, that will be the mean squared error of the model. So the technique of least squares is designed to find the slope, the w value, and the b value, the y-intercept, that minimize this squared error, this mean squared error. One thing to note about this linear regression model is that there are no parameters to control the model complexity. No matter what the value of w and b, the result is always going to be a straight line. This is both a strength and a weakness of the model, as we'll see later. When you have a moment, compare this simple linear model to the more complex regression model learned with k-nearest neighbors regression on the same data set. You can see that linear models make a strong prior assumption about the relationship between the input x and output y. Linear models may seem simplistic, but for data with many features, linear models can be very effective and generalize well to new data beyond the training set. Now the question is, how exactly do we estimate the linear model's w and b parameters so the model is a good fit? Well, the w and b parameters are estimated using the training data, and there are lots of different methods for estimating w and b depending on the criteria you'd like to use for the definition of what a good fit to the training data is and how you want to control model complexity. For linear models, model complexity is based on the nature of the weights w on the input features. Simpler linear models have a weight vector w that's closer to 0, i.e. where more features are either not used at all and have 0 weight, or have less influence on the outcome, a very small weight. Typically, given possible settings for the model parameters, the learning algorithm predicts the target value for each training example, and then computes what is called a loss function for each training example. That's a penalty value for incorrect predictions. A prediction is incorrect when the predicted target value is different than the actual target value in the training set. For example, a squared loss function would return the squared difference between the target value and the actual value as the penalty. The learning algorithm then computes or searches for the set of w-b parameters that minimize the total of this loss function over all training points. The most popular way to estimate w and b parameters is using what's called least squares linear regression, or ordinary least squares. Least squares finds the values of w and b that minimize the total sum of squared differences between the predicted y value and the actual y value in the training set. Or equivalently, it minimizes the mean squared error of the model. Least squares is based on the squared loss function mentioned before. This is illustrated graphically here, where I've zoomed in on the left lower portion of the simple regression dataset. The red line represents the least squares solution for w and b through the training data, and the vertical lines represent the difference between the actual y value of a training point, xi, y, and its predicted y value given xi, which lies on the red line where x equals xi. Adding up all the squared values of these differences for all the training points gives the total squared error, and this is what the least squares solution minimizes. Here, there are no parameters to control model complexity. The linear model always uses all of the input variables and always is represented by a straight line. Another name for this quantity is the residual sum of squares. The actual target value is given in yi, and the predicted y hat value for the same training example is given by the right side of the formula using the linear model with the parameters w and b. Let's look at how to implement this in scikit-learn. Linear regression in scikit-learn is implemented by the linear regression class in the sklearn.linearModel module. As we did with other estimators in scikit-learn, like the nearest neighbors classifier and the regression models, we use the train test split function on the original dataset and then create and fit the linear regression object using the training data in xtrain and the corresponding training data target values in ytrain. Here, note that we're doing the creation and fitting of the linear regression object in one line by chaining the fit method with the constructor for the new object. The linear regression fit method acts to estimate the feature weights w, which it calls the coefficients of the model, and it stores this in the coef underscore attribute, and the bias term b, which is stored in the intercept underscore attribute. Note that if a scikit-learn object's attribute ends with an underscore, this means that these attributes were derived from training data and not, say, quantities that were set by the user. If we dump the coef underscore and intercept underscore attributes for this simple example, We see that because there's only one input feature variable, there's only one element in the coef underscore list, the value 45.7. The intercept attribute has a value of about 148.4. And we can see that, indeed, these correspond to the red line shown in the plot, which has a slope of 45.7 and a y-intercept of about 148.4. Here's the same code in the notebook, with additional code to score the quality of the regression model in the same way that we did for k-nearest neighbors regression, using the R-squared metric. And here's the notebook code we used to plot the least squares linear solution for this data set. Now that we've seen both k-nearest neighbors regression and least squares regression, it's interesting now to compare the least squared linear regression results with the k-nearest neighbor results. Here we can see how these two regression methods represent two complementary types of supervised learning. The k-nearest neighbor regressor doesn't make a lot of assumptions about the structure of the data and gives potentially accurate but sometimes unstable predictions that are sensitive to small changes in the training data. So it has a correspondingly higher training set R-squared score compared to least squares linear regression. KNN achieves an R-squared score of 0.72, and least squares achieves an R-squared of 0.679 on the training set. On the other hand, linear models make strong assumptions about the structure of the data. In other words, that the target value can be predicted using a weighted sum of the input variables. And linear models give stable but potentially inaccurate predictions. However, in this case, it turns out that the linear model's strong assumption that there's a linear relationship between the input and output variables happens to be a good fit for this data set. And so it's better at more accurately predicting the y value for new x values that weren't seen during training. And we can see that the linear model gets a slightly better test set score of 0.492 versus 0.471 for k-nearest neighbors. And this indicates its ability to better generalize and capture this global linear trend. Now we'll look at another way to estimate W and B for a linear model, called ridge regression. Ridge regression uses the same least squares criterion, but with one difference. During the training phase, it adds a penalty for feature weights, the WI values, that are too large, as shown in the equation here. You'll see that large weights means mathematically that the sum of their squared values is large. Once ridge regression has estimated the W and B parameters for the linear model, the prediction of y values for new instances is exactly the same as in least squares. You just plug in your input feature values, the xi's, and compute the sum of the weighted feature values plus b with the usual linear formula. So why would something like ridge regression be useful? This addition of a penalty term to a learning algorithm's objective function is called regularization. Regularization is an extremely important concept in machine learning. It's a way to prevent overfitting and thus improve the likely generalization performance of a model by restricting the model's possible parameter settings. Usually the effect of this restriction from regularization is to reduce the complexity of the final estimated model. So how does this work with linear regression? The addition of the sum of squared parameter values that's shown in the box to the least squares objective means that models with larger feature weights W add more to the objective function's overall value. Because our goal is to minimize the overall objective function, the regularization term acts as a penalty on models with lots of large feature weight values. In other words, all things being equal, if ridge regression finds two possible linear models that predict the training data values equally well, it will prefer the linear model that has smaller overall sum of squared feature weights. The practical effect of using ridge regression is to find the feature weights, WI, that fit the data well in a least squares sense and that set lots of the feature weights to values that are very small. We don't see this effect with a single variable linear regression example, but for regression problems with dozens or hundreds of features, the accuracy improvement from using regularized linear regression like ridge regression can be significant. The amount of regularization to apply is controlled by the alpha parameter. Larger alpha means more regularization and simpler linear models with weights closer to 0. The default setting for alpha is 1.0. Notice that setting alpha to 0 corresponds to the special case of ordinary least squares linear regression that we saw earlier that minimizes the total squared error. In scikit-learn, you use ridge regression by importing the ridge class from sklearn.linearModel and then use that estimator object just as you would for least squares. The one difference is that you can specify the amount of the ridge regression regularization penalty, which is called an L2 penalty, using the alpha parameter. Here, we're applying ridge regression to the crime dataset. Now, you'll notice here that the results are not that impressive. The R-squared score on the test set is pretty comparable to what we got for least squares regression. However, there's something we can do in applying ridge regression that will improve the results dramatically. So now's the time for a brief digression about the need for feature preprocessing and normalization. Let's stop and think for a moment intuitively what ridge regression is doing. It's regularizing the linear regression by imposing that sum of squares penalty on the size of the W coefficients. So the effect of increasing alpha is to shrink the W coefficients towards 0 and towards each other. But if the input variables, the features, have very different scales, then when this shrinkage happens of the coefficients, input variables with different scales will have different contributions to this L2 penalty, because the L2 penalty is the sum of squares of all the coefficients. So transforming the input features so they're all on the same scale means the ridge penalty is in some sense applied more fairly to all features without unduly weighting some more than others, just because of the difference in scales. So more generally, you'll see as we proceed through the course that feature normalization is important to perform for a number of different learning algorithms beyond just regularized regression. This includes k-nearest neighbors, support vector machines, neural networks, and others. The type of feature preprocessing and normalization that's needed can also depend on the data. For now, we're going to apply a widely used form of feature normalization called min-max scaling that will transform all the input variables so they're all on the same scale between 0 and 1. To do this, we compute the minimum and maximum values for each feature on the training data, and then apply the min-max transformation for each feature as shown here. Here's an example of how it works with two features. Suppose we have one feature, height, whose values fall in a fairly narrow range between 1.5 and 2.5 units. But a second feature, width, has a much wider range between 5 and 10 units. After applying min-max scaling, values for both features are transformed so they are on the same scale, with the minimum value getting mapped to 0 and the maximum value being transformed to 1, and everything else getting transformed to a value between those two extremes. To apply min-max scaling in scikit-learn, you import the min-max scalar object from sklearn.preprocessing. To prepare the scalar object for use, you create it and then call the fit method using the training data, xtrain. This will compute the min and max feature values for each feature in this training data set. Then to apply the scalar, you call its transform method and pass in the data you want to rescale. The output will be the scaled version of the input data. In this case, we want to scale the training data and save it in a new variable called xtrain scaled, and the test data, saving that into a new variable called xtest scaled. Then we just use these scaled versions of the feature data instead of the original feature data. Note that it can be more efficient to perform fitting and transforming in a single step on the training set by using the scalar's fit transform method as shown here. There's one last but very important point here about how to apply min-max scaling or any kind of feature normalization in a learning scenario with training and test sets. You may have noticed two things here. First, that we're applying the same scalar object to both the training and the test data. And second, that we're training the scalar object on the training data and not on the test data. These are both critical aspects to feature normalization. If you don't apply the same scaling to training and test sets, you'll end up with more or less random data skew, which will invalidate your results. If you prepare the scalar or other normalization method by showing it the test data instead of the training data, this leads to a phenomenon called data leakage, where the training phase has information that is leaked from the test set, for example, like the distribution of extreme values for each feature in the test data, which the learner should never have access to during training. This in turn can cause the learning method to give unrealistically good estimates on the same test set. We'll look more at the phenomenon of data leakage later in the course. One downside to performing feature normalization is that the resulting model on the transformed features may be harder to interpret. Again, in the end, the type of feature normalization that's best to apply can depend on the data set, learning task, and learning algorithm to be used. We'll continue to touch on this issue throughout the course. Okay, let's return to ridge regression after we've added the code for min-max scaling of the input features. We can see the significant effect of min-max scaling on the performance of ridge regression. After the input features have been properly scaled, ridge regression achieves significantly better model fit, with an R-squared value on the test set of about 0.6, much better than without scaling, and much better now than ordinary least squares. In fact, if you apply the same min-max scaling with ordinary least squares regression, you should find that it doesn't change the outcome at all. In general, regularization works especially well when you have relatively small amounts of training data compared to the number of features in your model. Regularization becomes less important as the amount of training data you have increases. We can see the effect of varying the amount of regularization on the scaled training and test data using different settings for alpha in this example. The best R-squared value on the test set is achieved with an alpha setting of around 20. Significantly larger or smaller values of alpha both lead to significantly worse model fit. This is another illustration of the general relationship between model complexity and test set performance that we saw earlier in this lecture, where there's often an intermediate best value of a model complexity parameter that does not lead to either under or overfitting. Another kind of regularized regression that you could use instead of ridge regression is called lasso regression. Like ridge regression, lasso regression adds a regularization penalty term to the ordinary least squares objective that causes the model W coefficients to shrink towards 0. Lasso regression uses a slightly different regularization term called an L1 penalty instead of ridge regression's L2 penalty, as shown here. The L1 penalty looks kind of similar to the L2 penalty in that it computes a sum over the coefficients, but it's a sum over the absolute values of the W coefficients instead of a sum of squares. And the results are noticeably different. With lasso regression, a subset of the coefficients are forced to be precisely 0, which is a kind of automatic feature selection, since with a weight of 0, the feature is essentially ignored completely in the model. This sparse solution, where only a subset of the most important features are left with non-zero weights, also makes the model easier to interpret in cases where there are more than a few input variables. Like ridge regression, the amount of regularization for the lasso regression is controlled by the parameter alpha, which by default is 0. Also like ridge regression, the purpose of using lasso regression is to estimate the W and B model coefficients. Once that's done, the prediction model formula is the same as for ordinary least squares. You just use the linear model. In general, lasso regression is most helpful if you think there are only a few variables that have a medium or large effect on the output variable. Otherwise, if there are lots of variables that contribute small or medium effects, ridge regression is typically the better choice. Let's take a look at lasso regression in scikit-learn using the notebook, using our Communities in Crime regression dataset. To use lasso regression, you import the lasso class from sklearn.linearModel, and then just use it as you would use an estimator like ridge regression. With some data sets, you may occasionally get a convergence warning, in which case you can set the max_iter attribute to a larger value, so typically at least 20,000 or possibly more. Increasing the max iter parameter will increase the computation time accordingly. In this example, we're applying lasso to a min-max scaled version of the crime dataset as we did for ridge regression. You can see that for alpha set to 2.0, only 20 features with non-zero weights remain, because with lasso regularization, most of the features are set to have weights of exactly 0. I've listed the features with non-zero weights in order of their descending magnitude from the output. Although we need to be careful in interpreting any results for data on a complex problem like crime, the lasso regression results do help us see some of the strongest relationships between the input variables and outcomes for this particular data set. For example, looking at the top 5 features with non-zero weight that are found by lasso regression, we can see that location factors like percentage of people in dense housing, which indicates urban areas, and socioeconomic variables like the fraction of vacant houses in an area are positively correlated with crime. And other variables like the percentage of families with 2 parents is negatively correlated. Finally, we can see the effect of tuning the regularization parameter alpha for lasso regression. Like we saw with ridge regression, there's an optimal range for alpha that gives the best test set performance that neither under or overfits. Of course, this best alpha value will be different for different data sets and depends on various other factors, such as the feature preprocessing methods being used. Let's suppose for a moment that we had a set of 2-dimensional data points with features x0 and x1. Then we could transform each data point by adding additional features that were the 3 unique multiplicative combinations of x0 and x1. So x0 squared, x0, x1, and x1 squared. So we've transformed our original 2-dimensional points into a set of 5-dimensional points that rely only on the information in the 2-dimensional points. Now we can write a new regression problem that tries to predict the same output variable, y hat, but using these 5 features instead of 2. The critical insight here is that this is still a linear regression problem. The features are just numbers within a weighted sum. So we can use the same least squares techniques to estimate the 5 model coefficients for these 5 features that we used in the simpler 2-dimensional case. Now, why would we want to do this kind of transformation? Well, this is called polynomial feature transformation that we can use to transform a problem into a higher dimensional regression space. And in effect, adding these extra polynomial features allows us a much richer set of complex functions that we can use to fit to the data. So you can think of this intuitively as allowing polynomials to be fit to the training data instead of simply a straight line, but using the same least squares criterion that minimizes mean squared error. We'll see later that this approach of adding new features like polynomial features is also very effective with classification, and we'll look at this kind of transformation again in kernelized support vector machines. When we add these new polynomial features, we're essentially adding to the model's ability to capture interactions between the different variables by adding them as features to the linear model. For example, it may be that housing prices vary as a quadratic function of both the lot size that a house sits on and the amount of taxes paid on the property, as a theoretical example. A simple linear model could not capture this nonlinear relationship, but by adding nonlinear features like polynomials to the linear regression model, we can capture this nonlinearity. More generally, we can use other types of nonlinear feature transformations beyond just polynomials. This is beyond the scope of this course, but technically these are called nonlinear basis functions for regression and are widely used. Of course, one side effect of adding lots of new features, especially when we're taking every possible combination of k variables, is that these more complex models have the potential for overfitting. So in practice, polynomial regression is often done with a regularized learning method like ridge regression. Here's an example of polynomial regression using scikit-learn. There's already a handy class called polynomial features in the sklearn.preprocessing module that will generate these polynomial features for us. This example shows 3 regressions on a more complex regression dataset that happens to have some quadratic interactions between variables. The first regression here just uses least squares regression without the polynomial feature transformation. The second regression creates the polynomial features object with degree set to 2, and then calls the fit transform method of the polynomial features object on the original xf1 features to produce the new polynomial transformed features xf1 poly. The code then calls ordinary least squares linear regression. You can see indications of overfitting on this expanded feature representation as the model's R² score on the training set is close to 1, but much lower on the test set. So the third regression shows the effect of adding regularization via ridge regression on this expanded feature set. Now the training and test R² scores are basically the same, with the test set score of the regularized polynomial regression performing the best of all 3 regression methods. We're now going to look at a second supervised learning method that, in spite of being called a regression method, is actually used for classification, and it's called logistic regression. Logistic regression can be seen as a kind of generalized linear model. And like ordinary least squares and other regression methods, logistic regression takes a set of input variables, the features, and estimates a target value. However, unlike ordinary linear regression, in its most basic form, logistic regression's target value is a binary variable instead of a continuous value. There are flavors of logistic regression that can also be used in cases where the target value to be predicted is a multi-class categorical variable, not just binary. But for now, we'll focus on the simple binary case of logistic regression. Let's start by looking at linear regression, which we saw earlier. Linear regression predicts a real-valued output y based on a weighted sum of input variables or features, xi, plus a constant b term. This diagram shows that formula in graphical form. The square boxes on the left represent the input features, xi, and the values above the arrows represent the weights that each xi is multiplied by. The output variable y in the box on the right is the sum of all the weighted inputs that are connected into it. Note that we're adding b as a constant term by treating it as the product of a special constant feature with value 1 multiplied by a weight of value b. This formula is summarized in equation form below the diagram. The job of linear regression is to estimate values for the model coefficients wi hat and b hat that give a model that best fit the training data with minimal squared error. Logistic regression is similar to linear regression, but with one critical addition. Here we show the same type of diagram that we showed for linear regression, with the input variables xi in the left boxes and the model coefficients wi and b above the arrows. The logistic regression model still computes a weighted sum of the input features xi and the intercept term b, but it runs this result through a special nonlinear function f, the logistic function, represented by this new box in the middle of the diagram to produce the output y. The logistic function itself is shown in more detail on the plot on the right. It's an S-shaped function that gets closer and closer to 1 as the input value increases above 0, and closer to 0 as the input value decreases far below 0. The effect of applying the logistic function is to compress the output of the linear function so that it's limited to a range between 0 and 1. Below the diagram, you can see the formula for the predicted output y hat, which first computes the same linear combination of the inputs xi, model coefficient weights wi hat, and intercept b hat, but runs it through the additional step of applying the logistic function to produce y hat. If we pick different values for b hat and the w hat coefficients, we'll get different variants of this S-shaped logistic function, which again is always between 0 and 1. Because the job of basic logistic regression is to predict a binary output value, you can see how this might be used for binary classification. We could identify data instances with a target value of 0 as belonging to the negative class, and data instances with a target value of 1 as belonging to the positive class. Then, the value of y hat, that's the output from the logistic regression formula, can be interpreted as the probability that the input data instance belongs to the positive class given its input features. Let's look at a specific example of logistic regression with one input variable. Suppose we want to predict whether or not a student will pass a final exam based on a single input variable that's the number of hours they spend studying for the exam. Students who end up failing the exam are assigned to the negative class, which corresponds to a target value of 0, and students who pass the exam are assigned to the positive class and associated with a target value of 1. This plot shows an example training set. The x-axis corresponds to the number of hours studied, and the y-axis corresponds to the probability of passing the exam. The red points to the left with a target value of 0 represent points in the training set which are examples of students who failed the exam along with the number of hours they spent studying. Likewise, the blue points with target value 1 on the right represent points in the training set corresponding to students who passed the exam, with their x values representing the number of hours those students spent studying. Using logistic regression, we can estimate model coefficients for w hat and b hat that produce a logistic curve that best fits these training points. In this example, that logistic curve might look something like this. Once the model coefficients have been estimated, we now have a formula that can use the resulting logistic function to estimate the probability that any given student will pass the exam, given the number of hours they've studied. Students whose estimated probability of passing the exam is greater than or equal to 50% are predicted to be in the positive class. Otherwise, they're predicted to be in the negative class. So in this example, we can see that students who study for more than 3 hours will be predicted to be in the positive class. Let's look at an example that uses 2 input features now instead of 1. Here, the plots show a training set with 2 classes. Each data point has 2 features. Feature 1 corresponds to the x-axis, and feature 2 corresponds to the y-axis. The data points in the red class on the left form a cluster with low feature 1 value and high feature 2 value. And the points in the blue class have intermediate feature 1 value and low feature 2 value. We can apply logistic regression to learn a binary classifier using this training set, using the same idea we saw in the previous exam example. To do this, we'll add a third dimension, shown here as the vertical y-axis, corresponding to the probability of belonging to the positive class. We'll say that the red points are associated with the negative class and have a target value of 0, and the blue points are associated with the positive class and have a target value of 1. Then, just as we did in the exam studying example, we can estimate the w hat and b hat parameters of a logistic function that best fits this training data. The only difference is that the logistic function is now a function of 2 input features and not just 1. So it forms something like a 3-dimensional S-shaped sheet in this space. Once this logistic function has been estimated from the training data, we can use it to predict the class membership for any point given its feature 1 and feature 2 values, same way we did for the exam example. Any data instances whose logistic probability estimate y hat is greater than or equal to 0.5 are predicted to be in the positive blue class, otherwise in the other red class. Now if we imagine that there's a plane representing y equals 0.5, as shown here, that intersects this logistic function, it turns out that all the points that have a value of y equals 0.5, when you intersect that with a logistic function, the points all lie along a straight line. In other words, using logistic regression gives a linear decision boundary between the classes, as shown here. If you imagine looking straight down on the 3D logistic function on the left, you get the view that looks something like something on the right here. The points with y greater than or equal to 0.5 on the logistic function lie in a region to the right of the straight line, which is the dashed line on the right here. And the points with y less than 0.5 on the logistic function would form a region to the left of that dashed line. Let's look at an example with real data in scikit-learn. To perform logistic regression in scikit-learn, you import the logistic regression class from the sklearn.linearModel module, and then create the object and call the fit method using the training data just as you did for other classifiers like k-nearest neighbors. Here the code also sets a parameter c to 100, which we'll explain in a minute. The dataset we're using here is a modified form of our fruits dataset, using only height and width as the features in the feature space, and with the target class values modified into a binary classification problem, predicting whether an object is an apple, the positive class, or something other than an apple, the negative class. Here's a graphical display of the results. The x-axis corresponds to the height feature, and the y-axis corresponds to the width feature. The black points represent the positive apple class training points, and the yellow points are instances of all the other fruits in the training set. The gray decision region represents that area of the height and width feature space where a fruit would have an estimated probability greater than 0.5 of being an apple, and thus classified as an apple, according to the logistic regression function. The yellow decision region corresponds to the region of feature space for objects that have an estimated probability of less than 0.5 of being an apple. You can see the linear decision boundary where the gray region meets the yellow region that results from applying logistic regression. In fact, logistic regression results are often quite similar to those you might obtain from a linear support vector machine, another type of linear model we explore for classification. Like ridge and lasso regression, a regularization penalty on the model coefficients can also be applied with logistic regression and is controlled with the parameter c. In fact, the same L2 regularization penalty used for ridge regression is turned on by default for logistic regression with a default value c equals 1. Note that for both support vector machines and logistic regression, higher values of c correspond to less regularization. With large values of c, logistic regression tries to fit the training data as well as possible, while with small values of c, the model tries harder to find model coefficients that are closer to 0, even if that model fits the training data a little bit worse. You can see the effect of changing the regularization parameter c for logistic regression in this visual. Using the same apple classifier, we now vary c to take on values from 0.1 on the left to 1.0 in the middle and 100.0 on the right. Although the real power of regularization doesn't become evident until we have data that has higher dimensional feature spaces, you can get an idea of the trade-off that's happening between relying on a simpler model, one that puts more emphasis on a single feature in this case, out of the two features, but has lower training set accuracy. And that's an example as shown on the left with c equal 0.1. Or better training data fit on the right with c equal 100. You can find the code that created this example in the accompanying notebook. Finally, we show how logistic regression, again with L2 regularization turned on by default, can be applied to a real data set with many more features, the breast cancer data set. Here, logistic regression achieves both training and test set accuracy of 96%. Let's look at how linear models are also used for classification, starting with binary classification. This approach to prediction uses the same linear functional form as we saw for regression, but instead of predicting a continuous target value, we take the output of the linear function and apply the sign function to produce a binary output with two possible values, corresponding to the two possible class labels. If the target value is greater than 0, the function returns +1. And if it's less than 0, the function returns -1. Here's a specific example. So let's take a look at a simple linear classification problem, a binary problem that has two different classes and where each data instance is represented by two informative features. So we're going to call these features x1 on the x-axis and x2 on the y-axis. Now, how do we get from taking a data instance that's described by a particular combination of x1, x2 to a class prediction? Well, in a linear classifier, what we do is we take the feature values assigned to a particular data point. So in this case, it might be 2.10. So that represents the x1 and x2 feature values for this particular instance, let's say. And so that corresponds to the input here. And then we take those two x1, x2 values and put them through a linear function f here. And the output of this f needs to be a class value. So either we want it to return +1 if it's in one class and -1 if it's in the other class. So the linear classifier does that by computing a linear function of x1, x2. That's represented by this part of the equation here. So this w is a vector of weights. This x represents the vector of feature values, and then b is a bias term that gets added in. So this is a dot product. This circle here is a dot product, which means that, let's say in the simple case where we had weight vector 1 and 2, and a feature vector of x1, x2. The dot product of those is simply the linear combination of w1, x1 plus w2, x2. And then, so we take the x values, and we have certain weights that are learned for the classifier. So we compute w1, x1 plus w2, x2, and then we feed that, and then plus a bias term if there is one. And we feed the output of that through this sine function that converts the value in here. If it's above 0, it'll convert it to +1, and if it's below 0, it'll convert it to -1. And that's what the equation represents here. So that is the very simple rule that we use to convert a data instance with its input features to an output prediction. Okay, let's take a look using a specific linear function to see how this works in practice. So what I've done here is drawn a straight line through this space that it's defined by the equation x1 minus x2 equals 0. In other words, every point on this line satisfies this equation. So you can see, for example, that x1 equals -1 and x2 equals -1, and if you subtract them, you get 0. Essentially, it's just the line that represents all the points where x1 and x2 are equal. So this corresponds to, so we can sort of rewrite this x1 minus x2 equals 0 into a form that uses a dot product of weights with the input vector x. So in order to get x1 minus x2 equals 0, that's equivalent to writing a linear function where you have a weight vector of 1 and -1 and a bias term of 0. So for example, so if we have weights w1, w2, and dot product of x1, x2, recall that this is just the same as computing w1, x1 plus w2, x2. And so in this case, if w is 1 and -1, that's equivalent to x1 minus x2. So all I've done here then is just convert the description of this line into a form that can be used as a decision rule for a classifier. So it might help to look at a specific point. So suppose that we wanted to classify the point here that had coordinates negative 0.75 and negative 2.25. So this point right here. So all we would do to have the classifier make a prediction with this decision boundary would be to plug in those coordinates into this part of the function, apply the weights and the bias term that describe the decision boundary. So here we're computing, so this expression here corresponds to this part of the equation. And so if we compute weight 1 times x1 plus weight 2 times x2 plus 0, we get a value of 0.15 that's inside the sine function, and then the sine function will output 1 if this value is greater than 0, which it is, or minus 1 if the value is less than 0. So in this case, because it's greater than 0, the output from the decision function would be plus 1. So this has classified this point as being of class 1. If we look at a different point, let's take a look at the point negative 1.75 and negative 0.25. So again, we're just going to, so this is corresponding to the value of x1 and x2. And again, if we just take these values and plug them into this part of the equation, apply the weights and the bias term that describe the decision boundaries that we did before, we do this computation, we find out that, in fact, classifier predicts a class of -1 here. So you see that by applying a simple linear formula, we've been able to produce a class value for any point in this two-dimensional feature space. So one way to define a good classifier is to reward classifiers for the amount of separation they can provide between the two classes. And to do this, we need to define the concept of classifier margin. So informally, for a given classifier, the margin is the width that the decision boundary can be increased before hitting a data point. So what we do is we take the decision boundary and we grow a region around it that sort of in perpendicular to the line this direction and that direction, and we grow this width until we hit a data point. So in this case, we were only able to grow the margin a small amount here before hitting this data point. So this width here between the decision boundary and the nearest data point represents the margin of this particular classifier. Now you can imagine that for every classifier that we tried, we can do the same kind of calculation or simulation to find the margin. And so among all possible classifiers that separate these two classes then, we can define the best classifier as the classifier that has the maximum amount of margin, which corresponds to the one shown here. So you recall that the original classifier on the previous slide had a very small margin. This one manages to achieve a much larger margin. So again, the margin is the distance, the width that we can go from the decision boundary perpendicular to the nearest data point. And so you can see that by defining this concept of margin, it sort of quantifies the degree to which the classifier can split the classes into two regions that have some amount of separation between them. We can actually do a search for the classifier that has the maximum margin. And this maximum margin classifier is called a linear support vector machine, also known as an LSVM or a support vector machine with linear kernel. Now we'll explain more about what the concept of a kernel is and how you can define nonlinear kernels as well as kernels and why you want to do that We'll cover those shortly in a continuation of our support vector machine lecture later in this particular week. Here's an example in the notebook on how to use the default linear support vector classifier in scikit-learn, which is defined in the sklearn SVM library. The linear SVC class implements a linear support vector classifier and is trained in the same way as other classifiers, namely by using the fit method on the training data. Now, in the simple classification problem I just showed you, the two classes were perfectly separable with a linear classifier. In practice, though, we typically have noise or just more complexity in the dataset that makes a perfect linear separation impossible. But where most points can be separated without errors by a linear classifier. And our simple binary classification dataset here is an illustration of that. So how tolerant the support vector machine is of misclassifying training points as compared to its objective of minimizing the margin between classes is controlled by a regularization parameter called C, which by default is set to 1.0, as we have here. Larger values of C represent less regularization and will cause the model to fit the training set with as few errors as possible, even if it means using a smaller margin decision boundary. Very small values of C, on the other hand, use more regularization that encourages the classifier to find a large margin decision boundary, even if that decision boundary leads to more points being misclassified. Here's an example in the notebook showing the effect of varying C on this basic classification problem. On the right, when C is large, the decision boundary is adjusted so that more of the black training points are correctly classified, while on the left, for small values of C, the classifier is more tolerant of these errors in favor of capturing the majority of data points correctly with a larger margin. Finally, here's an example of applying the linear support vector machine to a real-world dataset, the breast cancer classification problem. And here we can see it achieves reasonable accuracy without much parameter tuning. On the positive side, linear models, in the case of linear and logistic regression, are simple and easy to train. And for all types of linear models, prediction's very fast because of the linear nature of the prediction function. Linear models, including linear support vector machines, also perform effectively on high-dimensional dataset, especially in cases where the data instances are sparse. Linear models scale well to very large datasets as well. In the case of linear support vector machines, they only use a subset of training points in the decision function. These training points are called support vectors, so the algorithm can be implemented in a memory-efficient way. In the examples we've used so far for classification, we've primarily focused on binary classification, where the target value to be predicted was a binary value. It was either a positive or a negative class. In a lot of real-world data sets, the target value to be predicted is actually a category. So for example, in our fruit data set, there were 4 different categories of fruit to be predicted, not just 2. So how do we deal with this multi-class classification situation with scikit-learn? Well, fortunately, scikit-learn makes it very easy to learn multi-class classification models. Essentially, it does this by converting a multi-class classification problem into a series of binary problems. What do I mean by that? Well, essentially when you pass in a data set that has a categorical variable for the target value, scikit-learn detects this automatically. And then for each class to be predicted, scikit-learn creates one binary classifier that predicts that class against all the other classes. So for example, in the fruit data set, there are 4 categories of fruit, so scikit-learn learns 4 different binary classifiers. To predict a new data instance, what it then does is takes that data instance to be predicted, whose label is to be predicted, and runs it against each of the binary classifiers in turn. And the classifier that has the highest score is the one that whose class it uses as the prediction value. So let's look at a specific example of multi-class classification with this fruit data set. Here we simply pass in the normal data set that has the value from 1 to 4 as the category of fruit to be predicted. And we fit it exactly the same way that we would fit the model as if it were a binary problem. And in general, if we're just fitting and then predicting, all of this would be completely transparent. Scikit-learn would simply do the right thing, and it would learn multiple classes, and it would predict multiple classes, and we wouldn't really have to do much else. However, we can get access to what's happening under the hood, as it were, if we look at the coefficients and the intercepts of the linear models that result from fitting to the training data. And this is what this example shows. So what we're doing here is fitting a linear support vector machine to the fruit training data. And if we look at the coefficient values, we'll see that instead of just one pair of coefficients for a single linear model classifier, we actually get 4 values. And these values correspond to the 4 classes of fruit in the training set. And so what scikit-learn has done here is it's created 4 binary classifiers, 1 for each class. And so you can see there are 4 pairs of coefficients here, and there are also 4 intercept values. So in this case, the first pair of coefficients corresponds to a classifier that classifies apples versus the rest of the fruit. And so these pair of coefficients and this intercept define a straight line. In this case, it's this. So the apples in this visual are the red points. And so the coefficients of the apple model define a decision boundary, a linear decision boundary, that's marked by this red line here. And if you plot it out, you'll see that indeed it has an intercept of -3, and it's you can actually compute for any data instance using this linear formula what it'll predict, either apple or not an apple. So if we take a specific example, something that has a height of 2 and a width of 6, so some query point here, for example. This is a linear classifier, so we can take the coefficients, this first pair of coefficients here, and this first intercept value here, and these form a linear classifier for apples versus not apples. So we can take the height feature, multiply it by the first coefficient, take the width feature, multiply it by the second coefficient, and then add in the third intercept feature, this third bias term. And so to predict whether this object that has height of 2 and width of 6 is an apple, we simply compute this linear formula. It turns out that the value is positive 0.59. And so because that value is greater than or equal to 0, that indicates that the model is predicting that the object is indeed an apple. And that makes sense because it's on this side of the apple versus not apple binary classifier decision boundary. Similarly, we can take another object, say one who has a height of 2 and a width of 2, so in this part of the space over here. And we can plug in those 2 feature values into the same apple classifier. And when we do that, it turns out that the prediction value of the linear model in that case is -2.3, and that's less than 0, which is on this side of the decision boundary. And so the linear model for apple versus not apple here is predicting that this object is not an apple. And so again, when scikit-learn has to predict the class of a new object with potentially multiple classes, it will go through each of these binary classifiers in turn, and it will predict the class whose classifier has the highest score for that instance. We saw earlier how linear support vector machines served as effective classifiers for some data sets by finding a decision boundary with maximum margin between the classes. Linear support vector machines worked well for simpler kinds of classification problems, where the classes were linearly separable or close to linearly separable, like this example on the left. But with real data, many classification problems aren't this easy, with the different classes located in feature space in a way that a line or hyperplane can't act as an effective classifier. Here's an example on the right. This dataset is difficult or impossible for a linear model, a line or a hyperplane, to classify well. So to help address the situation, we're now going to turn to our next type of supervised learning model, a very powerful extension of linear support vector machines called kernelized support vector machines. Basically, kernelized support vector machines, which I'll just call SVMs, can provide more complex models that go beyond linear decision boundaries. As with other supervised machine learning methods, SVMs can be used for both classification and regression. But due to time constraints, we'll focus only on classification in this lecture. We also won't go into the mathematical details of how SVMs operate, but we will give a high-level overview that hopefully captures the most important elements of this method. In essence, one way to think about what kernelized SVMs do is that they take the original input data space and transform it to a new higher dimensional feature space, where it becomes much easier to classify the transformed data using a linear classifier. Here's a simple one-dimensional example of what I mean. Here's a binary classification problem in one dimension with a set of points that lie along the x-axis, colored black for one class and white for the second class. Each data point here has just one feature, its position on the x-axis. If we gave this problem to a linear support vector machine, it would have no problem finding the decision boundary that gives the maximum margin between points of different classes. Here I've engineered the data points so that the maximum margin decision boundary happens to be at x equals 0. Now suppose we gave the linear support vector machine a harder problem, where the classes are no longer linearly separable. A simple linear decision boundary just doesn't have enough expressive power to classify all these points correctly. So what can we do about this? One very powerful idea is to transform the input data from a one-dimensional space to a two-dimensional space. We can do this, for example, by mapping each one-dimensional input data instance, xi, to a corresponding two-dimensional ordered pair, xi squared, whose new second feature is the squared value of the first feature. We're not adding any new information in the sense that all we need to obtain this new two-dimensional version is already present in the original one-dimensional data point. This might remind you of a similar technique that we saw when adding polynomial features to a linear regression problem earlier in the course. We can now learn a linear support vector machine in this new two-dimensional feature space, whose maximum margin decision boundary might look like this here, to correctly classify the points. Any future one-dimensional points for which we'd like to predict the class, we can just create the two-dimensional transformed version and predict the class of the two-dimensional point using this two-dimensional linear SVM. If we took the inverse of the transformation we just applied to bring the data points back to our original input space, we can see that the linear decision boundary in the two-dimensional space corresponds to the 2 points where a parabola crosses the x-axis. Now, just so this very important idea is clear, let's move from a one-dimensional problem to a two-dimensional classification problem and see the same powerful idea in action here. Here we have two classes represented by the black and the white points, each of which has two features, x0 and x1. The points of both classes are scattered around the origin, 0, 0, in a two-dimensional plane. The white points form a cluster right around 0, 0 that's completely surrounded by the black points. Again, this looks to be impossible for a linear classifier, which in two-dimensional space is a straight line, to separate the white points from the black points with any degree of accuracy. But just as we did in the one-dimensional case, we can map each two-dimensional point, x0, x1, to a new three-dimensional point by adding a third feature, mathematically 1 minus x0 squared plus x1 squared. And this transformation acts to shape the points into a paraboloid around 0, 0. Now the white points, since they're close to 0, 0, get mapped to points with higher vertical z-values, that new third feature, that are close to 1. While the black points, which are farther from 0, 0, get mapped to points with z-values that are either close to 0 or even negative. With this transformation, it makes it possible to find a hyperplane, say z equals 0.9, that now easily separates the white data points that are near z equals 1 from most or all of the black data points. Finally, the decision boundary consists of the set of points in 3D space where the paraboloid intersects the maximum margin hyperplane decision boundary. This corresponds to an ellipse-like decision boundary in 2D space that separates the white points from the black points in the original input space. This idea of transforming the input data points to a new feature space where a linear classifier can be easily applied is a very general and powerful one. There are lots of different possible transformations we could apply to data. And the different kernels available for the kernelized SVM correspond to different transformations. Here we're going to focus mainly on what's called the radial basis function kernel, which we'll abbreviate as RBF, and also look briefly at something called a polynomial kernel that's also included with scikit-learn's SVM module. The kernel function in an SVM tells us, given 2 points in the original input space, what is their similarity in the new feature space. For the radial basis function kernel, the similarity between 2 points in the transformed feature space is an exponentially decaying function of the distance between the vectors in the original input space, as shown by the formula here. So what does the radial basis function feature transformation look like? Well, this diagram should give an intuitive idea. Here's another graphical illustration of a binary classification problem. And again, this diagram is for illustration purposes only, and it's just an approximation. But essentially, you can think of it in a similar way to the 2D to 3D example we saw earlier. So on the left, there's a set of samples in the input space. The circles represent the training points of one class, and the squares represent training points of a second class. On the right, the same samples are shown in the transformed feature space. Using the radial basis function kernel, in effect, transforms all the points inside a certain distance of the circle class to one area of the transformed feature space, and all the points in the square class outside a certain radius get moved to a different area of the feature space. The dark circles and squares represent the points that might lie along the maximum margin for a support vector machine in the transformed feature space. And also it shows the corresponding points in the original input space. So just as we saw with the simple 1D and 2D examples earlier, the kernelized support vector machine tries to find the decision boundary with maximum margin between classes using a linear classifier in the transformed feature space, not the original input space. The linear decision boundary, learned in feature space by a linear SVM, corresponds to a nonlinear decision boundary in the original input space. So in this example, an ellipse-like closed region in the input space. Now, one of the mathematically remarkable things about kernelized support vector machines, something referred to as the kernel trick, is that internally the algorithm doesn't have to perform this actual transformation on the data points to the new high-dimensional feature space. Instead, the kernelized SVM can compute these more complex decision boundaries just in terms of similarity calculations between pairs of points in the high-dimensional space, where the transformed feature representation is implicit. This similarity function, which mathematically is a kind of dot product, is the kernel in kernelized SVM. And for certain kinds of high-dimensional spaces, the similarity calculation between points, the kernel function, can have a simple form, like we see with the radial basis function calculation. This makes it practical to apply support vector machines when the underlying transformed feature space is complex or even infinite dimensional. Even better, we can easily plug in a variety of different kernels, choosing one to suit the properties of our data. Again, different choices of kernel correspond to different types of transformations to that higher dimensional feature space. Here's the result of using a support vector machine with RBF kernel on that more complex binary classification problem we saw earlier. You can see that unlike a linear classifier, the SVM with RBF kernel finds a more complex and very effective set of decision boundaries that are very good at separating one class from the other. Note that the SVM classifier is still using a maximum margin principle to find these decision boundaries, but because of the nonlinear transformation of the data, these boundaries may no longer always be equally distant from the margin edge points in the original input space. Now let's look at an example of how we did this using scikit-learn in Python. To use SVMs, we simply import the svc class from sklearn.svm and use it just as we would any other classifier, for example, by calling the fit method with the training data to train the model. There is an svc parameter called kernel that allows us to set the kernel function used by the SVM. By default, the SVM will use the radial basis function, but a number of other choices are supported. Here in the second example and plot, we show the use of the polynomial kernel instead of the RBF kernel. The polynomial kernel, using the kernel poly setting, essentially represents a feature transformation similar to the earlier quadratic example. In the lecture, this feature space represented in terms of features that are polynomial combinations of the original input features, much as we saw also for linear regression. The polynomial kernel takes an additional parameter, degree, that controls the model complexity and the computational cost of this transformation. You may have noticed that the RBF kernel has a parameter, gamma. Gamma controls how far the influence of a single training example reaches, which in turn affects how tightly the decision boundaries end up surrounding points in the input space. Small gamma means a larger similarity radius, so that points farther apart are considered similar, which results in more points being grouped together and smoother decision boundaries. On the other hand, for larger values of gamma, the kernel value decays more quickly, and points have to be very close to be considered similar. This results in more complex, tightly constrained decision boundaries. You can see the effect of increasing gamma, that is, sort of sharpening the kernel, in this example from the notebook. Small values of gamma give broader, smoother decision regions, while larger values of gamma give smaller, more complex decision regions. You can set the gamma parameter when creating the SVC object to control the kernel width in this way, as shown in this code. You may recall from linear SVMs that SVMs also have a regularization parameter, C, that controls the trade-off between satisfying the maximum margin criterion to find a simple decision boundary and avoiding misclassification errors on the training set. The C parameter is also an important one for kernelized SVMs, and it interacts with the gamma parameter. This example from the notebook shows the effect of varying C and gamma together. If gamma is large, then C will have little to no effect, while if gamma is small, the model is much more constrained and the effect of C will be similar to how it would affect a linear classifier. Typically, gamma and C are tuned together, with the optimal combination typically in an intermediate range of values, for example, gamma between 0.0001 and 10, and C between 0.1 and 100, though the specific optimal values will depend on your application. Kernelized SVMs are pretty sensitive to settings of gamma. The most important thing to remember when applying SVMs is that it's important to normalize the input data so that all the features have comparable units that are on the same scale. We saw this earlier with some other learning methods like regularized regression. Let's apply a support vector machine with RBF kernel to a real-world dataset to see why this normalization is important. Here, we'll apply a support vector machine with RBF kernel to the breast cancer dataset. Note that we're not touching the input data in any way. We're simply passing in the raw values. We can see the results with training set accuracy of 1.00 and the test set accuracy of 0.63 that show that the support vector machine is overfitting. It's doing well on the training data, but very poorly on the test data. Now let's add a min-max scalar transformation of the training data, remembering to also apply the same scalar to the test data. After this scalar has been applied, all the input features now lie in the same range, 0 to 1. And looking at these new results, the test set accuracy is much, much higher, at 96%. This illustrates what a huge difference normalizing the features of the training data can have on SVM performance. Let's review the strengths and weaknesses of support vector machines. On the positive side, support vector machines perform well on a range of data sets and have been successfully applied on data that ranges from text to images and many more types. The support vector machine is also potentially very versatile due to its ability to specify different kernel functions, including possible custom kernel functions depending on the data. Support vector machines also typically work well for both low and high dimensional data, including data with hundreds, thousands, or even millions of sparse dimensions. This makes it well suited to text classification, for example. On the negative side, as the training set size increases, the runtime speed and memory usage in the SVM training phase also increases. So for large data sets with hundreds of thousands or millions of instances, an SVM may become less practical. As we saw when applying a support vector machine to a real-world data set, using an SVM requires careful normalization of the input data as well as parameter tuning. The inputs should be normalized so that all features have comparable units and are on similar scales if they aren't already. Support vector machines also don't provide direct probability estimates for predictions, which are needed for some applications. Now, there are ways to estimate these probabilities using techniques such as Platt scaling, which transforms the output of the classifier to a probability distribution over classes by fitting a logistic regression model to the classifier scores. Finally, it can be difficult to interpret the internal model parameters of a support vector machine, which means the applicability of support vector machines in scenarios where interpretation is important for people may be limited when we want to understand why a particular prediction was made. As a reminder, there are three main parameters that control model complexity for kernelized SVMs. First, there's the kernel type, which defaults to RBF for radial basis function, but several other common types are available in scikit-learn's SVC module. Second, each kernel has one or more kernel-specific parameters that control aspects like the influence of training points according to their distance. In the case of the RBF kernel, SVM performance is very sensitive to the setting of the gamma parameter that controls the kernel width. Finally, for any support vector machine, the C regularization parameter operates as we've discussed before, and is typically tuned with the kernel parameter, such as gamma, for optimal performance. So far, we've seen a number of supervised learning methods, and when applying each of these methods, we followed a consistent series of steps. First, partitioning the dataset into training and test sets using the train-test split function, then calling the fit method on the training set to estimate the model, and finally applying the model by using the predict method to estimate a target value for the new data instances, or by using the score method to evaluate the trained model's performance on the test set. Let's remember that the reason we divided the original data into training and test sets was to use the test set as a way to estimate how well the model trained on the training data would generalize to new, previously unseen data. The test set represented data that had not been seen during training, but had the same general attributes as the original data set, or in more technical language, was drawn from the same underlying distribution as the training set. Cross-validation is a method that goes beyond evaluating a single model using a single train test split of the data by using multiple train test splits, each of which is used to train and evaluate a separate model. So why is this better than our original method of a single train test split? Well, you may have noticed, for example, by choosing different values for the random state seed parameter in the train test split function when you're working on some examples or assignments, that the accuracy score you get from running a classifier can vary quite a bit just by chance, depending on the specific samples that happen to end up in the training set. Cross-validation basically gives more stable and reliable estimates of how the classifier is likely to perform on average by running multiple different training test splits and then averaging the results, instead of relying entirely on a single particular training set. Here's a graphical illustration of how cross-validation operates on the data. The most common type of cross-validation is k-fold cross-validation, most commonly with k set to 5 or 10. For example, to do 5-fold cross-validation, the original dataset is partitioned into 5 parts of equal or close to equal size. Each of these parts is called a fold. Then a series of 5 models is trained, one per fold. The first model, Model 1, is trained using folds 2 through 5 as the training set and evaluated using fold 1 as the test set. The second model, Model 2, is trained using folds 1, 3, 4, and 5 as the training set and evaluated using fold 2 as the test set, and so on. When this process is done, we have 5 accuracy values, one per fold. In scikit-learn, you can use the cross-val score function from the model selection module to do cross-validation. The parameters are, first, the model you want to evaluate, and then the dataset, and then the corresponding ground truth target labels or values. By default, cross-val score does 3-fold cross-validation, so it returns 3 accuracy scores, one for each of the 3 folds. If you want to change the number of folds, you can set the CV parameter. For example, CV equals 10 will perform 10-fold cross-validation. It's typical to then compute the mean of all the accuracy scores across the folds and report the mean cross-validation score as a measure of how accurate we can expect the model to be on average. One benefit of computing the accuracy of a model on multiple splits instead of a single split is that it gives us potentially useful information about how sensitive the model is to the nature of the specific training set. We can look at the distribution of these multiple scores across all the cross-validation folds to see how likely it is that by chance the model will perform very badly or very well on any new data set. So we can do a sort of worst case or best case performance estimate from these multiple scores. This extra information does come with extra cost. It does take more time and computation to do cross-validation. So for example, if we perform k-fold cross-validation and we don't compute the fold results in parallel, it'll take about k times as long to get the accuracy scores as it would with just one train test split. However, the gain in our knowledge of how the model is likely to perform on future data is usually well worth this cost. In the default cross-validation setup, to use, for example, 5 folds, the first 20% of the records are used as the first fold, the next 20% for the second fold, and so on. One problem with this is that the data might have been created in such a way that the records are sorted or at least show some bias in the ordering by class label. For example, if you look at our fruit dataset, it happens that all the labels for classes 1 and 2, the apples and the mandarin oranges, come before classes 3 and 4 in the data file. So if we simply took the first 20% of records for fold 1, which would be used as the test set to evaluate model 1, it would evaluate the classifier only on class 1 and 2 examples and not at all on the other classes 3 and 4, which would greatly reduce the informativeness of the evaluation. So when you ask scikit-learn to do cross-validation for a classification task, it actually does instead what's called stratified k-fold cross-validation. The stratified cross-validation means that when splitting the data, the proportions of classes in each fold are made as close as possible to the actual proportion of the classes in the overall data set, as shown here. For regression, scikit-learn uses regular k-fold cross-validation, since the concept of preserving class proportions isn't something that's really relevant for everyday regression problems. At one extreme, we can do something called leave one out cross-validation, which is just k-fold cross-validation with k set to the number of data samples in the dataset. In other words, each fold consists of a single sample as the test set and the rest of the data as the training set. Of course, this uses even more computation, but for small data sets in particular, it can provide improved estimates because it gives the maximum possible amount of training data to a model, and that may help the performance of the model when the training sets are small. Sometimes we want to evaluate the effect that an important parameter of a model has on the cross-validation scores. The useful function validation curve makes it easy to run this type of experiment. Like cross-val score, validation curve will do threefold cross-validation by default, but you can adjust this with the CV parameter as well. Unlike cross-val score, you can also specify a classifier, parameter name, and set of parameter values you want to sweep across. So you first pass in the estimator object, or that is the classifier or regression object to use, followed by the dataset samples x and target values y, the name of the parameter to sweep, and the array of parameter values that that parameter should take on in doing the sweep. Validation curve will return two-dimensional arrays corresponding to evaluation on the training set and a test set. Each array has one row per parameter value in the sweep, and the number of columns is the number of cross-validation folds that are used. For example, the code shown here will fit 3 models using a radial basis function support vector machine on different subsets of the data, corresponding to the 3 different specified values of the kernel's gamma parameter. And it returns two 4x3 arrays, that is 4 levels of gamma and times 3 fits per level, containing scores for the training and test sets. You can plot these results from validation curve as shown here to get an idea of how sensitive the performance of the model is to changes in the given parameter. The x-axis corresponds to values of the parameter, and the y-axis gives the evaluation score, for example, the accuracy of the classifier. Finally, as a reminder, cross-validation is used to evaluate a model and not learn or tune a new model. To do model tuning, we'll look at how to tune a model's parameters using something called grid search in a later lecture. Decision trees are a popular supervised learning method that, like many other learning methods we've seen, can be used for both regression and classification. Decision trees are easy to use and understand, and are often a good exploratory method if you're interested in getting a better idea about what the influential features are in your dataset. Basically, decision trees learn a series of explicit if-then rules on feature values that result in a decision that predicts the target value. Here's a simple example. Suppose we're playing a game where one person's thinking of one of several possible objects. So let's say an automobile, a bus, an airplane, a bird, an elephant, and a dog. A second person has to guess the identity of that thing by asking as few yes or no questions as possible, up to a limit of no more than, say, 10 questions. Suppose the first person secretly thinks of an automobile. So one of the first questions the second person might ask is it alive? Intuitively, we know that this type of broad question is much more informative and helps eliminate a larger set of possibilities early on, compared to asking a more specific question right away, like, does it have orange fur with black stripes? The more specific questions might be useful later, once we've narrowed the class of things down to particular animals or vehicles, for example. If we think of the property of being alive as a binary feature of an object, and the property of having orange fur with black stripes as another feature, we can say that the is-alive feature is more informative at an early stage of guessing, and thus would appear higher in our tree of questions. When the answer to the first question comes back as no, it's not alive, a second question might be, Does it fly? When that answer comes back no, we can continue to narrow down the set of possible answers by asking more and more specific questions, such as, can it carry more than 10 people? In this way, any given object can be categorized as either matching the target object the first person is thinking of or not, according to its features, as determined by asking this series of yes or no questions. We can form these questions into a tree, with a node representing one question and the yes or no possible answers as the left and right branches from that node that connect the node to the next level of the tree, one question being answered at each level. At the bottom of the tree are nodes called leaf nodes that represent actual objects as the possible answers. For any object, there's a path from the root of the tree to that object that is determined by the answers to the specific yes or no questions at each level. For example, a dog is alive, cannot fly, and doesn't have a trunk. You can view this as a kind of simple decision tree for predicting the class of an object. We can generalize this idea of finding a set of rules that can learn to categorize an object into the correct category to many other classification tasks. For example, we're going to look at a classification task next that involves finding rules that can predict what species a particular flower is, based on measurements of certain parts of the flower. Rather than try to figure out these rules manually for every task, there are supervised algorithms that can learn them for us in a way that gets to an accurate decision quickly, which we'll look at now. Let's start by looking at a famous dataset in machine learning called the iris dataset. This dataset is included with scikit-learn in the Datasets module. Each instance in the dataset represents one of 3 different species of iris, a type of flower. There are 4 attributes, or features, for each instance that represent measurements of different parts of the flower. The sepal length in centimeters, the sepal width in centimeters, petal length in centimeters, and petal width in centimeters. The 3 species are called setosa, versicolor, and virginica. The dataset has measurements for 150 flowers with 50 examples of each species. The classification task is to predict which of the 3 species and instances given these measurements. Unlike our simple example involving yes or no questions, which were binary features of the object, the iris dataset's features are continuous values, so the rules to be learned will be of the form, for example, is petal length greater than 2.3 centimeters? Let's take a look at how a decision tree is built on this data. The goal when building a decision tree is to find the sequence of questions that has the best accuracy at classifying the data in the fewest steps. Looking at a decision tree, each decision splits the data into 2 branches based on some feature value being above or below a threshold. For example, whether the petal width is greater than 1.2 centimeters might be an example of a splitting rule. And that threshold is called a split point. An important concept is how informative a split of the data is. So intuitively, an informative split of the data is one that does an excellent job at separating one class from the others. An example of an informative split might be to put all instances of the flowers with petal length less than 2.35 centimeters into one bin and the rest in the other bin. This is an informative split because, at least for this training set, using that rule separates the setosa class completely from the others and allows us to predict the setosa class perfectly just based on this one measurement. A less informative split, like a rule like sepal width less than or equal to 3 centimeters, would not produce as clear a separation of one class from the others. So for the best split, the results should produce as homogeneous a set of classes as possible. There are a number of mathematical ways to compute the best split. One criterion that's widely used for decision trees is called information gain, for example. So to build a decision tree, the decision tree building algorithm starts by finding the feature that leads to the most informative split. For any given split of the data on a particular feature value, even for the best split, it's likely that some examples will still be incorrectly classified or need further splitting. In the iris dataset, If we look at all the flowers with petal length greater than 2.35 centimeters, for example, using that split leaves a pool of instances that are a combination of virginica and versicolor that still need to be distinguished further. So we can further improve the accuracy of the classification by continuing this process of finding the best split for the remaining subsets. With the iris dataset, we can further split into flowers that have petal length less than versus greater than 4.95 centimeters, for example. This second split is informative because the resulting subsets are more homogeneous. That is, the split did a good job at dividing virginica from versicolor based on this second split test. We can continue this process recursively until we're left with leaves in the decision tree that all have the same, or at least a predominant majority of a target value. Trees whose leaf nodes each have all the same target value are called pure, as opposed to mixed, where the leaf nodes are allowed to contain at least some mixture of the classes. To predict the class of a new instance, given its feature measurements, using the decision tree, we simply start at the root of the decision tree and take the decision at each level based on the appropriate feature measurement until we get to a leaf node. The prediction is then just the majority class of the instances in that leaf node. So for the iris data, for example, a flower that has a petal length of 3 centimeters, a petal width of 2 centimeters, and a sepal width of 2 centimeters would end up at this leaf node, whose instances are all of the virginica class. So the prediction would be virginica. Decision trees can also be used for regression using the same process of testing the feature values at each node and predicting the target value based on the contents of the leaf node. For regression, the leaf node prediction would be the mean value of the target values for the training points in that leaf. In scikit-learn, to build a decision tree, you import the decision tree classifier class from the sklearn tree module and fit it just as you would any classifier by creating the object and calling the fit method on the training data. This code first loads the iris dataset and then computes the training and test accuracy in predicting the three classes. Notice that the training data here is predicted perfectly with an accuracy of 1.0, while the test data is a little bit worse. This is an indication that the tree is likely overfitting. And in fact, this is a problem with building decision trees in general that keep adding rules until the leaf nodes are pure. Typically, such trees are overly complex and essentially memorize the training data. So when building decision trees, we need to use some additional strategy to prevent this overfitting. One strategy to prevent overfitting is to prevent the tree from becoming really detailed and complex by stopping its growth early. This is called pre-pruning. Another strategy is to build a complete tree with pure leaves, but then to prune back the tree into a simpler form. This is called post-pruning, or sometimes just pruning. The decision tree implementation in scikit-learn only implements pre-pruning. We can control tree complexity via pruning by limiting either the maximum depth of the tree, using the max depth parameter, or the maximum number of leaf nodes, using the max leaf nodes parameter. We can also set a threshold on the minimum number of instances that must be in a node to consider splitting it, and this would be using the min samples leaf parameter. We can see the effect of pre-pruning by setting max depth to 3 on the iris dataset. Now the accuracy on the training data is slightly worse, but the accuracy on the test data is slightly better. One great advantage of decision trees, at least when they're not too big, is that they're easy to interpret. Visualizing the entire tree can show you exactly how the decision tree is making its predictions. So let's take a look at an example. In the shared utilities Python code for this course, we've provided a function call named plot decision tree that takes the classifier object, the feature names, and the class names as input, and uses the GraphViz library to visualize the tree. It works by calling the export GraphViz function in the sklearn tree module to create a dot file, which is a text file description of the tree, and then using the GraphViz library to visualize the dot file, creating an image. Here's an example of how to call the plot decision tree function using the classifier we learned on the iris dataset. Here's the resulting plot for the unpruned iris dataset tree. The first line in a node indicates the decision rule being applied for that node. The second line indicates the total number of data instances for that node. The third line shows the class distribution among those instances, and the fourth line shows the majority class of that node's data instances. For example, in the root node, the initial pool of data has 37 Sentosa examples, 34 versicolor examples, and 41 Virginica examples. After the first split into subsets that have petal length less than or equal to 2.35 on the left, and those that have petal length greater than 2.35 on the right, we have a leaf node on the left that consists entirely of the 37 Sentosa examples, and a decision node on the right that has 34 versicolor and 41 Virginica examples. This node on the right then makes a second split based on petal length, using a threshold of 4.95 centimeters, and that creates two subsets of 36 samples on the left, containing 33 versicolor examples, and 39 samples on the right, 38 of which are Virginica examples. We've used an option when plotting the decision tree to fill the nodes with colors that indicate the majority class of the data instances associated with that node. The intensity of the color indicates the strength of the majority count for that class. For larger trees that have, say, a depth of more than 5 or 10, instead of trying to analyze all the paths in the tree, it can be useful to see which paths most of the data takes. This can be done by looking for the largest samples values in the nodes. For example, if we follow the largest samples values down this tree, we can see that a significant set of 35 Virginica examples are classified perfectly when their petal length is greater than 5.05 centimeters. Another way of analyzing the tree, instead of looking at the whole tree at once, is to do what's called a feature importance calculation. And this is one of the most useful and widely used types of summary analysis you can perform on a supervised learning model. Feature importance is typically a number between 0 and 1 that's assigned to an individual feature. It indicates how important that feature is to the overall prediction accuracy. A feature importance of 0 means that the feature is not used at all in the prediction. A feature importance of 1 means the feature perfectly predicts the target. Typically, feature importance numbers are always positive, and they're normalized so that they sum to 1. In scikit-learn, feature importance values are stored as a list in an estimator property called feature_importances_. And note the underscore at the end of the name, which indicates it's a property of the object that's set as a result of fitting the model, and not, say, as a user-defined property. The shared utilities Python file contains a function called plot feature importances that you can import and use to visualize feature importance. It plots a horizontal bar chart with the features listed along the y-axis by name and feature importance along the x-axis. Here's the feature importance chart for the iris decision tree. In this example, for this particular train test split of the iris dataset, the petal length feature easily has the largest feature importance weight. We can confirm this by looking at the decision tree that this indeed corresponds to that feature's position at the top of the decision tree, showing that this first level, just using the petal length feature, does a good job splitting the training data into separate classes. Note that if a feature has a low feature importance value, that doesn't necessarily mean that the feature is not important for prediction. It simply means that the particular feature wasn't chosen at an early level of the tree. And this could be because the feature may be identical or highly correlated with another informative feature, and so doesn't provide any new additional signal for prediction. Feature importance values don't tell us which specific classes a feature might be especially predictive for, and they also don't indicate more complex relationships between features that may influence prediction. Even so, the feature importance values provide an easy-to-understand summary that can give useful insight about individual features in the learned model. Because feature importance can vary depending on the specific model learned for a particular train test split, for example, it's common when computing feature importance to use an average over multiple train test splits, for example, when performing cross-validation. Finally, let's apply decision trees to the breast cancer dataset that we've been using across multiple supervised learning algorithms. Here, we're controlling the model complexity by setting the max depth and min samples leaf parameters. And we've included the visualization of the resulting tree here, followed by a feature importance plot. As an exercise, try removing these two parameters to just use the default settings to see the effect on test set accuracy and the increase in overfitting that occurs. For this training set, the mean concave points feature gives the most informative initial split, followed by the worst area parameter. One of the major advantages of decision trees as a supervised learning method is that the decision rules are easily visualized and interpreted by people, including users without machine learning expertise. This makes decision trees a useful choice for getting an initial understanding of what some of the more important features are likely to be for a particular prediction task. Another advantage of decision trees is that you can use them without having to do feature preprocessing or normalization. Since each feature is processed independently and the splitting of the data doesn't depend on the absolute scale of the feature, the decision algorithm can operate on the original training data pretty much as is. So decision trees tend to work well with datasets that have a mixture of feature types, binary, categorical, or continuous, and with features that are on very different scales. One drawback of decision trees is that despite the use of pruning, they can still overfit on all or parts of the data and may not achieve the best generalization performance compared to other methods. One way to overcome that problem is to create what's called an ensemble of decision trees, which combines multiple decision trees to make a prediction. And we'll look at ensembles of decision trees in a following lecture. So to recap, scikit-learn enables you to control the model complexity of your decision trees with three key parameters. First, max depth controls the maximum depth, or the number of split points the decision can have, and is probably the most common parameter used to reduce tree complexity and thus reduce overfitting. The min samples leaf parameter is the threshold that controls what the minimum number of data instances has to be in a leaf to avoid splitting it further. This setting also reduces tree complexity. Finally, max leaf nodes limits the total number of nodes that are leaves of the tree. In effect, setting this parameter will indirectly influence the other two parameters and vice versa. So in practice, adjusting only one of these three is typically enough to control most overfitting. Although even with the most optimized parameter settings, individual decision trees will still tend to overfit. When we began working with supervised machine learning methods, we evaluated a classifier's performance using its accuracy. Accuracy, as you might recall, is the fraction of samples that were classified correctly. That is, where the classifier's predicted label matched the correct or true label. We also evaluated a regression model's performance using the default R-squared metric. In this module, you'll learn why measures like accuracy, which are simple and easy to understand, also have drawbacks in that they don't give a complete enough picture of a supervised learning model's performance and may not be the right metric for measuring success in your application. So we're going to cover several additional evaluation metrics beyond accuracy. We'll see how they're defined, what the motivation is for using them, and how to use them in scikit-learn to get a better picture of how well a supervised model is doing on a given data set. You'll also learn about how to choose the right evaluation metrics for your application that can help you select the best model or find the optimal parameters. So let's return for a moment to this workflow diagram that we introduced earlier in the course. You see that evaluation is a key part of this development cycle in applied machine learning. Once a model is trained, the evaluation step provides critical feedback on the trained model's performance characteristics, particularly those that might be important for your application. The results of the evaluation step, for example, might help you understand which data instances are being classified or predicted incorrectly, which might in turn suggest better features or a different kernel function or other refinements to your learning model in the feature and model refinement phase. As we discussed earlier, the objective function that's optimized during the training phase may be a different, what's called a surrogate metric that's easier to use in practice for optimization purposes than what's used for the evaluation metric. For example, a commercial search engine might use a ranking algorithm that is trained to recommend relevant web pages that best match a query, in other words, trying to predict a relevant label for a page. And that might be the objective in the training phase, but there are many evaluation methods in the evaluation phase that could be applied to measure aspects of that search engine's performance using that ranking algorithm that are important to the search company's business, for example, such as how many unique users the system sees per day, or how long a typical user search session is, and so on. So the evaluation measures are the ones that in the end are used to select between different trained models or settings. Actually, commercial search applications typically use a scorecard of multiple evaluation metrics to make important business decisions or development decisions about what models are chosen for use. So it's very important to choose evaluation methods that match the goal of your application. For predicting the correct digit from a handwritten image, let's say, where each digit is equally likely, then accuracy may be a sufficient metric. However, there are other possible aspects of evaluation and model performance that are beyond average accuracy that may be critical to measure. For example, in a health application that uses a classifier to detect tumors in a medical image, we may want the classifier to err on the side of caution and flag anything that even has a small chance of being cancerous, even if it means sometimes incorrectly classifying healthy tissue as diseased. In this case, the classifier evaluation method would try to reduce what are called false negative predictions. We'll look at this in more detail shortly. More generally, your application goal might be based on very different metrics such as user satisfaction, amount of revenue to your page, or increase in patient survival rates. So in the end, you'll be selecting the model or parameter settings that optimize those end evaluation metrics that are important to your goal. So in this module, we'll be focusing first on the widely used case of evaluating binary classification. And then we'll look at evaluation for the more general case of multi-class evaluation, as well as regression. Before we start defining and using some evaluation metrics for binary classification, let's start by looking at an example of why just looking at accuracy may not be enough to gain a good picture of what a classifier is doing. It'll also show us how knowing more about the types of errors a learning algorithm makes can help us get a better picture of a model's predictive performance. First, let's consider the case where we have a binary classification task where there are a lot of instances labeled with a negative class, but only a few instances that belong to the positive class. For example, we might see this scenario in online search or recommender systems, where the system has to predict whether or not to display an advertisement or product suggestion, or show a query suggestion or item on a page that's likely to be relevant given a user's query and what they clicked on in the past, and so on. So those would be the positive examples. But of course, there are many, many irrelevant items that are in the negative class that don't make sense to show a user. And so this is called an imbalanced class scenario. Another example might be data sets of credit card transactions, where the vast majority of transactions are classified as normal and not fraud, with a small minority of transactions that could be classified as fraudulent. These situations, which also apply to multi-class classification problems, involve data sets that have imbalanced classes. Imbalanced classes are very common in machine learning scenarios, so it's important to understand how to work with them. In particular, let's assume that we have an e-commerce application where for every 1,000 randomly sampled product items, one of them is relevant to a user's need and the other 999 are not relevant. So recall that accuracy computed over a set of instances is just the number of instances where the classifier's label prediction was correct divided by the total number of instances. Let's suppose you develop a classifier for predicting relevant e-commerce items. And after you finish the development, you measure its accuracy on a test set to be 99.9%. At first, that might seem to be amazingly good, right? It's incredibly close to perfect. But let's compare that to a dummy classifier that always just predicts the most likely class, namely the not relevant class. In other words, no matter what the actual instance is, the dummy classifier will always predict that an item is not relevant. So if we have a test set that has 1,000 items, on average, 999 of them will be not relevant anyway. So our dummy classifier will correctly predict the not relevant label for all of those 999 items. And so the accuracy of the dummy classifier is also going to be 99.9%. So in reality, our own classifier's performance isn't impressive at all. It's no better than just always predicting the majority class without even looking at the data. Let's take a look at another example of classification with imbalanced classes on a real data set using our notebook. I'll start here using the digits data set, which has images of handwritten digits labeled with 10 classes, representing the digits 0 through 9. As we can see by loading the data set and then computing the count of instances in each class using NumPy's bin count method, there are roughly the same number of instances in each class, so this data set has balanced classes. However, with this digits data set, now what we're going to do is create a new data set with two imbalanced classes by labeling all digits that are not the digit 1 as the negative class with label 0, and digits that are 1 as the positive class, label 1. So what I've done here is dump the first few entries from the original labels along with the new binary labels so you can see the imbalance visually. Now when we use bin count, we can see that there are about 1,600 negative examples, but only 182 positive examples. So indeed, we have a data set that is class imbalanced, or as expected, almost exactly a 9-to-1 ratio of negative to positive examples. Now let's create a train test partition on this imbalanced set, and then train a support vector machine classifier with these binary labels using the radial basis function as a kernel. We get the accuracy using the score method, and we can see this is just over 90%. Again, at first glance, 90% accuracy for a classifier seems pretty good. However, now let's create a dummy classifier that correctly reflects the class imbalance to see if 90% really is that impressive. scikit-learn makes it easy to create a dummy classifier just by using the dummy classifier class as shown here. Dummy classifiers, again, are called that because they don't even look at the data to make a prediction. They simply use the strategy or rule of thumb that you instruct them to use when creating them. In fact, when you create the classifier, you set the strategy argument to tell it what rule of thumb to use to make its predictions. So here we set this to the most frequent strategy to predict the most frequent class. The dummy classifier here is used just like a regular classifier. So to prepare it for prediction, we call the fit method on the xtrain and ytrain variables that hold the training set instances and labels. Now, this dummy classifier won't actually be looking at the individual data instances in those variables, but it does use the ytrain variable to determine which class in the training data is most frequent. Finally, just like a regular classifier, we can call the predict method to make predictions on the test set. This example shows the output of the dummy classifier's predictions, and as promised, you can see it's always predicting 0, or the negative class, for every instance in the test set. Now we can call the usual score method to get the accuracy of the dummy classifier's constant negative prediction. And we can see it's also about 90%, the same as our earlier support vector machine classifier with radial basis function kernel. So that support vector classifier was actually performing only very slightly better than the dummy classifier. The dummy classifier provides what is called a null accuracy baseline. That is, the accuracy that can be achieved by always picking the most frequent class. You should not use a dummy classifier for real classification problems, but it does provide a useful sanity check and point of comparison. There are other types of dummy classifiers that provide null baselines corresponding to other choices of the strategy parameter, as shown here. Most frequent is the strategy we've just seen that always predicts the most frequent label. The stratified strategy, unlike the constant most frequent prediction, is a random prediction that's based on the class distributions. For example, if the positive class occurs 90% of the time in the training set, then the stratified dummy classifier will output the positive class label with 90% probability. Otherwise, it will output the negative class label. This can help ensure that metrics that rely on having counts of both positive and negative class prediction outcomes can be computed. The uniform strategy is another random prediction method that will generate class predictions uniformly at random. That is, all classes have an equal chance of being output, as opposed to being weighted by their frequency in the training set. This strategy may be useful in gaining an accurate estimate of what are the most common types of prediction errors for each class. Finally, the constant strategy can be useful when computing some metrics like F-score, which we will cover in a few minutes. Well, why is that? Well, when we have a binary classification task where the most frequent class is the negative class, it turns out that using the most frequent strategy will never predict the positive class and will never be able to count the number of positive instances that are correctly predicted. And so the overall count of such positive correct predictions will be 0. So this in turn, as you'll see in a few minutes, will cause some important metrics like F-score to always be 0. So using the constant strategy, we can force a dummy classifier to always predict the positive class, even if it's the minority class in a set of classes. And this will lead to more meaningful computation of F-score. So what does it mean if we discover that our classifier has close to the dummy classifier's performance? Well, typically it means that the features in our model may be ineffective or erroneously computed or missing for some reason. It could also be caused by a poor choice of kernel or hyperparameters in the model. For example, if we change the support vector classifier's kernel parameter to linear from RBF and recompute the accuracy on this retrained classifier, we see that this leads to much better performance of almost 98% compared to the most frequent class baseline of 90%. Finally, if you have accuracy that is close to that of a dummy classifier, it could be because there is indeed a large class imbalance, and the accuracy gains produced by the classifier on the test set simply apply to too few examples to produce a significant gain. In general, for imbalanced classification problems, you should use metrics other than accuracy. We'll look at one shortly called AUC, which is short for area under the curve. Dummy regressors, as you might guess, are the counterpart to dummy classifiers for regression, and they serve a similar role as a null outcome baseline and sanity check for regression models. Since regression models have continuous valued prediction outputs, the strategy parameter for dummy regressors gives you a choice of function that you can apply to the distribution of target values found in the training set. You can ask for the mean or median value of the training set targets, the value corresponding to the quantile that you provide, or a custom constant value. Now let's look more carefully at the different types of outcomes we might see using a binary classifier. This will give us some insight into why using just accuracy doesn't give a complete picture of the classifier's performance and will motivate our definition and exploration of additional evaluation metrics. With a positive and negative class, there are 4 possible outcomes that we can break into 2 cases corresponding to the first and second row of this matrix. If the true label for an instance is negative, the classifier can predict either negative, which is correct and called a true negative, or it can erroneously predict positive, which is an error and called a false positive. If the true label for an instance is positive, the classifier can predict either negative, which is an error and called a false negative, or it can predict positive, which is correct, and that's called a true positive. So maybe a quick way to remember this is that the first word in these matrix cells is false if it's a classifier error, or true if it's a classifier success. The second word is negative if the true label is negative, and positive if the true label is positive. Another name for a false positive that you might know from statistics is a type 1 error, and another name for a false negative is a type 2 error. We're going to use these two-letter combinations, TN, FN, FP, and TP, as variable names when defining some new evaluation metrics shortly. We'll also use capital N here to denote the total number of instances of the sum of all the values in the matrix, the number of data points we're looking at. This matrix of all combinations of predicted label and true label is called the confusion matrix. We can take any classifier prediction on a data instance and associate it with one of these matrix cells depending on the true label of the instance and the classifier's predicted label. This also applies to multi-class classification, in addition to the special case of binary classification I've shown here. In the multi-class case with k classes, we simply have a k by k matrix instead of a 2 by 2 matrix. scikit-learn makes it easy to compute a confusion matrix for your classifier. Let's take a look at the notebook. Here, we import the confusion matrix class from sklearn.metrics. We're going to use the same training set from the digits dataset with the binary imbalance labels that we created earlier. To get the confusion matrix, we simply pass the y-test set of predicted labels and the y-predicted set of predicted labels, and then print the output. The order of the cells of the little matrix output here is the same as the one I just showed on the slide. True negative and false negative are in the first column, and true positive and false positive are in the second column. In particular, the successful predictions of the classifier are on the diagonal, where the true class matches the predicted class. The cells off the diagonal represent errors of different types. Here we compute the confusion matrices for different choices of classifier in the problem, so we can see how they shift slightly with different choices of model. And this gives us some insight into the nature of the successes and failures observed for each type of classifier. So first we'll apply the most frequent class dummy classifier we saw earlier. What we can see here is that the right column that represents cases where the classifier predicted the positive class is all 0, which makes sense for this dummy classifier because it's always predicting the negative class, the most frequent one. We see that 407 instances are true negatives, and there are 43 errors that are false negatives. Here we apply the stratified dummy classifier that gives random output in proportion to the ratio of labels in the training set. Now the right column is no longer all 0 because this dummy classifier does occasionally predict the positive class. If we add the numbers in the right column, we see that 32 plus 6 equals 38 times the number of times the classifier predicted the positive class. Of those times, in 6 cases, the lower right diagonal, this was a true positive. In the next case, we'll apply a support vector classifier with linear kernel and C parameter equal to 1. We note that looking along the diagonal compared to the stratified dummy classifier above, which had a total of 375 plus 6, or 381 correct predictions, the support vector classifier has a total of 402 plus 38, which is 440 correct predictions on the same data set. Likewise, we can apply a logistic regression classifier, and that obtains similar results to the support vector classifier. And finally, we can apply a decision tree classifier and look at the confusion matrix that results from that. One thing we notice is that unlike the support vector or logistic regression classifier, which had balanced numbers of false negatives and false positives, the decision tree makes more than twice as many false negative errors, 17 of them actually, as false positive errors, of which there are 7. Now that we've seen how a confusion matrix can give us a little more information about the types of errors a classifier makes, we're ready to move ahead and define some new types of evaluation metrics that use information from the confusion matrix to give different perspectives on classifier performance. So let's go back to the matrix of possible binary classification outcomes, this time filled out with the actual counts from the notebook's decision tree output. Remember, our original motivation for creating this matrix was to go beyond a single number, accuracy, to get more insight into the different types of prediction successes and failures of a given classifier. Now we have these 4 numbers that we can examine and compare manually. Let's look at this classification result visually to help us connect these 4 numbers to a classifier's performance. What I've done here is plot the data instances by using 2 specific feature values out of the total 64 feature values that make up each instance in the digits dataset. The black points here are the instances with true class positive, namely the digit 1, and the white points have true class negative, that is, they're all the other digits except for 1. The black line shows a hypothetical linear classifier's decision boundary for which any instance to the left of the decision boundary is predicted to be in the positive class, and everything to the right of the decision boundary is predicted to be in the negative class. The true positive points are those black points in the positive prediction region, and false positives are those white points in the positive prediction region. Likewise, true negatives are the white points in the negative prediction region, and false negatives are black points in the negative prediction region. We've already seen one metric that can be derived from the confusion matrix counts, namely accuracy. The successful predictions of the classifier, the ones where the predicted class matches the true class, are along the diagonal of the confusion matrix. So if we add up all the counts along the diagonal, that will give us the total number of correct predictions across all classes. And dividing this sum by the total number of instances gives us accuracy. But let's look at some other evaluation metrics we can compute from these 4 numbers. Well, a very simple related number that's sometimes used is classification error, which is the sum of the counts off the diagonal, namely all of the errors, divided by total instance count. And numerically, this is equivalent to just 1 minus the accuracy. Now for a more interesting example, let's suppose, going back to our medical tumor detecting classifier, that we wanted an evaluation metric that would give higher scores to classifiers that not only achieved a high number of true positives, but also avoided false negatives, that is, that rarely failed to detect a true cancerous tumor. Recall, also known as the true positive rate, sensitivity, or probability of detection, is such an evaluation metric, and it's obtained by dividing the number of true positives by the sum of true positives and false negatives. You can see from this formula that there are 2 ways to get a larger recall number. First, by either increasing the number of true positives, or by reducing the number of false negatives, since this will make the denominator smaller. In this example, there are 26 true positives and 17 false negatives, which gives a recall of 0.6. Now suppose that we have a machine learning task where it's really important to avoid false positives. In other words, we're fine with cases where not all true positive instances are detected, but when the classifier does predict the positive class, we want to be very confident that it's correct. A lot of customer-facing prediction problems are like this. For example, predicting when to show a user a query suggestion in a web search interface might be one such scenario. Users will often remember the failures of a machine learning prediction, even when the majority of predictions are successes. So, precision is an evaluation metric that reflects this situation, and it's obtained by dividing the number of true positives by the sum of true positives and false positives. So to increase precision, we must either increase the number of true positives the classifier predicts, or reduce the number of errors where the classifier incorrectly predicts that a negative instance is in the positive class. Here, the classifier has made 7 false positive errors, and so the precision is 0.79. Another related evaluation metric that will be useful is called the false positive rate, also known as specificity. This gives the fraction of all negative instances that the classifier incorrectly identifies as positive. Here we have 7 false positives, which out of a total of 407 negative instances gives a false positive rate of 0.02. Going back to our classifier visualization, let's look at how precision and recall can be interpreted. The numbers that are in the confusion matrix here are derived from this classification scenario. We can see that a precision of 0.68 means that about 68% of the points in the positive prediction region to the left of the decision boundary, or 13 out of the 19 instances, are correctly labeled as positive. A recall of 0.87 means that of all true positive instances, so all black points in the figure, the positive prediction region has quote-unquote found about 87% of them, or 13 out of 15. If we wanted a classifier that was oriented towards higher levels of precision, like in the search engine query suggestion task, we might want a decision boundary instead that looked like this. Now, all the points in the positive prediction region, 7 out of 7, are true positives, giving us a perfect precision of 1.0. Now, this comes at a cost because out of the 15 total positive instances, 8 of them are now false negatives. In other words, they're incorrectly predicted as being negative. And so recall drops to 7 divided by 15, or 0.47. On the other hand, if our classification task is like the tumor detection example, we want to minimize false negatives and obtain high recall, in which case we would want the classifier's decision boundary to look more like this. Now, all 15 positive instances have been correctly predicted as being in the positive class, which means these tumors have all been detected. However, this also comes with a cost, since the number of false positives, things that the detector triggers as possible tumors, for example, that are actually not, has gone up. So recall is a perfect 1.0 score, but the precision has dropped to 15 out of 42, or 0.36. These examples illustrate a classic trade-off that often appears in machine learning applications, namely that you can often increase the precision of a classifier, but the downside is that you may reduce recall. Or you could increase the recall of a classifier but at the cost of reducing precision. Recall-oriented machine learning tasks include medical and legal applications where the consequences of not correctly identifying a positive example can be high. Often in these scenarios, human experts are deployed to help filter out the false positives that almost inevitably increase with high recall applications. Many customer-facing machine learning tasks, as I just mentioned, are often precision-oriented, since here the consequences of false positives can be high. For example, hurting the customer's experience on a website by providing incorrect or unhelpful information. Examples include search engine ranking and classifying documents to annotate them with topic tags. When evaluating classifiers, it's often convenient to compute a quantity known as an F1 score that combines precision and recall into a single number. Mathematically, this is based on the harmonic mean of precision and recall using this formula. After a little bit of algebra, we can rewrite the F1 score in terms of the quantities that we saw in the confusion matrix: true positives, false negatives, and false positives. This F1 score is a special case of a more general evaluation metric known as an F score that introduces a parameter beta. By adjusting beta, we can control how much emphasis in the evaluation is given to precision versus recall. For example, if we have precision-oriented users, we might set beta equal to 0.5, since we want false positives to hurt performance more than false negatives. For recall-oriented situations, we might set beta to a number larger than 1, say 2, to emphasize that false negatives should hurt performance more than false positives. The setting of beta equals 1 corresponds to the F1 score special case that we just saw that weights precision and recall equally. Let's take a look now at how we can compute these evaluation metrics in Python using scikit-learn. Scikit-learn metrics provides functions for computing accuracy, precision, recall, and F1 score as shown here in the notebook. The input to these functions is the same. The first argument, here yTest, is the array of true labels of the test set data instances. And the second argument is the array of predicted labels for the test set data instances. Here we're using a variable called treePredicted, which are the predicted labels using the decision tree classifier in the previous notebook step. It's often useful when analyzing classifier performance to compute all of these metrics at once. So sklearn metrics provides a handy classification report function. Like the previous score functions, classification report takes the true and predicted labels as the first two required arguments. It also takes some optional arguments that control the format of the output. Here, we use the target names option to label the classes in the output table. You can take a look at the scikit-learn documentation for more information on the other output options. The last column, support, shows the number of instances in the test set that have that true label. Here we show classification reports for 4 different classifiers on the binary digit classification problem. The first set of results is from the dummy classifier, and we can see that as expected, both precision and recall for the positive class are very low, since the dummy classifier is simply guessing randomly, with low probability of predicting the positive class for the positive instances. Many classifiers in scikit-learn can provide information about the uncertainty associated with a particular prediction, either by using the decision function method or the predict_proba method. When given a set of test points, the decision function method provides for each one a classifier score value that indicates how confidently the classifier predicts the positive class. So there will be large magnitude positive scores for those points. Or if it predicts a negative class, there'll be large magnitude negative scores for negative points. Here's an example in the notebook showing the first few instances from our classification problem using a logistic regression classifier. We can see that instances in the negative class often have large magnitude negative scores. And indeed, the instances in the positive class have positive scores from the logistic regression classifier. Likewise, the predict_proba function provides predicted probabilities of class membership. Typically, a classifier would choose the more likely class. That is, in a binary classifier, the class with probability greater than 50%. Adjusting this decision threshold affects the predictions of the classifier. A higher threshold means the classifier has to be more confident in predicting the class. For example, we might predict class 1 only if the estimated probability of class 1 was over 70%, and this results in a more conservative classifier. Here's an example of getting these prediction probabilities for the test instances for the same logistic regression classifier. You can see that many entries with a positive label of 1 have a high probability like 0.995, while many negative label instances have a very low prediction probability. Note that not all models provide useful probability estimates of this type. For example, a model that was overfit to a training set might provide overly optimistic high probabilities that were in fact not accurate. Now we can use these decision scores or prediction probabilities for getting a more complete evaluation picture of a classifier's performance. For a particular application, we might pick a specific decision threshold depending on whether we want the classifier to be more or less conservative about making false positive or false negative errors. It might not be entirely clear when developing a new model what the right decision threshold will be, and how that choice will affect evaluation metrics like precision and recall. So instead, what we'll do is look at how the classifier performs for all possible decision thresholds. This example shows how that works. On the left here is a list of test instances with their true label and classifier score. If we set a decision threshold, then all the instances above that line, so for example, if we set the decision threshold to be minus 20 here, then all the instances above the line are below the threshold of minus 20, so minus 20 or less. And all the instances in this direction are above the threshold of minus 20. And so the ones below the threshold will be predicted to be in the negative class, and the ones above the threshold will be predicted to be in the positive class. So if we pick a specific threshold, so in this case minus 20, and we partition the test points in this way, we can compute precision and recall for the points that are predicted to be in the positive class. So in this case, we have 12 instances here, 12 total instances that are being predicted as positive, and only 4 of them, this one, this one, this one, and this one, are actually positive. And so the precision here is 4 divided by 12, or approximately 0.34. The recall, on the other hand, there are 4 positive labeled instances in the whole set of test examples here, and we found all of them with this particular threshold setting. So the recall here is 4 out of 4. We found all 4 positive labeled examples. And so for this particular threshold of minus 20, we can obtain precision and recall score for that threshold. Let's pick a different threshold. Let's look at what happens when the threshold is negative 10, right here. So again, anything below this line is treated, it has a higher value than minus 10 here, so those would be treated as positive predictions. Things above the line have a score below negative 10, so these would be predicted to be negative. And again, we can compute a precision and recall for this decision threshold setting. And we can see here that there are a total of 6 instances in the positive prediction class, of which 4 are actually of the positive class. And so the precision here is 4 over 6, or about 0.67. And again, the recall here is going to be 4 out of 4, and it's going to be 1.0 again. And so that corresponds to this point in the table over here. And then as we're computing these different precisions and recalls for different thresholds, we can also plot them on this precision recall chart. So the first pair of precision and recall numbers that I got, 0.34 and 1.0, we can plot on this point in precision recall space. The second example, so this was for the threshold of minus 20. When the threshold was minus 10, we got precision of 0.67 and a recall of 1, corresponding to this point that we can plot. And so you can see that if we do this for a number of other thresholds, for example, the threshold of 0, we'll get a precision of 0.75 and a recall of 0.75 that corresponds to this point, and that choice of decision threshold. And we can keep doing that for different thresholds. And we actually are plotting a series of points through the space, which can be connected as a curve. And so in this way, we can get a more complete picture by varying the threshold of how the precision and recall of the resulting classifier output changes as a function of the decision threshold. And this resulting chart here is called a precision recall curve. And we'll look at it in more detail next. Precision recall curves are a very widely used evaluation method for machine learning. As we just saw in the example, the x-axis shows precision and the y-axis shows recall. Now, an ideal classifier would be able to achieve perfect precision of 1.0 and perfect recall of 1.0. So the optimal point would be up here in the top right. And in general, with precision recall curves, the closer, in some sense, the curve is to the top right corner, the more preferable it is, the more beneficial the trade-off it gives between precision and recall. And we saw some examples already of how there is a trade-off between those two quantities, between precision and recall, with many classifiers. This example here is an actual precision recall curve that we generated using the following notebook code. The red circle indicates the precision and recall that's achieved when the decision threshold is 0. So I created this curve using exactly the same method as we saw in the previous example by looking at the decision function output from a support vector classifier, applying varying decision boundary, and looking at how the precision and recall changed as the decision boundary changed. Now, fortunately, scikit-learn has a function that's built in that does all of that, that can compute a precision and recall curve. And that's what we've been using in the notebook here. So you can see that in this particular application, there is a general downward trend. So as the precision of the classifier goes up, the recall tends to go down. In this particular case, you'll see also that it's not exactly a smooth curve. There are these sort of jaggy areas here, and in fact, it gets sort of the jumps tend to get a little bigger as we approach maximum precision. And this is a consequence of how the formulas for precision and recall are computed. They use discrete counts that include the number of true positives. And so as the decision threshold increases, there are fewer and fewer points that remain as positive predictions. So the fractions that are computed for these smaller numbers can change pretty dramatically with small changes in the decision threshold. And that's why these sort of trailing edges of the precision recall curve can appear a bit jagged when you plot them. ROC curves, or receiver operating characteristic curves, are a very widely used visualization method that illustrate the performance of a binary classifier. ROC curves on the x-axis show a classifier's false positive rate, so that would go from 0 to 1.0. And on the y-axis, they show a classifier's true positive rate, so that would also go from 0 to 1.0. The ideal point in ROC space is one where the classifier achieves 0, a false positive rate of 0, and a true positive rate of 1. So that would be the upper left corner. So curves in ROC space represent different trade-offs as the decision boundary, decision threshold is varied for the classifier. So just as in the precision recall case, as we vary a decision threshold, we'll get different numbers of false positives and true positives that we can plot on a chart. So the dotted line here that I'm showing is the classifier curve that results, the ROC curve that results from a classifier that simply randomly guesses the label for a binary class. So it's basically like flipping a coin. So if you have two classes with equal numbers of positive and negative instances, then flipping a coin will get you randomly equal numbers of false positives and true positives for large data sets. So the dotted line here is used as a baseline. So a bad classifier will have performance that is random or maybe even worse than random, or maybe slightly better than random. A reasonably good classifier will give an ROC curve that is consistently better than random across all decision threshold choices. And then an excellent classifier would be one like I've shown here, which is way up and to the left. This particular example is an example of a logistic regression classifier using the notebook example that you've seen. So The shape of the curve can be important as well, the steepness of the curve. We want classifiers that maximize the true positive rate while minimizing the false positive rate. Now, as we'll see next, we can quantify the goodness of a classifier in some sense by looking at how much area there is underneath the curve. So the area underneath the random classifier is going to be 0.5. But then the area, as you can see, the size of the bumpiness of the classifier as it approaches the top left corner, the area underneath the curve will get larger and larger, and it'll approach 1. And so, as we'll see in the next slide, we use something called area under the curve, AUC. That's a single number that measures this total area underneath the ROC curve as a way to summarize a classifier's performance. So an AUC of 0 represents a very bad classifier, and an AUC of 1 will represent an optimal classifier. Now that we've looked at evaluation of binary classifiers, let's take a look at how the more general case of multi-class classification is handled in evaluation. So, in many respects, multi-class evaluation is a straightforward extension of the methods we use in binary evaluation. Instead of 2 classes, we have multiple classes, so the results for a multi-class evaluation amount to a collection of true versus predicted binary outcomes per class. And just as we saw in the binary case, you can generate confusion matrices in the multi-class case. They're especially useful when you have multiple classes because there are many different kinds of errors that result from one true class being predicted as a different class. So we'll look at an example of that. Classification reports that we saw in the binary case are easy to generate for the multi-class case. Now, the one area which is worth a little more examination is how averaging across classes takes place. There are different ways to average multi-class results that we'll cover shortly. The support, the number of instances for each class, is important to consider. So just as we were interested in how to handle imbalanced classes in the binary case, it's important, as we'll see, to consider a similar issue of how the support for classes might vary to a large or small extent across multiple classes. There is a case of multi-label classification in which each instance could have multiple labels. For example, a web page might be labeled with different topics that come from a predefined set of areas of interest. We won't cover multi-label classification in this lecture. Instead, we'll focus exclusively on multi-class evaluation. The multi-class confusion matrix is a straightforward extension of the binary classifier 2x2 confusion matrix. For example, in our digits dataset, there are 10 classes for the digits 0 through 9. So the 10-class confusion matrix is a 10 by 10 matrix with the true digit class indexed by row and the predicted digit class indexed by column. As with the 2x2 case, the correct predictions by the classifier, where the true class matches the predicted class, are all along the diagonal, and misclassifications are off the diagonal. In this example, which was created using the following notebook code, based on a support vector classifier with linear kernel, we can see that most of the predictions are correct, with only a few misclassifications here and there. The most frequent type of mistake here was apparently misclassifying the true digit 8 as a predicted digit 1, which happened 3 times. And indeed, the overall accuracy is high, about 97%, as shown here. As an aside, it's sometimes useful to display a confusion matrix as a heat map in order to highlight the relative frequencies of different types of errors. So I've included the code to generate that here. For comparison, I've also included a second confusion matrix on the same dataset for another support vector classifier that does much worse in a distinctive way. The only change is to use an RBF radial basis function kernel instead of a linear kernel. While we can see from the accuracy number of about 49% below the confusion matrix that the classifier is doing much worse than with the linear kernel, that single number doesn't give much insight into why. Looking at the confusion matrix, however, reveals that for every true digit class, a significant fraction of outcomes are to predict the digit 4. That's rather surprising. For example, of the 44 instances of the true digit 2 in row 2, 17 are classified correctly, but 27 are classified as the digit 4. Clearly something is broken with this model, and I picked this second example just to show an extreme example of what you might see when things go quite wrong. This digits dataset is well established and free of problems, but especially when developing with a new dataset, seeing patterns like this in a confusion matrix could give you valuable clues about possible problems, say in the feature preprocessing, for example. So as a general rule of thumb, as part of model evaluation, I suggest always looking at the confusion matrix for your classifier to get some insight into what kinds of errors it is making for each class, including whether some classes are much more prone to certain kinds of errors than others. Next, just as in the binary case, you can get a classification report that summarizes multiple evaluation metrics for a multi-class classifier, with an average metric computed for each class. Now, what I'm about to describe also applies to the binary class case, but it's easier to see when looking at a multi-class classification problem with several classes. So here's an example of how to compute macro average precision and micro average precision on a sample data set that I've extracted from our fruit data set. In this example, we have 3 columns, where the first column is the true class of an example, the second column is the predicted class from some classifier, and the third column is a binary variable that denotes whether the predicted class matches the true class. And here we have this is a multi-class classification problem, and so we have 3 classes here. We have several instances that are of the orange class, we have 2 instances that are the lemon class, and we have 2 instances that are the apple class. So in this first example, we'll compute macro average precision. And the key aspect of macro average precision is that each class has equal weight. So in this case, each of these classes will contribute 1/3 weight towards the final macro average precision value. So there are 2 steps to compute macro average precision. The first one is to compute the metric. So in this case, we're going to compute precision within each class. So let's take a look at the orange class. There are 5 total examples in the orange class, and only one of them was predicted correctly by the classifier, and so that leads to a precision for the orange class of 1 out of 5, or 0.20. For the second class, the lemon class, there are a total of 2 instances, and only one of them was predicted correctly, and that leads to a precision of 1/2, or 0.50, for the lemon class. That's right, the precision for each of the classes that we have calculated. So this was and for the third class, the apple class, the classifier predicted both of these correctly, so that's a precision of 2 out of 2, or 1.0. So that's the first step. We've computed the precision metric within each class. And then in the second step, we simply average these across these three to produce the final result, to get our final macro average precision. And so we can simply compute the average of 0.2, 0.5, and 1, and we get a final macro average precision for this set of results of 0.57. You'll notice here that no matter how many instances there were in each class, because we computed precision within each class first, each class contributes equally to the overall macro average. So we could have had, for example, 1,000,000 examples from the orange class, but that class would have still been weighted equally because we would have first computed precision for the 1,000,000 orange examples, and then that number would still get a third of the weight compared to the other two classes. So that's macro average precision. Micro average precision is computed a little differently, and it gives each instance in the data results here equal weight. In micro average precision, we don't compute precision for each class separately. We treat the entire data set, the entire set of results here, as an aggregate outcome. So to compute micro average precision, we simply look at how many of all of the examples. We have 9 examples here in total. And micro average precision will simply compute the precision for all the examples regardless of class in this set of results. So out of these 9 instances, we have found that the classifier predicted 4 of them correctly. And so the micro average precision is simply computed as 4 divided by 9, or 0.44. And you'll notice here that if we had 1,000,000 instances of the orange class, for example, that with micro average precision, because each instance has equal weight, that would lead to the orange class contributing many, many more instances to our overall micro average precision. And so the effect of micro average precision is to give classes with a lot more instances much more influence. So the average here would have been influenced much more by the 1,000,000 orange examples than by the 2 lemon and apple examples. And so that is the difference between micro and macro average precision. If the classes have about the same number of instances, macro and micro average will be about the same. If some classes are much larger, have more instances than others, and you want to weight your metric toward the largest ones, use micro averaging. If you want to weight your metric towards the smallest classes, use macro averaging. If the micro average is much lower than the macro average, then examine the larger classes for poor metric performance. If the macro average is much lower than the micro average, then you should examine the smaller classes to see why they have poor metric performance. Here we use the average parameter on the scoring function. In the first example, we use the precision metric and specify whether we want micro average precision, which is the first case, or macro average precision in the second case. In the second example, we use the F1 metric and compute micro and macro averaged F1. Now that we've seen how to compute these metrics, let's take a look at how to use them to do model selection. We saw that for classification, because there were some scenarios like medical diagnostic predictions or customer-facing website features, where the consequences of false positives were very different than false negatives, it made sense to distinguish these types of errors and do a more detailed analysis. In evaluating classifiers, for example, we looked at plots like precision recall curves that could show the trade-offs a classifier could achieve between making errors of those two types. In theory, we could apply the same type of error analysis and more detailed evaluation to regression that we applied for classification. For example, we could analyze the regression model's predictions and categorize errors of one type where the regression model's predicted value was much larger than the target value, compared to a second error type where the predicted value was much smaller than the target value. In practice, though, it turns out that for most applications of regression, distinguishing between these types of different errors is not as important. This simplifies evaluation for regression quite a bit. In most cases, the default R-squared score that's available for regression in scikit-learn and that summarizes how well future instances will be predicted is adequate for most tasks. As a reminder, the R-squared score for a perfect predictor is 1.0, and for a predictor that always outputs the same constant value, the R-squared score is 0. The R-squared score, despite the squared in the name that suggests it's always positive, does have the potential to go negative for bad model fits, such as when fitting nonlinear functions to data. There are a few alternative regression evaluation metrics you should be aware of that work a bit differently than the R-squared score. Mean absolute error takes the mean absolute difference between the target and predicted values. In machine learning terms, this corresponds to the expected value of the L1 norm loss. This is sometimes used, for example, to assess forecast outcomes for regression in time series analysis. Mean squared error takes the mean squared difference between the target and predicted values, and this corresponds to the expected value of the L2 norm loss. This is widely used for many regression problems, and larger errors have correspondingly larger squared contributions to the mean error. Like mean absolute error, mean squared error doesn't distinguish between over and under estimates. Finally, one situation that does arise quite often is the existence of outliers in the data, which can have unwanted influence on the overall R-squared or mean score value. So in those cases, when ignoring outliers is important, you can use the mean absolute error score, which is robust to the presence of outliers because it uses the median of the error distribution rather than the mean. We saw how using dummy classifiers could give us simple but useful baselines to compare against when evaluating a classifier. The same functionality exists for regression. There is a dummy regressor class that provides predictions using simple strategies that do not look at the input data. This example, which is available as the regression example from this lecture's notebook, shows a scatter plot using data based on a single input variable, which is plotted along the x-axis, from the diabetes dataset. The points are the data instances from the test split and form a cloud that looks like it may trend down slightly to the right. The green line, which is also labeled fitted model, is the default linear regression that was fit to the training points. We can see that it's not a particularly strong fit to the test data. The red line, labeled dummy mean, shows a linear model that uses the strategy of always predicting the mean of the training data. So this is an example of a dummy regressor. You can look at the notebook to see that a dummy regressor is created and used just like a regular regression model. You create, fit with the training data, and then call predict on the test data. Although again, like the dummy classifier, you should not use the dummy regressor for actual problems. Its only use is to provide a baseline for comparison. Looking at the regression metrics output from the linear model compared to the dummy model, we can see that, as expected, the dummy regressor achieves an R-squared score of 0, since it always makes a constant prediction without looking at the output. In this instance, the linear model provides only slightly better fit than the dummy regressor according to both mean squared error and the R-squared score. Aside from the strategy of always predicting the mean of the training target values, You can also create some other flavors of dummy regressors that always predict the median of the training target values, or a particular quantile of those values, or a specific custom constant value that you provide. Although regression typically has simpler evaluation needs than classification, it does pay to double check to make sure the evaluation metric you choose for a regression problem does penalize errors in a way that reflects the consequences of those errors for the business, organizational, or user needs of your application. Now that you've seen a number of different evaluation metrics for both binary and multi-class classification, let's take a look at how you can apply them as criteria for selecting the best classifier for your application, otherwise known as model selection. In previous lectures, we've seen a number of different evaluation frameworks for potential model selection. First, we simply did training and testing on the same dataset, which, as we well know, typically overfits badly and doesn't generalize well to new data. As a side note, however, it can serve as a useful sanity check to make sure your software engineering and feature generation pipeline is working correctly. Second, we frequently used a single train test split to produce a single evaluation metric. While fast and easy, this doesn't give as realistic a set of estimates for how well the model may work on future new data, and we don't get a good picture for the variance in the evaluation metrics that may result as we do prediction on different test sets. Third, we used k-fold cross-validation to create k-random train test splits where the evaluation metric was averaged across splits. This leads to models that are more reliable on unseen data. In particular, we can also use grid search using, for example, the grid search CV method within each cross-validation fold to find optimal parameters for a model with respect to the evaluation metric. The default evaluation metric used for a cross-val score or grid search CV is accuracy. So how do you apply the new metrics you've learned about here, like AUC, in model selection? scikit-learn makes this very easy. You simply add a scoring parameter that's set to the string with the name of the evaluation metric you want to use. Let's first look at an example using the scoring parameter for cross-validation, and then we'll take a look at the other primary method of model selection, grid search. In the notebook here, we have a cross-validation example where we're running 5 folds using a support vector classifier with a linear kernel and C parameter set to 1. The first call to cross-val score just uses default accuracy as the evaluation metric. The second call uses the scoring parameter using the string ROC_AUC, and this will use AUC as the evaluation metric. The third call sets the scoring parameter to recall, to use that as the evaluation metric. You can see the resulting list of 5 evaluation values, 1 per fold for each metric. Now here we're not doing any parameter tuning, we're simply evaluating our model's average performance across multiple folds. Now in this grid search example, we use a support vector classifier that uses a radial basis function kernel. And the critical parameter here is the gamma parameter that intuitively sets the radius or width of influence of the kernel. We use grid search CV to find the value of gamma that optimizes a given evaluation metric in 2 cases. In the first case, we just optimize for average accuracy. In the second case, we optimize for AUC. In this particular case, the optimal value of gamma happens to be the same, 0.001, for both evaluation metrics. But as we'll see later, in other cases, the optimal parameter value can be quite different depending on the evaluation metric used to optimize. You can see the complete list of names for the evaluation metrics supported by the scoring parameter by running the following code that uses the scorers variable imported from sklearn metrics. You can see metrics for classification, such as the string precision_micro that represents micro-average precision, as well as metrics for regression, such as the R2 metric for R² regression loss. Let's take a look at a specific example that shows how a classifier's decision boundary changes when it's optimized for different evaluation metrics. This classification problem is based on the same binary digit classifier training and test sets we've been using as an example throughout the notebook. In these classification visualization examples, the positive examples, the digit 1, are shown as black points, and the region of positive class prediction is shown in the light-colored or yellow region to the right of the decision boundary. The negative examples, all other digits, are shown as white points, and the region of negative class prediction here in these figures is to the left of the decision boundary. The data points have been plotted using 2 out of the 64 feature values in the digits dataset, and have been jittered a little, that is, I've added a little bit of random noise so we can see more easily the density of examples in the feature space. Here's the scikit-learn code that produced this figure. We apply grid search here to explore different values of the optional class weight parameter that controls how much weight is given to each of the 2 classes during training. As it turns out, optimizing for different evaluation metrics results in different optimal values of the class weight parameter. As the class weight parameter increases, more emphasis will be given to correctly classifying the positive class instances. The precision-oriented classifier we see here, with class weight of 2, tries hard to reduce false negatives while increasing true positives, so it focuses on the cluster of positive class points in the lower right corner, where there are relatively few negative class points. Here, precision is over 50%. In contrast, the recall-oriented classifier, with class weight of 50, tries hard to reduce the number of false negatives while increasing true positives. That is, it tries to find most of the positive class points as part of its positive class predictions. We can also see that the decision boundary for the F1-oriented classifier has an optimal class weight of 2, which is between the optimal class weight values for the precision and recall-oriented classifiers. Visually, we can see that the F1-oriented classifier also has a kind of intermediate positioning between the precision and recall-oriented decision boundaries. This makes sense, given that F1 is the harmonic mean of precision and recall. The AUC-oriented classifier, with optimal class weight of 5, has a similar decision boundary to the F1-oriented classifier, but shifted slightly in favor of higher recall. We can see the precision-recall trade-off very clearly for this classification scenario in the precision recall curve for the default support vector classifier with linear kernel optimized for accuracy on the same data set, and using the balanced option for the class weight parameter. Let's take a look at the code that generated this plot. Take a moment to imagine how the extreme lower right part of the curve on this precision recall curve represents a decision boundary that's highly precision-oriented in the lower right of the classification plot where there's a cluster of positive examples. As the decision threshold is shifted to become less and less conservative, tracing the curve up and to the left, the classifier becomes more and more like the recall-oriented support vector classifier example. Again, the red circle represents the precision recall trade-off achieved at the 0 score mark, which is the actual decision boundary chosen for the trained classifier. For simplicity, we've often used a single train test split in showing examples of evaluation scoring. However, using only cross-validation or a test set for model selection or parameter tuning may still lead to more subtle forms of overfitting and thus optimistic evaluation estimates for future unseen data. An intuitive explanation for this might be the following. Remember that the whole point of evaluating on a test set is to estimate how well a learning algorithm might perform on future unseen data. The more information we see about our dataset as part of repeated cross-validation passes in choosing our model, the more influence any potential held-out test data has played into selecting the final model, not merely evaluating it. This is sometimes called data leakage, and we'll describe more about that phenomenon in another module. So we haven't done an evaluation with truly held-out test set unless we commit to holding back a test split that isn't seen by any process until the very end of the evaluation. So that's what's actually done in practice. There are 3 data splits: training for model building, validation for model selection, and a test set for the final evaluation. The training and test sets are typically split out first, and then cross-validation is run using the training data to do model and parameter selection. Again, the test set is not seen until the very end of the evaluation process. Machine learning researchers take this protocol very seriously. The train, validate, test design is a very important, universally applied framework for effective evaluation of machine learning models. That brings us to the end of this section of the course on evaluation for machine learning. You should now understand why accuracy only gives a partial picture of a classifier's performance, and be more familiar with the motivation and definition of important alternative evaluation methods and metrics in machine learning, like confusion matrices, precision, recall, F1 score, and area under the ROC curve. You've also seen how to apply and choose these different evaluation metric alternatives in order to optimize model selection or parameter tuning for a classifier to maximize a given evaluation metric. Finally, I'd like to leave you with a couple of points. First, simple accuracy may not often be the right goal for your particular machine learning application. As we saw, for example, with tumor detection or credit card fraud, false positives and false negatives might have very different real-world effects for users or for organization outcomes. So it's important to select an evaluation metric that reflects those user, application, or business needs. Second, there are a number of other dimensions along which it may be important to evaluate your machine learning algorithms that we don't cover here, but that are important for you to be aware of. I'll mention 2 specifically here. Learning curves are used to assess how a machine learning algorithm's evaluation metric changes or improves as the algorithm gets more training data. Learning curves may be useful as part of a cost-benefit analysis. Gathering training data in the form of labeled examples is often time-consuming and expensive, so being able to estimate the likely performance improvement of your classifier, if you say invest in doubling the amount of training data, can be a useful analysis. Second, sensitivity analysis amounts to looking at how an evaluation metric changes as small adjustments are made to important model parameters. This helps assess how robust the model is to choice of parameters. This may be important to perform, especially if there are other costs, such as runtime efficiency, that are critical variables when deploying an operational system that are correlated with different values of parameter, for example, decision tree depth or feature value threshold. In this way, a more complete picture of the trade-offs achievable across different performance dimensions can help you make the best practical deployment decisions for your machine learning model. Another family of supervised learning models that's related to linear classification models is the naive Bayes family of classifiers, which are based on simple probabilistic models of how the data in each class might have been generated. Naive Bayes classifiers are called naive because, informally, they make the simplifying assumption that each feature of an instance is independent of all the others, given the class. In practice, of course, this is not often the case. Features often are somewhat correlated. For example, in predicting whether a house is likely to sell above the owner's asking price, some features, such as the area of the interior rooms, are likely to be correlated with other features, such as the size of the land that the house is built on or the number of bedrooms. And these features, in turn, might be correlated with the location of the property and so on. This naive simplifying assumption means, on the one hand, that learning a naive Bayes classifier is very fast because only simple per-class statistics need to be estimated for each feature and applied for each feature independently. On the other hand, the penalty for this efficiency is that the generalization performance of naive Bayes classifiers can often be a bit worse than other more sophisticated methods, or even linear models for classification. Even so, especially for high-dimensional data sets, naive Bayes classifiers can achieve performance that's often competitive to other more sophisticated methods like support vector machines for some tasks. There are three flavors of naive Bayes classifier that are available in scikit-learn. The Bernoulli naive Bayes model uses a set of binary occurrence features. When classifying text documents, for example, the Bernoulli naive Bayes model is quite handy because we can represent the presence or absence of a given word in the text with a binary feature. Of course, this doesn't take into account how often the word occurs in the text. So the multinomial naive Bayes model uses a set of count-based features, each of which does account for how many times a particular feature, such as a word, is observed in a training example, like a document. In this lecture, we won't have time to cover the Bernoulli or multinomial naive Bayes models. However, those models are particularly well suited to textual data, where each feature corresponds to an observation for a particular word. And so you'll see naive Bayes again, including the Bernoulli and multinomial models, in more depth in the text mining part of this specialization. This lecture will focus on Gaussian naive Bayes classifiers, which assume features that are continuous or real-valued. During training, the Gaussian naive Bayes classifier estimates, for each feature, the mean and the standard deviation of the feature value for each class. For prediction, the classifier compares the features of the example data point to be predicted with the feature statistics for each class, and selects the class that best matches the data point. More specifically, the Gaussian naive Bayes classifier assumes that the data for each class was generated by a simple class-specific Gaussian distribution. Predicting the class of a new data point corresponds mathematically to estimating the probability that each class's Gaussian distribution was most likely to have generated the data point. The classifier then picks the class that has highest probability. Without going into the mathematics involved, it can be shown that the decision boundary between classes in the two-class Gaussian naive Bayes classifier in general is a parabolic curve between the classes. And in the special case, where the variance of each feature is the same for both classes, the decision boundary will be linear. Here's what that looks like typically on a simple binary classification dataset. The gray ellipses give an idea of the shape of the Gaussian distribution for each class, as if we were looking down from above. You can see the centers of the Gaussians correspond to the mean value of each feature for each class. More specifically, the gray ellipses show the contour line of the Gaussian distribution for each class that corresponds to about 2 standard deviations from the mean. The line between the yellow and gray background areas represents the decision boundary, and we can see that this is indeed parabolic. To use the Gaussian naive Bayes classifier in Python, we just instantiate an instance of the Gaussian NB class and call the fit method on the training data, just as we would with any other classifier. It's worth noting that the naive Bayes models are among a few classifiers in scikit-learn that support a method called partial fit, which can be used instead of fit to train the classifier incrementally in case you're working with a huge data set that doesn't fit into memory. More details on that are available in the scikit-learn documentation for naive Bayes. For the Gaussian NB class, there are no special parameters to control the model's complexity. Looking at one example in the notebook from our synthetic 2-class dataset, we can see that in fact the Gaussian naive Bayes classifier achieves quite good performance on this simple classification example. When the classes are no longer as easily separable as with this second, more difficult binary example here, like linear models, naive Bayes does not perform as well. On a real-world example using the breast cancer dataset, the Gaussian naive Bayes classifier also does quite well, being quite competitive with other methods such as support vector classifiers. Typically, Gaussian naive Bayes is used for high-dimensional data, when each data instance has hundreds, thousands, or maybe even more features. And likewise, the Bernoulli and multinomial flavors of naive Bayes are used for text classification, where there are a very large number of distinct words as features and where the feature vectors are sparse, because any given document uses only a small fraction of the overall vocabulary. There's more in-depth material on the Bernoulli and multinomial naive Bayes classifiers in the text mining portion of this specialization. It can be shown that naive Bayes classifiers are related mathematically to linear models, and so many of the pros and cons of linear models also apply to naive Bayes. On the positive side, naive Bayes classifiers are fast to train and use for prediction, and thus are well suited to high-dimensional data, including text, and to applications involving very large data sets where efficiency is critical and computational costs rule out other classification approaches. On the negative side, when the conditional independent assumption about features doesn't hold, in other words, for a given class there's significant covariance among features, as is the case with many real-world data sets, other more sophisticated classification methods that can account for these dependencies are likely to outperform naive Bayes. And on a side note, when getting confidence or probability estimates associated with predictions, naive Bayes classifiers produce unreliable estimates typically. Still, naive Bayes classifiers can perform very competitively on some tasks and are also often very useful as baseline models against which more sophisticated models can be compared. A widely used and effective method in machine learning involves creating learning models known as ensembles. An ensemble takes multiple individual learning models and combines them to produce an aggregate model that is more powerful than any of its individual learning models alone. Why are ensembles effective? Well, one reason is that if we have different learning models, although each of them might perform well individually, they'll tend to make different kinds of mistakes on a dataset. And typically this happens because each individual model might overfit to a different part of the data. By combining different individual models into an ensemble, we can average out their individual mistakes to reduce the risk of overfitting, while maintaining strong prediction performance. Random forests are an example of the ensemble idea applied to decision trees. Random forests are widely used in practice and achieve very good results on a wide variety of problems. They can be used as classifiers via the scikit-learn random forest classifier class, or for regression using the random forest regressor class, both in the sklearn ensemble module. As we saw earlier, one disadvantage of using a single decision tree was that decision trees tend to be prone to overfitting the training data. As its name would suggest, a random forest creates lots of individual decision trees on a training set, often on the order of tens or hundreds of trees. The idea is that each of the individual trees in a random forest should do reasonably well at predicting the target values in the training set, but should also be constructed to be different in some way from the other trees in the forest. Again, as the name would suggest, this difference is accomplished by introducing random variation into the process of building each decision tree. This random variation during tree building happens in two ways. First, the data used to build each tree is selected randomly. And second, the features chosen in each split test are also randomly selected. To create a random forest model, you first decide on how many trees to build. This is set using the n-estimator parameter for both random forest classifier and random forest regressor. Each tree will be built from a different random sample of the data, called a bootstrap sample. Bootstrap samples are commonly used in statistics and machine learning. If your training set has n instances or samples in total, a bootstrap sample of size n is created by just repeatedly picking one of the n dataset rows at random with replacement. That is, allowing for the possibility of picking the same row again at each selection. You repeat this random selection process n times. The resulting bootstrap sample has n rows, just like the original training set, but with possibly some rows from the original dataset missing and others occurring multiple times, just due to the nature of the random selection with replacement. When building a decision tree for a random forest, the process is almost the same as for a standard decision tree, but with one important difference. When picking the best split for a node, instead of finding the best split across all possible features, a random subset of features is chosen, and the best split is found within that smaller subset of features. The number of features in this subset that are randomly considered at each stage is controlled by the max features parameter. This randomness in selecting the bootstrap sample to train an individual tree in a forest ensemble, combined with the fact that splitting a node in the tree is restricted to random subsets of the features at each split, virtually guarantees that all of the decision trees in the random forest will be different. The random forest model is quite sensitive to the max features parameter. If max features is set to 1, the random forest is limited to performing a split on the single feature that was selected randomly, instead of being able to take the best split over several variables. This means the trees in the forest will likely be very different from each other, and possibly with many levels, in order to produce a good fit to the data. On the other hand, if max features is high, close to the total number of features that each instance has, the trees in the forest will tend to be similar and probably will require fewer levels to fit the data, using the most informative features. Once a random forest model is trained, it predicts the target value for new instances by first making a prediction for every tree in the random forest. For regression tasks, the overall prediction is then typically the mean of the individual tree predictions. For classification, the overall prediction is based on a weighted vote. Each tree gives a probability for each possible target class label. Then the probabilities for each class are averaged across all the trees, and the class with the highest probability is the final predicted class. Here's an example of learning a random forest on the example fruit data set using two features, height and width. Here we're showing the training data plotted in terms of two feature values, with height on the x-axis and width on the y-axis. As usual, there are 4 categories of fruit to be predicted. Because the number of features is restricted to just 2 in this very simple example, the randomness in creating the tree ensemble is coming mostly from the bootstrap sampling of the training data. You can see that the decision boundaries overall have the box-like shape that we associate with decision trees, but with some additional detailed variation to accommodate specific local changes in the training data. Overall, you can get an impression of the increased complexity of this random forest model in capturing both the global and local patterns in the training data compared to the single decision tree model we saw earlier. Let's take a look at the notebook code that created and visualized this random forest on the fruit data set. This code also plots the decision boundaries for the other 5 possible feature pairs. Again, to use the random forest classifier, we import the random forest classifier class from the sklearn ensemble library. After doing the usual train test split and setting up the pie-plot figure for plotting, we iterate through pairs of feature columns in the dataset. For each pair of features, we call the fit method on that subset of the training data x using the labels y. We then use the utility function plot class regions for classifier that's available in the shared module for this course to visualize the training data and the random forest decision boundaries. Let's apply random forests to a larger data set with more features. For comparison with other supervised learning methods, we'll use the breast cancer data set again. We create a new random forest classifier, and since there are about 30 features, we'll set max features to 8 to give a diverse set of trees that also fit the data reasonably well. We can see that random forests with no feature scaling or extensive parameter tuning achieve very good test set performance on this data set. In fact, it's as good or better than all the other supervised methods we've seen so far, including kernelized support vector machines and neural networks that require more careful tuning. Notice that we did not have to perform scaling or other preprocessing as we did with a number of other supervised learning methods. This is one advantage of using random forests. Also note that we passed in a fixed value for the random state parameter in order to make the results reproducible. If we didn't set the random state parameter, the model would likely be different each time due to the randomized nature of the random forest algorithm. So on the positive side, random forests are widely used because they're very powerful. They give excellent prediction performance on a wide variety of problems, and they don't require careful scaling of the feature data or extensive parameter tuning. And even though building many different trees requires a corresponding increase in computation, building random forests is easily parallelized across multiple CPUs. On the negative side, while random forests do inherit many of the benefits of decision trees, one big difference is that random forest models can be very difficult for people to interpret, making it difficult to see the predictive structure of the features or to know why a particular prediction was made. In addition, random forests are not a good choice for tasks that have very high-dimensional sparse features, like text classification, where linear models can provide efficient training and fast, accurate prediction. So to recap, here are some of the key parameters that you'll need for using random forests. N estimators sets the number of trees to use. The default value for N estimators is 10, and increasing this number for larger data sets is almost certainly a good idea, since ensembles that can average over more trees will reduce overfitting. Just bear in mind that increasing the number of trees in the model will also increase the computational cost of training. You use more time and more memory. So in practice, you'll want to choose the parameters that make best use of the resources available on your system. As we saw earlier, the max features parameter has a strong effect on performance. It has a large influence on how diverse the random trees in the forest are. Typically, the default setting of max features, which for classification is the square root of the total number of features, and for regression is the log base 2 of the total number of features, works quite well in practice, although explicitly adjusting max features may give you some additional performance gain, with smaller values of max features tending to reduce overfitting. The max depth parameter controls the depth of each tree in the ensemble. The default setting for this is none. In other words, the nodes in a tree will continue to be split until all leaves contain the same class or have fewer samples than the minimum sample split parameter value, which is 2 by default. Most systems now have a multi-core processor, and so you can use the njobs parameter to tell the random forest algorithm how many cores to use in parallel to train the model. Generally, you can expect something close to a linear speedup. So, for example, if you have 4 cores, the training will be 4 times as fast as if you just use 1. If you set njobs to -1, it will use all the cores on your system. And setting njobs to a number that's more than the number of cores on your system won't have any additional effect. Finally, given the random nature of random forests, if you want reproducible results, it's especially important to choose a fixed setting for the random state parameter. In the examples we've shown here, we typically set random state to 0, but any fixed number will work just as well. Another tree-based ensemble method that's gained wide use in real-world applications is gradient-boosted decision trees. Like random forests, gradient-boosted trees use an ensemble of multiple trees to create more powerful prediction models for classification and regression. In this lecture, we'll provide a brief overview of gradient-boosted decision trees, along with a discussion of their key parameters that control model complexity. Unlike the random forest method that builds and combines a forest of randomly different trees in parallel, the key idea of gradient-boosted decision trees is that they build a series of trees where each tree is trained so that it attempts to correct the mistakes of the previous tree in the series. Typically, gradient-boosted tree ensembles use lots of shallow trees, known in machine learning as weak learners, built in a non-random way, to create a model that makes fewer and fewer mistakes as more trees are added. Once the model is built, making predictions with gradient-boosted tree models is fast and doesn't use a lot of memory. Like random forests, the number of estimators in a gradient-boosted tree ensemble is an important parameter in controlling model complexity. A new parameter that does not occur with random forest is something called the learning rate. The learning rate controls how the gradient-boosted tree algorithm builds the series of corrective trees. When the learning rate is high, each successive tree puts strong emphasis on correcting the mistakes of its predecessor, and thus may result in a more complex individual tree, and thus overall a more complex model. With smaller settings of the learning rate, there's less emphasis on thoroughly correcting the errors of the previous step, which tends to lead to simpler trees at each step. Here's an example showing how to use gradient-boosted trees in scikit-learn on our sample fruit classification task, plotting the decision regions that result. The code is more or less the same as what we use for random forests, but from the sklearn ensemble module, we import the gradient boosting classifier class. We then create the gradient boosting classifier object and fit it to the training data in the usual way. By default, the learning rate parameter is set to 0.1, the n estimators parameter giving the number of trees to use is set to 100, and the max depth is set to 3. As with random forests, you can see the decision boundaries have that box-like shape that's characteristic of decision trees or ensembles of trees. Now let's apply gradient-boosted decision trees to the breast cancer dataset. This code trains two different gradient-boosted classifiers. The first one uses the default settings. We can see that the first result has perfect accuracy on the training set, which indicates the model is likely overfitting. Two ways to learn a less complex gradient-boosted tree model are to reduce the learning rate so that each tree doesn't try as hard to learn a more complex model that fixes the mistakes of its predecessor, and to reduce the max depth parameter for the individual trees in the ensemble. The second classifier example makes these changes in the parameters, and you can see that the training set accuracy does decrease while the test set accuracy increases slightly. Gradient-boosted decision trees are among the best off-the-shelf supervised learning methods available, achieving excellent accuracy with only modest memory and runtime requirements to perform prediction once the model has been trained. Some major commercial applications of machine learning have been based on gradient-boosted decision trees. Like other decision tree-based learning methods, you don't need to apply feature scaling for the algorithm to do well, and the features can be a mix of binary, categorical, and continuous types. Boosted decision trees do have several downsides. So like random forests, ensembles of trees are very difficult for people to interpret compared to individual decision trees. However, this often may not matter for many applications where prediction accuracy is the most important goal. Gradient-boosted methods can require careful tuning of the learning rate and other parameters, and the training process can require a lot of computation. And like the other tree-based learning methods we saw, using gradient-boosted methods for text classification or other scenarios where the feature space has thousands of features with sparse values is usually not a good choice for accuracy and computational cost reasons. The key parameters controlling model complexity for gradient-boosted tree models are n estimators, which sets the number of small decision trees, the weak learners, to use in the ensemble, and the learning rate. Typically, these two parameters are tuned together, since making the learning rate smaller will require more trees to maintain model complexity. Unlike random forests, increasing n estimators can lead to overfitting. So typically, the n estimator setting is chosen to best exploit the speed and memory capabilities of the system during the training, and other parameters like the learning rate are then adjusted given that fixed n estimator setting. The max depth parameter can also have an effect on model complexity by controlling the depth and hence the complexity of the individual trees. The gradient boosting method assumes that each tree is a weak learner, and so the max depth parameter is usually quite small, on the order of 3 to 5 for most applications. In this part of the course, you'll get an introduction to the basics of neural networks, which are a broad family of algorithms that have formed the basis for the recent resurgence in the computational field called deep learning. Early work on neural networks actually began in the 1950s and 60s, and just recently has experienced a resurgence of interest as deep learning has achieved impressive state-of-the-art results on specific tasks that range from object classification in images to fast, accurate machine translation to game playing. The topic of neural networks requires its own course, and indeed, if you're interested in more depth, you can check out the excellent course on Coursera called Neural Networks for Machine Learning by a pioneer in this area, Professor Jeff Hinton. Here, we'll provide an introduction to the basic concepts and algorithms that are foundation of neural networks and of the much more sophisticated deep learning methods in use today. You'll learn about some basic models called multi-layer perceptrons, supported by scikit-learn, that can be used for classification and regression. Let's start by briefly reviewing simpler methods we've already seen for regression and classification: linear regression and logistic regression, which we show graphically here. Linear regression predicts a continuous output, y hat, shown as the box on the right, as a function of the sum of the input variables xi, shown in the boxes on the left, each weighted by a corresponding coefficient wi hat, plus an intercept or bias term b hat. We saw how various methods like ordinary least squares, ridge regression, or lasso regression could be used to estimate these model coefficients wi hat and b hat, shown above the arrows in the diagram, from training data. Logistic regression takes this one step further by running the output of the linear function of the input variables xi through an additional nonlinear function, the logistic function, represented by the new box in the middle of the diagram, to produce the output y, which because of the logistic function is now constrained to lie between 0 and 1. We use logistic regression for binary classification since we can interpret y as the probability that a given input data instance belongs to the positive class in a two-class binary classification scenario. Here's an example of a simple neural network for regression called a multi-layer perceptron, which I'll sometimes abbreviate by MLP. These are also known as feed-forward neural networks. MLPs take this idea of computing weighted sums of the input features like we saw in logistic regression, but it takes it a step beyond logistic regression by adding an additional processing step called a hidden layer, represented by this additional set of boxes, H0, H1, and H2 in the diagram. These boxes within the hidden layer are called hidden units, and each hidden unit in the hidden layer computes a nonlinear function of the weighted sums of the input features, resulting in intermediate output values v0, v1, v2. Then the MLP computes a weighted sum of these hidden unit outputs to form the final output value y hat. This nonlinear function that the hidden unit applies is called the activation function. In this example, the activation function is the hyperbolic tangent function, which is related to the logistic function. You can see that the result of adding this additional hidden layer processing step to the prediction model is a formula for y hat that is already more involved than the one for logistic regression. Now predicting y involves computing a different initial weighted sum of the input feature values for each hidden unit, which applies a nonlinear activation function, and then all of these nonlinear outputs are combined using another weighted sum to produce y. In particular, there's one weight between each input and each hidden unit, and one weight between each hidden unit and the output variable. In fact, this addition and combination of nonlinear activation functions allows multi-layer perceptrons to learn more complex functions than is possible with a simple linear or logistic function. This additional expressive power enables neural networks to perform more accurate prediction when the relationship between the input and output is itself complex. Of course, this complexity also means that there are a lot more weights, model coefficients, to estimate in the training phase, which means that both more training data and more computation are typically needed to learn a neural network compared to a linear model. As an aside, there are a number of choices for the activation function in a neural network that gets applied in hidden units. Here, the plot shows the input value coming into the activation function from the previous layer's inputs on the x-axis, and the y-axis shows the resulting output value from the function. This code to plot this example is available in the accompanying notebook. The three main activation functions we'll compare later in this lecture are the hyperbolic tangent, that's the S-shaped function in green, the rectified linear unit function, which I'll abbreviate to ReLU, shown as the piecewise linear function in blue, and the familiar logistic function, which is shown in red. The ReLU activation function is the default activation function for neural networks in scikit-learn. It maps any negative input values to 0. The hyperbolic tangent function, or tanh function, maps large positive input values to outputs very close to 1, and large negative input values to outputs very close to -1. These differences in the activation function can have some effect on the shape of regression prediction plots or classification decision boundaries that neural networks learn. In general, we'll be using either the hyperbolic tangent or the ReLU function as our default activation function, since these perform well for most applications. Let's take a look at how we use neural networks in scikit-learn for classification, using the more complex synthetic binary classification dataset. To use a neural network classifier, you import the MLP classifier class from the sklearn neural network module. This code example shows the classifier being fit to the training data using a single hidden layer with 3 different numbers of hidden units in the layer: 1 unit, 10 units, and 100 units. As with all other classification types we've seen, you can create the classifier object with the appropriate parameters and call the fit method on the training data. Here, the main parameter for a neural network classifier is this parameter, hidden layer sizes. This parameter is a list with one element for each hidden layer that gives the number of hidden units to use for that layer. So here we're passing a list with a single element, meaning we want one hidden layer, using the number in the variable called units. By default, if you don't specify the hidden layer sizes parameter, scikit-learn will create a single hidden layer with 100 hidden units. While a setting of 10 may work well for simple datasets like the one we use as examples here, for really complex datasets, the number of hidden units could be in the thousands. It's also possible, as we'll see shortly, to create an MLP with more than one hidden layer by passing a hidden layer sizes parameter with multiple entries. I want to also note the use of this extra parameter called solver, which specifies the algorithm to use for learning the weights of the network. Here we're using the LBFGS algorithm. We'll discuss the solver parameter setting further at the end of this lecture. Also note that we're passing in a random state parameter when creating the MLP classifier object, like we did for the train test split function, and we happen to set this random state parameter to a fixed value of 0. This is because for neural networks, their weights are initialized randomly, which can affect the model that is learned. Because of this, even without changing the key parameters on the same dataset, the same neural network algorithm might learn 2 different models, depending on the value of the internal random seed that is chosen. So by always setting the same value for the random seed used to initialize the weights, we can ensure the results will always be the same for everyone using these examples. This graphic plots the results of running this code to show how the number of hidden units in a single layer neural network affects the model complexity for classification. With a single hidden unit, the model is mathematically equivalent to logistic regression. We see the classifier returns the familiar simple linear decision boundary between the 2 classes. The training set score is low and the test score is not much better, so this network model is underfitting. With 10 hidden units, we can see that the MLP classifier is able to learn a more complex decision boundary that captures more of the nonlinear, cluster-oriented structure in the data, though the test set accuracy is still low. With 100 hidden units, the decision boundary is even more detailed and achieves much better accuracy on both the training and the test sets. Here's a graphical depiction of a multi-layer perceptron with 2 hidden layers. Adding the second hidden layer further increases the complexity of functions that the neural network can learn from more complex datasets. Taking this complexity further, large architectures of neural networks with many stages of computation are why deep learning methods are called deep, and we'll summarize deep learning in an upcoming lecture for this week. Here's an example in the notebook showing how we create a two-layer MLP with 10 hidden units in each layer. We just set the hidden layer sizes parameter when creating the MLP classifier to a 2-element list, indicating 10 units in each of the 2 hidden layers. You can see the result of adding the second hidden layer on the classification problem we saw earlier. On the left is the original MLP with one hidden layer of 10 units, and on the right is the same dataset using a new MLP with 2 hidden layers of 10 units each. You can see the MLP with 2 hidden layers learned a more complex decision boundary and achieved in this case a much better fit on the training data and slightly better accuracy on the test data. Once we start adding more hidden layers with lots of hidden units, you can see that the number of weights, or model coefficients, to estimate for a neural network can increase rapidly, so that more complex neural networks could have many thousands of weights to estimate. We can control this model complexity just as we did with ridge and lasso regression by adding an L2 regularization penalty on the weights. Remember that L2 regularization penalizes models that have a large sum of squares of all the weight values, with the effect being that the neural network prefers models with more weights shrunk close to 0. The regularization parameter for MLPs is called alpha, like with the linear regression models. And in scikit-learn is set to a small value by default, like 0.0001, that gives a little bit of regularization. This code example shows the effect of changing alpha for a larger MLP with 2 hidden layers of 100 nodes each, from a small value of 0.01 to a larger value of 5.0. For variety here, we're also setting the activation function to use the hyperbolic tangent function. Here's the graphical output of this notebook code. You can see the effect of increasing regularization with increasing alpha. In the left plot, when alpha is small, the decision boundaries are much more complex and variable, and the classifier is overfitting, as we can see from the very high training set score and low test score. On the other hand, the right plot uses the largest value of alpha here, alpha 5.0, and that setting results in much smoother decision boundaries, while still capturing the global structure of the data. And this increased simplicity allows it to generalize much better and not overfit to the training set. And this is evident from the much higher test score in this case. As with other supervised learning models like regularized regression and support vector machines, it can be critical when using neural networks to properly normalize the input features. Let's apply the multi-layer perceptron to the breast cancer dataset. And notice that we first apply the min-max scaler to pre-process the input features. Here, we'll combine a more complex network using 2 hidden layers with 100 hidden units each, with a higher regularization setting of alpha at 5.0, and using the LBFGS solver again. You can see that with this multi-layer perceptron, both the training and test set accuracy are among the highest we've obtained on this dataset. Like many of the other supervised learning methods we've seen, you can also use multi-layer perceptrons for regression, as well as classification. We're including MLP regression here as an example for 2 reasons. First, because MLP regression may be useful for some regression problems on its own, but more generally because some deep learning problems are regression problems, and so, as with classification, using multi-layer perceptrons is a good starting point to learn about the more complex architectures used for regression in deep learning. Here's an example of a simple MLP regression model in our notebook. You use the multi-layer perceptron regressor by importing the MLP regressor class from the sklearn neural network module, and then creating the MLP regressor object. When creating the object here, we're setting the number of hidden layers and units within each hidden layer using the same hidden layer sizes parameter that we used for classification. This example uses 2 hidden layers with 100 hidden nodes each. This notebook code has a loop that cycles through different settings of the activation function parameter and the alpha parameter for L2 regularization. Here we've included regression results that use, in the top row, the hyperbolic tangent activation function, and in the bottom row, the ReLU activation function. You can see the smoothness of the activation function somewhat influences the smoothness of the corresponding regression results. Along the columns, the plots also show the effect of using different alpha settings to increase the amount of L2 regularization from left to right. Again, as with classification, the effect of increasing the amount of L2 regularization by increasing alpha is to constrain the regression to use simpler and simpler models with fewer and fewer large weights. You can see this effect for both activation functions in the top and bottom rows. The regression line on the left has higher variance than the much smoother regularized model on the right. On the positive side, beyond the simple examples we've shown here, neural networks form the basis of advanced learning architectures that capture complex features and give state-of-the-art performance on an increasingly wide variety of difficult learning tasks, from world championship play for the game of Go to detailed and robust recognition of objects in images. However, with this increased power come increased costs. These larger and more complex models typically require significant volumes of data, computation, and training time to learn. In addition, careful preprocessing of the input data is needed to help ensure fast, stable, meaningful solutions to finding the optimal set of weights. In general, neural networks are a good choice when the features are of similar types, for example, all derived from the pixels of an image, and less of a good choice when the features are of very different types. Finally, let's review the key parameters for the multilayer perceptron in scikit-learn that can be used to control model complexity. The main way to control model complexity for the MLP is to control the hidden unit size and structure, using the hidden layer sizes parameter that controls the number of hidden layers and the number of units within each layer. Alpha controls the amount of regularization that helps constrain the complexity of the model by constraining the magnitude of the model weights. Finally, you can experiment with at least 3 different choices for the nonlinear activation function by using the activation parameter. Earlier, we saw the solver parameter for specifying the algorithm that learns the network weights. The solver is the algorithm that actually does the numerical work of finding the optimal weights. And one intuitive way of visualizing this process is that all of the solver algorithms have to do a kind of hill climbing in a very bumpy landscape with lots of local minima, where each local minimum corresponds to a locally optimal set of weights. That is, a choice of weight settings that's better than any nearby choices of weights. So across this whole landscape of very bumpy local minima, some will have higher validation scores on the test data and some will have lower. So depending on the initial random initialization of the weights and the nature of the trajectory in the search path that a solver takes through this bumpy landscape, the solver can end up at different local minima, which can have different validation scores. The default solver, Atom, tends to be both efficient and effective on large data sets with thousands of training examples. For small data sets, like many of the ones we used in these examples, the LBFGS solver tends to be faster and find more effective weights. You can find further details on these more advanced settings in the documentation for scikit-learn. As we discussed in the first week of the course, one of the key challenges in machine learning is finding the right features to use as input to a learning model for a particular problem. This is called feature engineering and can be part art and part science. It can also be the single most important factor in doing well on a learning task. Sometimes, in fact, more often, more important than the choice of the model itself. We'll discuss this further in the last week of the course. Because of the difficulty of feature engineering, there's been a lot of research on what's called feature learning or feature extraction algorithms that can find good features automatically. This brings us to deep learning. At a high level, one of the advantages of deep learning is that it includes a sophisticated automatic feature learning phase as part of its supervised training. Moreover, deep learning is called deep because this feature extraction typically doesn't use just one feature learning step, but a hierarchy of multiple feature learning layers, each feeding into the next. Here's one simplified example of what a deep learning architecture might look like in practice for an image recognition task, in this case, digit recognition, recognizing a handwritten digit from 0 to 9, for example. You can see the automatic feature extraction step made up of a hierarchy of feature layers, each of which is based on a network that does convolution, which can be thought of as a filter for a specific pattern, followed by a subsampling step, also known as pooling, that can detect a translated or rotated version of that feature anywhere in the image, so that features are detected properly for the final classification step, which is implemented as a fully connected network. The subsampling step also has the effect of reducing the computational complexity of the network. Depending on the properties of the object we want to predict, for example, if we care only about the presence of an object in an image compared to its, say, specific location, the subsampling part of the architecture may or may not be included. And this is only one example of a deep learning architecture. The size, structure, and other properties may look very different depending on the specific learning problem. This image from a paper by Honglak Lee and colleagues at the University of Michigan shows an illustration of multi-layer feature learning for face recognition. Here there are 3 groups from left to right, corresponding to first, second, and third stages of feature learning. The matrix at each stage shows a set of image features, with 1 feature per square. Each feature can be thought of as a detector or filter that lights up when that pattern is present in the underlying image. The first layer of their deep learning architecture extracts the most primitive low-level features such as edges and different kinds of blobs. The second layer creates new features from combinations of those first layer features. For faces, this might correspond to key elements that capture shapes of higher level features like noses or eyes. The third layer in turn creates new features from combinations of the second layer features, forming still higher level features that capture typical face types and facial expressions. Finally, all of these features are used as input to the final supervised learning step, namely the face classifier. Here are the feature layers that result from training on different types of objects: cars, elephants, chairs, and a mixture of objects. These kinds of complex features can't be learned from a small number of layers. Advances in both algorithms and computing power allow current deep learning systems to train architectures that can have dozens of layers of nonlinear hierarchical features. It turns out that the human brain does something quite related to this when processing visual information. There are specific neural circuits that first do low-level feature extraction, such as edge detection and finding the frequency of repeated patterns, which are then used to compute more sophisticated features to help estimate things like simple shapes and their orientation, or whether a shape is in the foreground or background, followed by further layers of higher-level visual processing that support more complex tasks such as face recognition and interpreting the motion of multiple moving objects. On the positive side, deep learning systems have achieved impressive gains and have achieved state-of-the-art performance on many difficult tasks. Deep learning's automatic feature extraction mechanisms also reduce the need for human guesswork in finding good features. Finally, with current software, deep learning architectures are quite flexible and can be adapted for different tasks and domains. On the negative side, however, deep learning can require very large training sets and computing power, and that can limit its practicality in some scenarios. The complexity of implementation could be considered as one of the negatives of deep learning, and this is the reason that a number of sophisticated high-level software packages have been developed to assist in the development of deep learning architectures. Also, despite the faces example we saw earlier, which gave clear, easy-to-interpret features in most cases, often the features and weights of typical deep learning systems are not nearly so easy to interpret. That is, it's not clear why or what features led a deep learning system to make a particular prediction. While scikit-learn with the MLP classifier and MLP regressor classes provides a useful environment to learn about and apply simple neural networks, if you're interested in getting a deep understanding of deep learning and the software tools required to use it, we've provided some links to additional resources. In particular, software packages usable with Python include Keras and Lasagna, which in turn use libraries that include TensorFlow and Theano. Deep learning typically requires not only significant volumes of data for training, but also significant computation. It turns out that the processors inside video cards, called GPUs, or high-performance graphical processing units, are well suited to large-scale, highly parallelized high-performance computing because they can do key underlying operations like matrix multiplication very quickly. This is because they're designed to process large volumes of data from memory, as you might do for streaming video, for example, and they have many high-speed registers that can operate in parallel on this data. Unlike scikit-learn, which cannot currently exploit GPUs, these deep learning libraries can make full use of GPU clusters for large-scale learning of deep learning architectures. In data science, the term data leakage, sometimes just referred to as leakage, describes the situation where the data you're using to train a machine learning algorithm happens to include unexpected extra information about the very thing you're trying to predict. Basically, leakage occurs any time that information is introduced about the target label or value during training that would not legitimately be available during actual use. Maybe the simplest example of data leakage would be if we included the true label of a data instance as a feature in the model. The model would learn the equivalent of, if this object is labeled as an apple, predict it's an apple. Another clear example of data leakage that we've seen before is having test data accidentally included in the training data, which leads to overfitting. However, data leakage can happen for many other reasons too, often in ways that are quite subtle and hard to detect. When data leakage does occur, it typically causes results during your model development phase that are too optimistic, followed by the nasty surprise of disappointing results after the prediction model is actually deployed and evaluated on new data. In other words, leakage can cause your system to learn a suboptimal model that does much worse in actual deployment than a model developed in a leak-free setting. So leakage can have dramatic implications in the real world, ranging from the financial cost of making a bad monetary and engineering investment in something that doesn't actually work, to system failures that hurt customers' perception of your system's quality or impact the company's brand. For these reasons, data leakage is one of the most serious and widespread problems in data mining and machine learning, and something that as a machine learning practitioner, you must always be on guard against. So now we'll cover what data leakage is, why it matters, how it can be detected, and how you might avoid it in your applications. As an aside, this term data leakage is also used in the field of data security to mean the unauthorized transfer of information outside of a secure facility like a data center. However, in some ways, this security-based meaning is actually somewhat appropriate for our machine learning setting, given the importance of keeping the information about the prediction securely separated from the training and model development phase. Let's look at some more subtle examples of data leakage problems. One classic case happens when information about the future that would not legitimately be available in actual use is included in the training data. Suppose you're developing a retail website and building a classifier to predict whether the user is likely to stay and view another page or leave the site. If the classifier predicts they're about to leave, the website might pop up something that offers incentives to continue shopping. An example of a feature that contains leaked information would be the user's total session length, or the total number of pages they viewed during their visit to the site. This total is often added as a new column during a post-processing phase of the visit log data, for example. This feature has information about the future, namely how many more visits the user is going to make. That's impossible to know in an actual deployment. A solution is to replace the total session length feature with a page visit in session feature that only knows the total pages visited so far in the session and not how many are remaining. A second example of leakage might involve trying to predict if a customer on a bank's website was likely to open an account. If the user's record contains an account number field, It might normally be empty for users still in the process of exploring the site, but eventually is filled in once the user does open an account. Clearly, the user account field is not a legitimate feature that it should be used in this case, because it may not be available at the time the user is still exploring the site. Another example of future information leaking in the past might be if you were developing a diagnostic test to predict a particular medical condition. The existing patient dataset might contain a binary variable that happens to mark whether or not the patient had surgery for that condition. Obviously, such a variable would be highly predictive of the medical condition. There are many other ways predictive information could leak into this feature set. There might be a certain combination of missing diagnosis codes that was very indicative of the medical condition. But again, these would not be legitimate to use since that information isn't available while a patient's condition is still being studied. Or finally, another example in the same patient dataset might involve the form of the patient ID. The ID might be assigned depending on a particular diagnosis path. In other words, the ID could be different if it's the result of a visit to a specialist, where the initial doctor determined that the medical condition was likely. This last example is a great illustration of the fact that there are many different ways data leakage could occur in a training set, and in fact, it's often the case that more than one leakage problem is present at once. Sometimes fixing one leaking feature can reveal the existence of a second one, for example. As a guide, here are some additional examples of data leakage. We can divide leakage into two main types: leakage in the training data, typically where test data or future data gets mixed into the training data, and leakage in features, where something highly informative about the true label somehow gets included as a feature. One very important cause of data leakage is performing some kind of preprocessing on the entire dataset whose results influence what is seen during training. This can include such scenarios as computing parameters for normalizing and rescaling, or finding minimum and maximum feature values to detect and remove outliers, and using the distribution of a variable across the entire dataset to estimate missing values in the training set or perform feature selection. Another critical need for caution occurs when working with time series data, where records for future events are accidentally used to compute features for a particular prediction. The session length example that we saw was one instance of this, but more subtle effects can occur if there are errors in data gathering or missing value indicators. If a feature relates to collecting at least one record in a time span, the presence of an error may give away information about the future. In other words, that no further observations are to be expected. Leakage in features includes the case where we have a variable like diagnosis ID in a patient record that we remove, but neglect to also remove other variables, known as proxy variables, that contain the same or similar information. The patient ID in the case where the ID number had clues about the nature of the patient's diagnosis due to the admission process was an example of this. In some cases, dataset records are intentionally randomized or certain fields anonymized that contain specific information about a user, such as their name, location, and so on. Depending on the prediction task, undoing this anonymization can reveal user or other sensitive information that is not legitimately available in actual use. Finally, any of the above examples we've discussed here could be present in a third-party dataset that gets joined to the training set as an additional source of features. So always be aware of the features in such external data and their interpretation and origin. So how can you detect and avoid data leakage in your applications? Before building the model, exploratory data analysis can reveal surprises in the data. For example, look for features very highly correlated with the target label or value. An example of this from the medical diagnostic example might be the binary feature that indicated a patient had a particular surgical procedure for the condition. That might be extremely highly correlated with a particular diagnosis. After building the model, look for surprising feature behavior in the fitted model, such as extremely high feature weights or very high information gain associated with a variable. Next, look for overall surprising model performance. If your model evaluation results are substantially higher than the same or similar problems on similar datasets, then look closely at the instances or features that have most influence on the model. One more reliable check for leakage, but also potentially expensive, is to do a limited real-world deployment of the trained model to see if there's a big difference between the estimated performance suggested by the model training and development results and the actual results. This check that the model is generalizing well to new data is useful, but may not give much immediate insight into if or where the leakage is happening, or if any drop in performance is due to other reasons like classical overfitting. There are practices you can follow to help reduce the chance of data leakage in your application. One important rule is to make sure that you perform any data preparation within each cross-validation fold separately. In other words, if you are scaling or normalizing features, any statistics or parameters that you estimate for this should only be based on the data available in the cross-validation split and not the entire dataset. You should also make sure that you use these same parameters on the corresponding held-out test fold. If you're working with time series data, keep track of the timestamp that's associated with processing a particular data instance, such as a user's click on a web page, and make sure any data used to compute features for this instance does not include records with a later time than the cutoff value. This will help ensure you're not including information from the future in your current feature calculations or training data. If you have enough data, consider splitting off a completely separate test set before you even start working with a new data set, and then evaluating your final model on this test data only as a very last step. The goal here is similar to doing a real-world deployment, to check that your trained model does generalize reasonably well to new data. If there's no significant drop in performance, great, but if there is, leakage may be one contributing factor, along with the usual suspects like classical overfitting. For more real-world examples, analysis, and guidance about preventing data leakage, you can take a look at the optional readings provided in the lesson plan. Unsupervised machine learning involves a wide variety of tasks where, unlike supervised learning, there's no target value to be predicted. Instead, the job of the unsupervised learning algorithm is to take the raw data and capture some interesting structure in it. This is useful for a number of scenarios: to explore and visualize the structure in a complex data set, to do density estimation to predict the probabilities of events, to compress the data, to extract more effective features before applying a supervised learning algorithm, or to discover important structures like clusters of similar objects or unusual or individual outliers in the data. All of these and other unsupervised learning tasks have in common the property that there are no target values, labels, or output to learn from or to be predicted. Instead, we only have the unlabeled samples in the dataset as input. Here's an example of an unsupervised method called clustering. Suppose you're in charge of running a website that allows people to buy products from your company, and the site gets thousands of visits per day. As people access the site by clicking links to products or typing in search terms, their interactions are logged by the web server that creates a large log file. It might be useful for your business to understand who's using your site by grouping users according to their shopping behavior. For example, there might be a group of more expert users who use more advanced features to find something very specific, while another group of non-expert users might just enjoy browsing a broader set of items. By clustering users into groups, you might gain some insight into who your typical customers are and what site features different types of users find important. You could use insights from clustering users to improve the site's features for different groups, or to recommend products to specific groups that would be more likely to buy them. So in this lecture, we'll give a brief survey of unsupervised learning methods, divided into two major categories. First, we'll look at one family of unsupervised methods called transformations, because they essentially just run the original data through some kind of useful process that extracts or computes information of some kind. Then we'll look at the other broad family of unsupervised learning methods, which are the clustering methods, like in our website example, that find groups in the data and assign every point in the dataset to one of the groups. Okay, let's look at some important unsupervised learning methods that transform the input data in useful ways. One method, called density estimation, is used when you have a set of measurements scattered throughout an area and you want to create what you can think of as a smoothed version over the whole area that gives a general estimate for how likely it would be to observe a particular measurement in some area of that space. For example, in a medical application related to diagnosing diabetes, density estimation with one variable might be used to estimate the distribution of a specific test score, the plasma glucose concentration number from a blood test, for people who have a particular form of diabetes. With this density estimate, we can estimate the probability that anyone with that medical condition has a particular glucose score, even if that specific score wasn't seen in the original dataset. We could then compare this to the range of glucose levels for people who do not have that condition, which is shown by the red line here. Often, density estimates are then used in further machine learning stages as part of providing features for classification or regression. The more technical way to say this is that density estimation calculates a continuous probability density over the feature space, given a set of discrete samples in that feature space. With this density estimate, we can estimate how likely any given combination of features is to occur. In scikit-learn, you can use the kernel density class in the sklearn neighbors module to perform one widely used form of density estimation, called kernel density estimation. Kernel density is especially popular for use in creating heat maps with geospatial data, like this one. Another very important family of unsupervised learning methods that fall into the transformation category are known as dimensionality reduction algorithms. As the name suggests, this kind of transform takes your original dataset that might contain, say, 200 features, and finds an approximate version of the dataset that uses, say, only 10 dimensions. One very common need for dimensionality reduction arises when first exploring a dataset, to understand how the samples may be grouped or related to each other, by visualizing it using a two-dimensional scatter plot. One very important form of dimensionality reduction is called principal component analysis, or PCA. Intuitively, what PCA does is take your cloud of original data points and finds a rotation of it so that the dimensions are statistically uncorrelated. PCA then typically drops all but the most informative initial dimensions that capture most of the variation in the original dataset. Here's a simple example of what I mean with a synthetic two-dimensional dataset. Here, if we have two original features that are highly correlated, represented by this cloud of points, PCA will rotate the data so the direction of highest variance, called the first principal component, which is along the long direction of the cloud, becomes the first dimension. It will then find the direction at right angles that maximally captures the remaining variance. This is the second principal component. In two dimensions, there's only one possible such direction at a right angle to the first principal component, but for higher dimensions there would be infinitely many. With more than two dimensions, the process of finding successive principal components at right angles to the previous ones would continue until the desired number of principal components is reached. One result of applying PCA is that we now know the best one-dimensional approximation to the original two-dimensional data. In other words, we can take any data point that used two features before, x and y, and approximate it using just one feature, namely its location when projected onto the first principal component. Here's an example of using scikit-learn to apply PCA to a higher dimensional dataset, the breast cancer dataset. To perform PCA, we import the PCA class from sklearn decomposition. It's important to first transform the dataset so that each feature's range of values has zero mean and unit variance. And we can do this using the fit and transform methods of the standard scalar class, as shown here. We then create the PCA object, specify that we want to retain just the first two principal components to reduce the dimensionality to just two columns, and call the fit method using our normalized data. This will set up PCA so that it learns the right rotation of the dataset. We can then apply this properly prepared PCA object to project all the points in our original input dataset to this new two-dimensional space. Notice here, since we're not doing supervised learning and evaluating a model against a test set, we don't have to split our dataset into training and test sets. You see that if we take the shape of the array that's returned from PCA, it's transformed our original dataset with 30 features into a new array that has just 2 columns, essentially expressing each original data point in terms of 2 new features representing the position of the data point in this new two-dimensional PCA space. We can then create a scatter plot that uses these 2 new features to see how the data forms clusters. In this example, we've used a dataset that has labels for supervised learning, namely the malignant and benign labels on cancer cells, so that we can see how well PCA serves to find clusters in the data. Here's the result of plotting all the 30 feature data samples using the 2 new features computed with PCA. We can see that the malignant and benign cells do indeed tend to cluster into 2 groups in this space. In fact, we could now apply a linear classifier to this two-dimensional representation of the original dataset, and we can see that it would likely do fairly well. This illustrates another use of dimensionality reduction methods like PCA to find informative features that could then be used in a later supervised learning stage. We can create a heat map that visualizes the first 2 principal components of the breast cancer dataset to get an idea of what feature groupings each component is associated with. Note that we can get the arrays representing the 2 principal component axes that define the PCA space using the PCA.components_ attribute that's filled in after the PCA fit method is used on the data. We can see that the first principal component is all positive, showing a general correlation between all 30 features. In other words, they tend to vary up and down together. The second principal component has a mixture of positive and negative signs. But in particular, we can see a cluster of negatively signed features that covary together and in the opposite direction of the remaining features. Looking at the names, it makes sense this subset would covary together. We see the pair mean texture and worst texture, and the pair mean radius and worst radius varying together, and so on. PCA gives a good initial tool for exploring a dataset, but may not be able to find more subtle groupings that produce better visualizations for more complex datasets. There's a family of unsupervised algorithms called manifold learning algorithms that are very good at finding low-dimensional structure in high-dimensional data and are very useful for visualizations. One classic example of a low-dimensional subset in a high-dimensional space is this dataset in 3 dimensions, where the points all lie on a 2-dimensional sheet with an interesting shape. This lower dimensional sheet within a higher dimensional space is called a manifold. PCA is not sophisticated enough to find this interesting structure. One widely used manifold learning method is called multidimensional scaling, or MDS. There are many flavors of MDS, but they all have the same general goal: to visualize a high-dimensional dataset and project it onto a lower dimensional space, in most cases a 2-dimensional page, in a way that preserves information about how the points in the original data space are close to each other. In this way, you can find and visualize clustering behavior in your high-dimensional data. Using a technique like MDS in scikit-learn is quite similar to using PCA. Like with PCA, each feature should be normalized so its feature values have 0 mean and unit variance. After importing the MDS class from sklearn manifold and transforming the input data, you create the MDS object, specifying the number of components, typically set to 2 dimensions for visualization. You then fit the object using the transformed data, which will learn the mapping, and then you can apply the MDS mapping to the transformed data. Here's an example of applying MDS to the fruit dataset. And you can see it does a pretty good job of visualizing the fact that the different fruit types do indeed tend to cluster into groups. An especially powerful manifold learning algorithm for visualizing your data is called TSNE. TSNE finds a two-dimensional representation of your data such that the distances between points in the 2D scatter plot match as closely as possible the distances between the same points in the original high-dimensional dataset. In particular, TSNE gives much more weight to preserving information about distances between points that are neighbors. Here's an example of TSNE applied to the images in the handwritten digits dataset. You can see that this two-dimensional plot preserves the neighbor relationships between images that are similar in terms of their pixels. For example, the cluster for most of the digit 8 samples is closer to the cluster for the digits 3 and 5, in which handwriting can appear more similar than to, say, the digit 1, whose cluster is much farther away. And here's an example of applying TSNE on the fruit dataset. The code is very similar to applying MDS and essentially just replaces MDS with TSNE. The interesting thing here is that TSNE does a poor job of finding structure in this rather small and simple fruit dataset, which reminds us that we should try at least a few different approaches when visualizing data using manifold learning to see which works best for a particular dataset. TSNE tends to work better on datasets that have more well-defined local structure. In other words, more clearly defined patterns of neighbors. Aside from transformations, the other family of unsupervised learning methods are the clustering methods. The goal of clustering is to find a way to divide up a dataset into groups, called clusters, so that groups of similar data instances are assigned to the same cluster, while very dissimilar objects are assigned to different clusters. If new data points were being added over time, some clustering algorithms could also predict which cluster a new data instance should be assigned to, similar to classification, but without being able to train the clustering model using labeled examples in advance. One of the most widely used clustering algorithms is called k-means clustering. K-means clustering finds k cluster centers in different regions of the feature space that it thinks represent very different groups. You need to specify the value of k ahead of time, which is one of the drawbacks of k-means. For some problems, we may know the number of classes the data should fall into, but for many other tasks, we might not. K-means operates by first randomly picking locations for the k cluster centers. Then it goes back and forth between two steps. In the first step, given the locations of existing cluster centers, it assigns each data point to a cluster center based on its distance from the center. In other words, it assigns each data point to the closest center. Then in the second step, it adjusts the locations of each cluster center. It does this by setting the new cluster center to the mean of the positions of all the data points in that cluster. Somewhat magically, after running this alternating process for a while, coherent clusters do start to form, and the cluster centers and the corresponding cluster assignment for each data point eventually settle down to something stable. Now, one aspect of k-means is that different random starting points for the cluster centers often result in very different clustering solutions. So typically, the k-means algorithm is run in scikit-learn with 10 different random initializations, and the solution occurring the most number of times is chosen. Here's a step-by-step example. We first choose 3 locations in the space randomly to be the cluster centers. Then we assign each data point to the cluster with the nearest center. Now, for each cluster, we compute the mean location of all points in the cluster and use that as the new cluster center for the next iteration. Here's the second iteration of the first and second steps. Eventually, after 20 or 50 or 100 steps, things settle down to converge on one solution, as shown here. K-means clustering is simple to apply in scikit-learn. You import the k-means class from sklearn cluster, Create the k-means object, setting the value of k by specifying the n clusters parameter, and then calling the fit method on the dataset to run the algorithm. One distinction should be made here between clustering algorithms that can predict which center new data points should be assigned to, and those that cannot make such predictions. K-means supports the predict method, and so we can call the fit and predict methods separately. Later methods we'll look at, like agglomerative clustering, do not and must perform the fit and predict in a single step, as we'll see. Here's the output from the notebook code showing the results applied to the fruits dataset, where we know the value of k ahead of time. Note that k-means is very sensitive to the range of feature values, so if your data has features with very different ranges, it's important to normalize using min-max scaling, as we did for some supervised learning methods. Because each cluster in k-means clustering is defined entirely by its center point, it can only capture fairly simple types of clusters. K-means clustering tends to work well when the data points form into groups of roughly the same size with simple globular shapes that are well separated. K-means will tend not to do well if the data forms long, irregular clusters, for example. Also, the version of k-means we saw here assumed that the data features were continuous values. However, in some cases we may have categorical features where taking the mean doesn't make sense. In that case, there are variants of k-means that can use a more general definition of distance, such as the k-medoids algorithm that can work with categorical features. Agglomerative clustering refers to a family of clustering methods that work by doing an iterative bottom-up approach. First, each data point is put into its own cluster of one item. Then, a sequence of clusterings are done, where the most similar two clusters at each stage are merged into a new cluster, and this process is repeated until some stopping condition is met. In scikit-learn, the stopping condition is the number of clusters. Here's a visual example of how agglomerative clustering might proceed on a sample dataset until 3 clusters are reached. In stage 1, each data point is in its own cluster, shown by the circles around the points. At stage 2, the 2 most similar clusters, which at this stage amounts to the finding the closest points, are merged, and this process is continued as denoted by the expanding enclosed regions that denote each cluster. You can choose how the agglomerative clustering algorithm determines the most similar cluster by specifying one of several possible linkage criteria. In scikit-learn, the following 3 linkage criteria are available: Ward, average, and complete. Ward's method chooses to merge the 2 clusters that give the smallest increase in total variance within all clusters. Average linkage merges the 2 clusters that have the smallest average distance between points. Complete linkage, which is also known as maximum linkage, merges the 2 clusters that have the smallest maximum distance between their points. In general, Ward's method works well on most data sets, and that's our usual method of choice. In some cases, if you expect the sizes of the clusters to be very different, for example, that one cluster is much larger than the rest, it's worth trying average and complete linkage criteria as well. To perform agglomerative clustering in scikit-learn, you import the agglomerative clustering class from sklearn_cluster. When initializing the object, you specify the n clusters parameter that causes the algorithm to stop when it has reached that number of clusters. You call the fit_predict method using the dataset as input, and it returns a set of cluster assignments for the data points, as shown here. One of the nice things about agglomerative clustering is that it automatically arranges the data into a hierarchy as an effect of the algorithm, reflecting the order and cluster distance at which each data point is assigned to successive clusters. This hierarchy can be useful to visualize using what's called a dendrogram, which can be used even with high-dimensional data. Here's the dendrogram corresponding to the Ward's method clustering of the previous dataset example. The data points are at the bottom and are numbered, and the y-axis represents cluster distance, namely the distance that 2 clusters are apart in the data space. The data points form the leaves of the tree at the bottom, and a new node parent in the tree is added as each pair of successive clusters is merged. The height of the node parent along the y-axis captures how far apart the two clusters were when they merged, with the branch going up representing the new merged cluster. Note that you can tell how far apart the merged clusters are by the length of each branch in the tree. This property of a dendrogram can help us figure out the right number of clusters. In general, we want clusters that have highly similar items within each cluster, but that are far apart from other clusters. For example, we can see that going from 3 clusters to 2 happens at a fairly high y value, which means the clusters that were merged were a significant distance apart. We might want to avoid choosing 2 clusters and stick with 3 clusters that don't involve forcing a merge for clusters that have very dissimilar items in them. Scikit-learn doesn't provide the ability to plot dendrograms, but SciPy does. SciPy handles clustering a little differently than scikit-learn, but here's an example. We first import the dendrogram and ward functions from the SciPy cluster hierarchy module. The ward function returns an array that specifies the distances spanned during the agglomerative clustering. This ward function returns a linkage array, which can then be passed to the dendrogram function to plot the tree. Typically, making use of this hierarchy is most useful when the underlying data itself follows some kind of hierarchical process so that the tree is easily interpreted. For example, hierarchical clustering is especially useful for genetic and other biological data, where the levels represent stages of mutation or evolution. But there are other data sets where both k-means clustering and agglomerative clustering don't perform well. So we're now going to give an overview of a third clustering method called dbScan. dbScan is an acronym that stands for Density-Based Spatial Clustering of Applications with Noise. One advantage of dbScan is that you don't need to specify the number of clusters in advance. Another advantage is that it works well with datasets that have more complex cluster shapes. It can also find points that are outliers that shouldn't reasonably be assigned to any cluster. dbScan is relatively efficient and can be used for large datasets. The main idea behind dbScan is that clusters represent areas in the data space that are more dense with data points, while being separated by regions that are empty or at least much less densely populated. The two main parameters for dbScan are min samples and EPS. All points that lie in a more dense region are called core samples. For a given data point, if there are min sample other data points that lie within a distance of EPS, that given data point is labeled as a core sample. Then, all core samples that are within a distance of EPS units apart are put into the same cluster. In addition to points being categorized as core samples, points that don't end up belonging to any cluster are considered as noise, while points that are within a distance of EPS units from core points, but not core points themselves, are termed boundary points. Here's an example of dbScan applied to a sample dataset. As with the other clustering methods, dbScan is imported from the sklearn cluster module. And just like with agglomerative clustering, dbScan doesn't make cluster assignments for new data, so we use the fit-predict method to cluster and get the cluster assignments back in one step. One consequence of not having the right settings of EPS and min samples for your particular dataset might be that the cluster memberships returned by dbScan may all be assigned the label -1, which indicates noise. Basically, the EPS setting does implicitly control the number of clusters that are found. With dbScan, if you've scaled your data using standard scaler or min-max scaler to make sure the feature values have comparable ranges, finding an appropriate value for EPS is a bit easier to do. One final note, make sure that when you use the cluster assignments from dbScan, you check for and handle the -1 noise value appropriately, since this negative value might cause problems, for example, if the cluster assignment is used as an index into another array later on. Unlike supervised learning, where we have existing labels or target values to use for evaluating the effectiveness of the learning method, It can be difficult to evaluate unsupervised learning algorithms automatically, since there's typically no ground truth to compare against. In some cases, as in the breast cancer example, we may have existing labels that can be used to evaluate the quality of the clusters by comparing the assignment of a data point to a cluster with the label assigned to the same data point. But there are many cases where labels are not available. In addition, in the case of clustering, for example, there's ambiguity in the sense that there are typically multiple clusterings that could be plausibly assigned to a given data set, and none of them is obviously better than another unless we have some additional criteria, such as performance on a specific application task that does have an objective evaluation, to use as a basis for comparison. For example, in cases where the results of the clustering are used as features for supervised learning, we could use the overall classifier accuracy gain from adding these clustering-based features as a measure of success for the underlying clustering. Another issue with evaluating clustering algorithms is that it can be hard to automatically interpret or label the meaning of the clusters that are found. And this is still a step that requires human expertise to judge. As you've probably gathered by following the variety of topics in this course, the world of machine learning encompasses a broad set of ideas and methods, and the field itself continues to advance rapidly. So the goal of a survey course like this one is to cover the most important basic concepts and visit a few of the more important and interesting areas, and hopefully inspire you enough to continue exploring after you finish the course. I've put together this course so it's not only a source of lectures and assignments, but also a collection of useful readings you can draw on based on my experience in this area that I've chosen for you as good starting points to continue your learning in different aspects of machine learning. By now we've covered quite a bit of ground, starting with an understanding of the general concepts and workflow of applied machine learning, and then getting some exposure to a variety of learning algorithms for important tasks like classification and regression, along with an understanding of the important parameters that control model complexity for these algorithms. You should now have a better understanding of critical problems like overfitting and data leakage, along with an idea for some strategies you can use for detecting and avoiding these problems. We've covered how machine learning algorithms are evaluated and how to tune their parameters to optimize different evaluation criteria that may be appropriate for different tasks. Finally, we've applied these ideas with the help of notebook examples and assignments to gain more experience with a very powerful machine learning library in Python, scikit-learn. I want to say something briefly about an important family of machine learning tasks that we've touched on in this course, but didn't focus on specifically, and that is machine learning that involves text. This includes problems such as email spam detection and classifying web pages by topic. The course following this one in our data science series focuses specifically on text mining and machine learning with text. So if you have a particular interest in diving into the use of natural language processing with machine learning, I encourage you to check it out. Thanks for your interest in this course. I've really enjoyed putting together this tour through the fascinating field of machine learning. I hope this course helped you in some way along whatever path of exploration you might have. And as always, we welcome your feedback on any aspect of this course. Thank you, and all the best in your own future learning.